TOC, theory of computation. T means theory, O means of, C means computation. What is a symbol? Symbol is the basic building block. What happens if I see one more A or B? So let me discuss the cross product method now. If you look at deterministic machines and non-deterministic machines, most of the machines we use in our daily life, we have regular languages and we have deterministic context-free languages and we have context-free languages. But then it is a multi-tape Turing machine. It is going to have 3 tapes, a proper subset of context-sensitive languages, which means a finite set is less than, countable set is less than uncountable set. Having this final state is not just enough, that final state should be reachable from the initial state. So let me start this subject. Today I am going to discuss TOC, theory of computation. T means theory, O means of, C means computation. So by this name, you must be understanding that this is something about computation. So what is computation? Computation is nothing but any task that can be performed by a calculator or a computer. So we are going to mathematically model a computer or any machine in general, and then we are going to study the theory about it. Which means what are the capabilities of this machine, what are the problems that could be solved by this machine, and what are the limitations of such a machine. Okay, so the basics of this subject are, I'm going to discuss all the basics now. Right, first of all, the basics of the symbol is, the basic of the subject is a symbol. What is a symbol? Symbol is the basic building block in this subject of TOC, and a symbol can be any letter like this or anything. Even you can have pics. This is a symbol. From a symbol we can form alphabet. This is generally represented by sigma. Sigma is also called as alphabet. So the alphabet is nothing but some collection of these symbols. For example, A comma B. Now once if you define the alphabet, all these strings, okay, what is a string? I'm going to discuss it. Everything will be based on this set, this predefined set called alphabet. So you can have any number of alphabet, any number of symbols in the alphabet. In this sense, you can even have ABC, or you can even have 0, 1, or you can even have 0, 1 to 9. It is a finite set and it can be anything. Okay, and from the alphabet we are going to discuss a string. A string is a sequence of the symbols, which is nothing but, example is, let us say A. If alphabet is A comma B, small a is a string over this alphabet which is of length 1, and small b is also a string of alphabet which is of length 1, and AA is also a string of the alphabet which is of length 2, AB, BC, so on. So maybe if you consider this alphabet, some of the interesting questions are, how many strings of length n are possible over this alphabet? How many strings of length 2 are possible over this alphabet? Length 2. Okay, so you can say AA, AB, BA, BB, which means 4. Now I am asking you, how many strings of length n are possible? Length n are possible. We have n blank spaces and we have 2 options to fill in with, right? So what are the 2 options? Either A or B, either A or B, so on, which means 2 into 2 into 2 into so on n times, so which is 2 power n. So in fact you can even extend this concept to any alphabet. Since we have only 2 symbols in this alphabet, we have got 2 power n. So in general, if you have n symbols, or let us say the number of sigmas in this sigma, if they are represented by mod sigma, then the number of strings of length n possible over sigma is sigma power n. Sigma power n. So just think about it, just revise what we have seen till now. First thing is symbol. What is a symbol? Symbol is the smallest building block in TOC. And if you take few symbols, we can form an alphabet. Once we have defined an alphabet, we are going to form strings using only the symbols in that alphabet. So symbol, alphabet and string. Okay. Now using this, I am going to define few more things. Next thing is language. Language. What is a language? So we know what a string is. Even if you consider English language is nothing but collection of words, isn't it? So in TOC, a language is nothing but collection of strings, isn't it? So for example, let us say sigma equal to a comma b. Then languages can be defined like this. Language L1 equal to, you can represent it say set of all strings of length 2. So using this alphabet sigma, what are set of all strings of length 2 we can form? So definitely the set is going to be AA, AB, BA, BB. So if you can check it, if sigma is a comma b, then the set of all strings of length 2 is nothing but AA, AB, so on 4. And in fact, this set is a finite set. So I can call that L1 is a finite language. Okay. So let us define one more language, L2. Let us say L2 is set of all strings of length maybe 3. Set of all strings of length 3 over the same alphabet sigma equal to a comma b. Then L2 is going to be A, B, A, B, A, B, 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 A, B, A, B, 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 A, B, B, B. Right? So there are 8 strings. Again, this L2 is also finite. Let us say L3. L3 is, let's define it like this, set of all strings over the same alphabet sigma equal to a comma b, where each string starts with a. So that equal to, I am interested in set of all strings where each string should start with a. So the smallest string which starts with a is small a, right? And the next biggest string which starts with a is either AA or AB. And the next string which starts with a, see, starting with a, starting with a, starting with a. And the next string which starts with a is A followed by AA, or A followed by AB, or A followed by BA, or A followed by BB, so on, so on. So if you look at this language L3 is infinite. If you look at these languages L1 and L2, they are finite. So now you have seen that a language which can be formed over a sigma, which can be formed over a alphabet, can be finite or infinite. Okay, please make a note of this. Fine. I'll be moving on to the next topic. Powers of sigma. So first thing is sigma power 1. So if, let us say, we have defined sigma as a comma b, which means our input alphabet contains only two symbols, small a and small b, only two symbols. Now sigma power 1. Sigma power 1 is nothing but set of all strings which can be formed over a comma b, which are of length exactly 1. Again, sigma power 1 is set of all strings over sigma of length exactly 1, okay? So they are simply a and b. So we can extend this definition as sigma square. Sigma square equal to sigma concatenated with sigma, that is nothing but a comma b concatenated with a comma b, that equal to, so how can I concatenate these two sets is 1, a concatenated with a is a concatenated with b is a b concatenated with a is b concatenated with b is b. Set of all strings, and all these strings are always formed over the same alphabet, so I'm not going to mention it. All these strings of length 2. Okay, and the next one is sigma cube. So as you might have guessed by now, sigma cube is nothing but all the strings of length 3, and there will be exactly, and if you look at it, the sigma cube is set of all strings of length 3, and the cardinality of this set is going to be 8, so on. Sigma power n. Sigma power n is set of all strings of length n, which is nothing but n length strings. So let us say sigma power 0. Sigma power 0 is set of all strings of length 0. Set of all strings of length 0. So the smallest string which is of length 0 is sigma power 0 contains a special symbol called epsilon. So it is also called as a null string, and I am going to use epsilon, this symbol, to represent a string of length 0. This is a special symbol. This one is a special symbol of length 0. So just remember that epsilon is a special symbol of length 0, and I can even write it like this. Length of epsilon is 0, and everything else is same, right? So string is, you have to just see the number of symbols, and then you can say the length of the string. But only for epsilon, just remember that the length of epsilon is 0. Okay, so if you want to make a note of it, please do it. I'll be moving on to the next topic. Next important concept is sigma star. So sigma star is nothing but, in place of star you can substitute any number starting from 0. Again, in place of star you can substitute any number starting from 0. So sigma power star is sigma power 0 union sigma power 1 union sigma power 2, so on. So what is sigma power 0? As you know, sigma power 0 is simply 0. Let us define sigma first. Sigma for this question is a comma b, and the sigma can change from question to question. Okay, so in this question for sigma star, it is going to be, sigma power 0 is going to be epsilon union sigma power 1 is going to be a comma b union sigma power 2 is going to be a ab BA, BB, so on. Finite or infinite? Obviously it is infinite. And if you see this, maybe by looking at this definition or by looking at these sets, you can conclude that sigma star is nothing but set of all strings possible over a comma b, which means set of all strings possible over a comma b of all lengths. So maybe you can call it as the mother of all languages, or maybe you can call it as the universal set. So sigma star contains all possible strings possible over a comma b. Sigma star contains everything that includes a comma b. Finite or infinite? Obviously it is infinite. Okay, so this is about sigma star. Once we define sigma and sigma star, next thing is we can define a language. So we have already seen that language L1, L2 and L3 previously are nothing but sets of strings. L1 and L2 are finite and L3 was infinite. I mean, in the previous example, if you can remember it. So we have already seen that there are some finite languages and there are some infinite languages. Now you can see this, either this L1 or L2 or L3 are actually parts are present in this. So I can even write it like this. So L1 is actually a subset of sigma star, L2 is also a subset of sigma star, and L3 is also a subset of sigma star. Okay, so now we have languages. We have sigma, which is alphabet, we have sigma star, which is set of all strings possible over the alphabet, and then we have chosen some subsets which are nothing but the languages. So a language is nothing but any subset. It can be finite or infinite, which you should be able to define precisely. And these are all the languages possible over sigma star. There are how many languages are possible over sigma star? Infinite. Number of strings possible over sigma is infinite, and the number of languages that are possible over sigma star are infinite. And now the question is, why are we discussing about strings and why are we discussing about languages? Where are we going to use it in practice? There are many applications, there are many practical applications, but I would like to take just one example and tell you where we are going to use them at practice. Okay, so you can consider the C programming language. Let us assume we have the language, the C programming language. Okay, if you look at the C programming language, what are the symbols that we type when we are writing a program? Maybe you type the symbols like this: small a, small b, so on, small z, capital A, capital B, so on, capital Z, 0, 1, so on, 9, and some special symbols like plus, star, so on. So this is a finite set. We are going to always use a finite number of symbols in order to represent a C program, in order to type a C program. And now you can call this as sigma for the C program. So the alphabet for any C program is going to be this. The alphabet for any C program is going to be this, which is obviously a finite. Always remember, alphabet is going to be finite. It is never going to be infinite. Okay, and next one is, using these strings or using these symbols, we are going to form a string, right? So if you write like this, void main something, and then int a comma b, so on, and close it. This is nothing but a string. This is actually a program in C. In C it is a program, but coming to TOC, it is nothing but a string, isn't it? Sigma is nothing but alphabet when you come to TOC, and is nothing but set of all symbols which are allowed when you look at C programming language. And now a program is nothing but a string. Interesting. Now the question is, what is C programming language? What is C programming language? C programming language is nothing but set of all valid programs. Set of all valid programs. So when I say, the important word is valid, which means there can even be invalid programs which will give you some error when you are going to compile it or when you try to run it. So the interesting question here is, what are the valid programs? And given any program, how can I say that the program is valid and the program is invalid, right? So first question is, how many strings will be there in the C programming language, or how many programs are possible over C programming language? Answer is infinite. You can write any number of valid C programs, like let us say P1 is a program, P2 is a program, P3 is a program, so on, infinite. So the C programming language is going to be infinite. Now the next question is, given a program Pn, given any program Pn, how can you say that it is valid? We can say that it is valid if the program is present in this set, in this language. Now the question is, how can I find out whether a given string is in the language or not? Or let's go to C programming language. How can you find out that a program is valid, and how can you find out that there are no errors in the program? So smallest thing, maybe the naive answer is, you can ask me to save set of all possible programs on a computer and then just check if this program Pn is a part of that all the programs or not, which means that the smallest solution or the simplest solution we can think of is save all these programs on the computer, and given a program, go on scanning programs one by one, and if there is a match, we can say that it is valid. But the problem with this is, any computer will have a finite memory, but then the number of programs possible is infinite. So obviously we cannot do this. So we are mainly interested in this. Given a language and a string. Now the interesting question I want to ask is whether this string is present in this language or not. If the language is finite, yes, you can enumerate all these strings in your memory, and then given a string, we can scan all these strings one by one and we can check if this is present or not. But the problem is, if the language is infinite, obviously we cannot store all these strings in the language on a computer. Therefore, entire thing boils down to small point. I'm going to erase this, please make a note of it. So now the entire thing is going to boil down to this. If L is finite, let us say example is, if sigma equal to a comma b, let us say L1 equal to set of all strings of length 2, AA, AB, BA, BB. If this is the language, and if I give any string, let us say AAA, and if I ask a question whether this string is present in this language or not, you could take each string and then examine each string and then verify each string and then verify, and you can say that it is not there. Since the language is finite, you can do it. But what if the language is infinite? Let us say language L2 is set of all strings which are going to start with A. Then the language is A, 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 B, so on. There are lots of strings, right? So if any string is given, let us say string given is B, A, B, A. And if I ask you whether this string is present in this language L2 or not, then the problem is how long should I be comparing this? See, don't say that maybe by looking at the first symbol, it is very clear that string is not in the language. Yes, for us it is clear. But then for a machine, it doesn't think this way. It doesn't think logically. You have to give it a method, right? So, so if this language is infinite, if you use the method of linearly searching all these strings and then matching it against, then the language will take forever, or the machine will take forever to answer this question. So the simple thing is, how can you, given a language, come up with a finite representation and some finite representation which can be stored in the memory, using which if I give a string, now you should be able to say yes, this string is in the language, or no, this string is not in the language. Now for a language, I want a finite representation. Whatever you could do, I want to store it on a computer in a finite amount of memory and then execute on this using this, and given a string to this finite representation, I want to say whether this string is present in the language or it is not present in the language. That is the simplest thing. Okay. So maybe let's take an example and see what this finite representation could be. Okay. So I'm going to erase this. You can make a note of it. The finite language, see what is the finite representation is the simplest or the smallest machine. It is also called as a machine. Okay, so let us say given a language, I will try to construct some finite representation which is called a finite automata, and then using this finite automata, if I give a string to this finite automata will say yes, I accept this string, no, I reject this string, which means the string is present in the language or the string is not present in the language. Before discussing about what a finite automata is and what are the types of finite automatas, I would like to take a small example and maybe we shall discuss the definitions later. Fine. So let us say I'm drawing some finite representation for a language. L1 is a language which is set of all strings. So we have seen that a problem or a DFA where we constructed the DFA for set of all strings of length exactly 2. Now what if the question is construct a DFA which accepts set of all strings over a comma b where the string length is at least 2. Now I want to construct a DFA for set of all strings over a comma b, DFA for set of all strings over a comma b such that length of the string is at least 2, greater than or equal to 2. So how can we construct it? First of all, identify the sigma. Sigma is nothing but a comma b. And now we have to identify the words. The language contains set of all strings of length greater than or equal to 2. So strings of length 2, AA, AB, BA, BB, and strings of length 3, AAA, so on, BBB, so on. Finite or infinite? Definitely the language is infinite. If a language is finite, we will be able to give finite automata. But if the language is infinite, we don't know whether we will be able to give finite automata or not. But then we shall try. We shall try to give a finite automata for this. So as usual, take the smallest string and give the skeleton and then try to understand the states. Try to understand the states. This is in the language, so I am accepting it. Now try to understand the states. What does this state represent? This state represents set of all strings of length 0. What does this state represent? This state represents set of all strings of length 1. Set of all strings of length 2. If I see small a or small b, it makes they are all these strings of length 1. Then if I see a followed by a or a b followed by a and a followed by b or b followed by b, all these are set of all strings of length 2. So according to the question, I have even accept set of all strings of length 2 and I have accepted set of all strings of length 2 here because this is the final state. Now, is this a DFA? No, it is not the DFA. The reason is for state A and state B, we have shown the transitions on small a, small b, but for state small c, we didn't show any transition. For the state C, we didn't show any transition. How? So we have to decide about what happens if I see one more A or B. Already we have seen a string of length 2 and we have reached C. And now if you see one more A or B, that is nothing but strings of length greater than or equal to 2. Therefore, I am going to accept it. Why? Because all the strings which are greater than or equal to 2 have to be accepted. So if you look at this, we have 3 states and the C is the final state and C even represents set of all strings of length 2 or more. 2 is because of these 2 transitions and more is because of this one. Now let's see the problem where we want to design a DFA which accepts set of all strings over a comma b such that length of the string is less than or equal to 2. We have seen exactly equal to 2. We have seen at least 2. Now it is at most 2. This is at most 2. Okay. So what does this contain? This contains set of all strings of length 0 because 0 is less than 2, of length 1 and of length 2. So if I enumerate the language is going to be set of all strings of length 0 which is sigma and epsilon and set of all strings of length 1 which is a comma b and set of all strings of length 2 which is aa, ab, ba, bb. What can you say about the language? It is finite. Since the language is finite, we will definitely be able to give finite automata. So whenever the language is finite, obviously you have to give the skeleton taking the biggest string. So I'm going to do like this. I'll be giving for this a, accept it. Okay. Now let's talk about the relevance of these states according to this problem. Now the first state, let's call it A, represents set of all strings of length 0, and the second state, this one, let us call B, represents set of all strings of length 1. C represents set of all strings of length 2. I can write like this. Why? Because A or B is set of all strings of length 1 and followed by A or B is nothing but set of all strings of length 2. So whatever we wanted to accept, we have to accept epsilon. Always remember, whenever we have to accept epsilon in a DFA, make initial state equal to final state. There is no other way we can accept a epsilon in a DFA other than this. Therefore, always make this one as final state. And we have to even accept A or B. Therefore, I have to make this one also final. So 0 length, 1 length, 2 length. Is this the DFA? Final answer? I think it is not the DFA. Why? Because A and B are complete, but for C, we didn't give any transition on A or B. So just think about what will happen if I see small a or small b at state C. This will lead to any string of length 3, and we should not accept it because maximum length that is accepted is 3. So this is nothing but set of all strings of length 3 and more. Because of this loop, 3 or more. And this is going to act as a dead state, because once I reach the state D, there is no way I can again come back and reach any of the final states. Therefore, the D is dead state. So this is the minimal finite automata. Okay, so whenever I was discussing about DFAs, keep one thing in mind. I was drawing everything, I was designing this just with practice. When you try to do the same, when you try to construct the DFAs on your own, you might get some other answer, and that answer might be right. So given a language, you can draw many DFAs. A language may contain many DFAs, but then it will always contain only one minimal DFA. If you draw any DFA for this language using minimum number of states, which is 4, you should always get this. You can even construct a DFA which will have more states and which is also right, but then I am interested in minimal DFAs. There is a procedure to construct a DFA, a correct DFA, and then minimize it into this, but then try drawing the DFA as minimal as possible, because it will help you in the exam. Till now we have seen 3 kinds of problems. One is string length is exactly 2. The string length is exactly 2. And the other is string length is at least 2. And the other is string length is at most 2. So let's just see the diagrams. String length is exactly 2. A or B, I'll accept it, and if I get anything else, I'm going to reject it. String length is at least 2. A or B, I'll accept it, and anything I'll accept it. Next one, string length is at most 2. A or B, 0 length string, 1 length string, 2 length string, and A or B. I'll reject it. So now if you look at this, the number of states in the string of length 2 is 4, and in the string of length greater than or equal to 2 is 3, less than or equal to 2 is 4. So why do you think that we need 2 states here? 4 states here. 3 states are required to put the string of length 2 onto it. These 3 states are definitely required, and then 1 state is required because I don't want to accept anything greater than 2. Here 3 states are required because 2 states are used to put the string of length 2, and then the third state is just going to accept anything. And here also 3 states are required to accept strings of length 2, and then one more state is used to not to accept anything greater than 2. Therefore, in general, if I have to accept strings of length n, then the number of states required is n plus 2. Number of states required in a minimal DFA which accepts set of all strings whose length is n plus 2. Now number of states required in a minimal DFA which accepts set of all strings whose length is greater than or equal to n, which means whose length is at least n is n plus 1, and whose length is at most n is n plus 2. This is an important point. You please try to remember this because it is a frequently asked gate question. Okay. Now, let us say we want to construct a minimal DFA which accepts set of all strings over a comma b. W is a string over a comma b such that if I take the length of W and if I divide it with 2, If I take length of W and if I divide it with 2, then the remainder should be 0. So what does this mean? It means that if I take a string whose length is, if I take the length of a string and if I divide it with 2, the remainder should be 0, which is nothing but the length of the string should be even. If I take any even length string and if I divide the length of it by 2, definitely the remainder is going to be 0. If I take any odd length string, it is going to be 1. So how should I start it is, let's write down the language. What does the language contain? Language will definitely contain set of all strings of length 0, which is nothing but epsilon, and set of all strings of length 2. So what are all the strings of length 2? AA, AB, BA, BB, and set of all strings of length 4. A, so on, B, so on. Finite or infinite? Definitely the language is infinite. Why is it infinite? Because we have lot of strings, and it is not finite because we don't have any upper bound on the length of the string. The condition is it has to be divisible by 2. So whenever the language is infinite, we don't know whether we can give finite automata or not. But then let's just try using the previous methods we have learned. Let us say the first state indicates set of all strings of length 0. If I see A or B, it indicates set of all strings of length 1. So I have to accept set of all strings of length 0 because epsilon is there in the language, and I should not accept set of all strings of length 1 because A or B are not in the language. And then next one is, if I go to one more state on seeing A or B, this represents set of all strings of length 2 and which are there in the language. Therefore, I have to accept it. If I see one more A or B, it is going to be set of all strings of length 3. I should not accept it. A or B, set of all strings of length 4. I should accept it. So on. So if I use this method, the finite automata is never going to end. In fact, then it should not be called a finite automata. Why is it called a finite automata? Is the number of states inside the finite automata is finite. That is the reason we are calling it as finite automata. And now if you make it infinite, it is definitely not a finite automata. So let's try to decrease the number of states using some method, some intuition. See, actually I want to differentiate between two things. One is even length and other is odd length strings. I don't want to distinguish the strings between every length. I just want to distinguish it between two classes. One is even length strings and other is odd length strings. Let us see if I can do it. This is odd length, this is even length. If I get one more A or B, it is odd length. A or B 1 length, A or B 1 length, 1 length, 2 length, 3 length. If I get one more A or B, 4 length. If I get one more A or B, 5 length. If I get one more A or B, 6 length. If I get one more A or B, 7. One more A or B, 8. So on. So this is nothing but set of all strings of odd length strings. Right? And this is nothing but even length strings. So this is definitely a finite automata. And this is definitely deterministic finite automata. It is finite automata because the number of states are finite, and it is deterministic finite automata because for every state we have shown what to do on small a and small b. It is definitely DFA, but then it is not minimal. The reason is I can even try to minimize it. Let us say when my purpose is to distinguish only between two classes of strings, one is class of strings whose length is even, other is class of strings whose length is odd, then I will have only two states. One state is going to accept even length strings and other state is going to accept odd length strings. Okay, so see this. This is nothing but strings of length even, strings are of length odd. Okay, so 0 length, 1 length. If I get one more A or B, this is going to be 2 length, 3 length, 4 length, 5 length, 6 length, 7 length. Therefore, this is the final DFA which accepts set of all strings whose length is divisible by 2. What if I want to accept set of all strings whose length is not divisible by 2, which is set of all strings whose length when divided by 2 is 1, which means set of all odd strings. So how can I solve this problem? you can take the same one. This state, initial state, indicates set of all strings of length 0, and on seeing a comma b, if you accept it, this is set of all strings of length 1. On seeing a comma b, set of all strings of length 0, of length 1, of length 2, of length 3, 4, 5, 0, 1, 2, 3, 4, 5, so on. So this will accept odd length strings, this will accept even length strings. So by looking at this problem, we can even analyze it in another way. When a number is divided by 2, we get two possible remainders. One is remainder can be 0 and the remainder can be 1. That is why I am having two states. If the question is the string length has to be divisible by 3, then we will get 3 states. Why? Because when we divide any string with a number 3, then the possible remainders are 0, 1, 2. So in the previous problem we have counted number of A's and number of B's in one method where we divided all the strings into 4 classes. One is even, odd, even, odd, right? So now I am going to discuss some other method in which we can access the same language. So now again the problem is same. Let us say I wanted to count set of all strings, or I wanted to draw a DFA for set of all strings over a comma b in such a way that number of A's in W is even, which means if I take number of A's, it should be even. If I divide the number of A's with 2, remainder should be 0, and number of B's in W should be even. So yesterday we have seen that I classified set of all strings into 4 classes. According to this problem, we have 4 classes. One is number of A's can be even, number of B's can be odd, odd, even, odd, and then odd, odd. We have seen those 4. Now let us try to do it in a different manner using some other method. This is also called as cross product method. First thing is we want to count number of A's as well as we want to count number of B's. So let me draw it like this. Independently I am going to do. First thing is counting A's. I'm counting A's. Capital A, B. So this is going to count 0 A's, 1 A, 2, 3, 4, 5, which is nothing but this state A represents even number of A's and state B represents odd number of A's. I am not going to count B's, so B's are going to be here. Okay, now I will count B's. Counting B's. Okay, so same, but then I am going to use different names. Let us say this is state C and let us say this is state D. 0 B's, 1 B, 2 B's, and number of A's I don't count. Number of A's I don't count, and the even number of B's is this. Now I want to combine these two. I'm going to combine these two using a method called cross product. So first of all, I'm going to discuss this cross product method, and then I'll be changing the problem and doing it in another way. So let me discuss the cross product method now. So in the problem, there are two independent DFAs and the initial final state is A and final state is B. So the cross product method goes like this. First write number of states in this. A comma B cross. Now write number of states in this. C comma D. This is going to give a cross product of this. So I'm going to combine two sets. So I'm going to get ordered pairs, and this ordered pair I'm going to write it like this. AC, AD, BC, BD. I have 4 states: AC, AD, BC, BD. Okay. So since in the initial, now when I apply the cross product, I got 4 states, and since in the initial diagrams A and C are the final states, here AC is going to be final state. I'll talk about it later. Okay. First of all, we know that there are 4 states, so I'm just going to draw 4 states. One is A, C, okay, and the other is A, D, okay, and the other is B, C, and the other is B, D. I'm drawing just 4 states, okay. And now, after drawing these states, I should know the transition. For example, I should know what is the transition of AC on small a. In order to know this, go to the original diagram and see what A is doing. Capital A on small a is going to capital B, and capital C on small a is going to capital C. Therefore, AC on small a is going to BC. So I'm going to write it like this. Okay, so understand this. I have initially constructed the DFAs independently, and then I'm trying to club them. It is also called as cross product method. So when I'm trying to merge them, the diagram is going to look something like this. Though we know that there are 4 states, now I have to fill up the transitions. I'll take a state and then I'll see what is the transition I wanted, AC on small a. Therefore, I'll go to the original diagram and see what capital A is doing on small a and what capital B is doing on small a. So capital C is doing on small a. So I got that. I have to go to BC. Okay, and now AC, again AC on small b. Let us see what is AC doing on small b. So if you look at AC on small b, capital A is going to capital A itself, and capital C on small b is going to capital D. Therefore, AC on small b is going to AD. Fine. Now let us see BC. Let us talk about BC. BC on small a, B on small a is going to A, and C on small a is going to C itself. Therefore, BC on small a is going to AC. BC on small a is going to AC. Okay. Now, what about BC on small b? Capital B on small b is going to B itself. Therefore, B, and capital C on small b is going to capital C on small b is going to D. Okay. So it is going to be like this. So BC on B is going to BD. Okay. So BC is done, AC is done, BC is done. Now let's take AD. AD on small A on small a is going to B, and D on small a is going to D itself. Therefore, AD on A is going to BD. Right? And now AD on B. A on B is going to A, and D on B is going to C. So AD on B is going to AC. Fine. So AC, BC, AD are done. Now let's talk about BD. BD. BD on A. So B on A is going to capital A, and D on A is going to capital D. So BD on small a is going to AD. BD on small a is going to AD, and BD on small b. Look at this. BD on small b is going to B itself, capital B, and D is going to C. So BD on small b is going to BC. So that is how I filled it up. Now if you can compare the previous question and this question, it looks exactly the same. The diagram looks exactly the same, and in fact AA is nothing but even number of A's and even number of B's. AC is nothing but even number of A's and even number of B's. And now BC is nothing but odd number of A's and even number of B's. And AD is nothing but even number of A's and odd number of B's. And this one is nothing but odd number of A's and odd number of B's. So according to the problem, both the A's and B's have to be even, therefore AC has to be the final state. Or even if A and C, in the original diagram A and C are the final states, so whatever is the combination, I am going to take it as the final state. And now this model can be extended to any number of questions. What are the other possible questions they can ask us is, the question can even be, here let us say they have asked for AND, which means if they ask for number of A's and number of B's, if the question is number of A's is even and number of B's is even, then we have seen that EE is the final state. Only one final state, which is EE, or in this case AA. In the previous question EE, both are same, right? The question can even be number of A's is even or number of B's is even. What if this is the question? Which means either the number of A's can be even or the number of B's can be even. So see this, first one is E should be the final state, definitely. Why? Because number of A's and number of B's both are even. And moreover, EO can even be final state because number of A's is even, and OE can even be final state because number of B's can be even. So in this case, if I have OR, I'll get more than one final state. Only state which will not be a final state in this question is O, which means odd odd. Odd odd should not be there in this case, because if the string contains odd number of A's and odd number of B's, it is neither even number of A's or even number of B's. So the question can be extended to any level. You can use your imagination and frame many other questions. But for now, this is enough. And this is one method of forming the answer. I will just tell you one more method in which we can even solve such questions. That will be the easiest way. And one point worth noting here is the cross product method. If a automata, a DFA, contains n number of states, and if other DFA contains m number of states, then the final DFA which is obtained by cross producting of these two will contain n cross m, n into m number of states. Which means if one automata contains 2 number of states and if the other one contains 2 number of states, then the cross product is going to contain 4 number of states. So similarly, you can extend this question to any number. For example, how I can draw it without using this cross product method is, if you observe this question, just observe this diagram, just focus on this diagram. Okay, so if you see this, it is going to be number of A's are counted horizontally and number of B's are counted vertically. Just observe this for some time. Number of A's are counted horizontally, right? And number of B's are counted vertically, which means like this. So I can even extend this question to the next level also, which means you can even check number of A's and number of B's to be, let us say, number of A's is multiple of 3. Let us just change the question, or let me just explain this with the same one in a different diagram. Let us say I want to draw a diagram in which number of A's have to be multiple of 2 and number of B's have to be multiple of 2. Then the diagram is going to look something like this. A's are being covered horizontally, counted horizontally. A's are being counted horizontally and B's are being covered vertically. B's are counted vertically. Right? You can directly draw it like this. Till now we have seen various kinds of DFAs and many problems about it. Now let's consider NFA. NFA is non-deterministic finite automata. NFA, non-deterministic. So what is the difference between deterministic finite automata and non-deterministic finite automata is, if we are starting from a state, from one particular state, on seeing some input, let us say W, if we are starting from state Q1, it will go to some particular state Q2 or Qn or something. But in non-deterministic, if you are starting from a state Q1, on seeing a input W, there is no guarantee that you will end up in only one state. You might end up in many states, Q1, Q2, so on, Qn, or you might even end up in nothing, right? So non-determinism means, if you are starting from one state, if you see an input, if you are going to be in none of the states, or if you are going to be in many states, or you can even be in one state, that is non-determinism. So if you look at deterministic machines and non-deterministic machines, most of the machines we use in our daily life, for example, if you take a computer, or you can take any mechanical device, or you can take us, even the human beings, we are all deterministic, which means we cannot make copies of ourselves, many copies of ourselves, depending on the input. But then in case of non-deterministic machines, yes, it can make many copies, and non-deterministic machines are not real, which means no real machine can actually be non-deterministic. But then the question is, if the non-deterministic machines are not real, then why are we studying about it? The reason is this: sometimes some of the problems have to be solved or can be solved by exhaustive search, which means we have to search all possible solutions, and backtracking. So exhaustive search and backtracking is a method which might give us some better solutions. So if you take any game, let us say I have taken a game chess, based on your move, the final output will decide. So at every step you have to take some move, and based on your move, the final output will be decided, which means you might either win or lose. But then if you change the move now, there can be a change in the output. If you take any deterministic machine, the way it plays is, it will take only one decision at any step, and then it will either lose or win. But a non-deterministic machine can take many moves at the same time, and it will produce all possible combinations by the end. Therefore, some of them may win and some of them may lose. So non-determinism is very important if you have to search about exhaustive search and backtracking. And determinism is important if you don't want to do any backtracking. Though non-determinism can be implemented by a deterministic machine, sometimes it is possible that non-deterministic machine can be implemented even by using a deterministic machine, but then it is somewhat difficult. But then it can be implemented. Okay, so let's see what is NFA, non-determinism, when it comes to the case of NFA, finite automatas. Okay, so in order to define NFA, NFA can be defined this way. NFA is a quintuple, which means a 5-tuple set, which will contain Q, sigma, delta, Q naught, and F. So you have seen all this before in the case of DFA also, where Q is set of states. We have seen this, set of states which has to be obviously finite. Since this is a finite automata, the set of states have to be finite. And sigma is, as you know, input alphabet. So it has to be a finite set. And let's talk about delta later. Q naught is start state. And capital F is a set of final states. Now the important point is, what is delta? In order to explain about delta, I would like to take an example of an NFA, and then we can decide about what exactly the delta is. So I would like to construct an NFA, non-deterministic finite automata. See this? I want to construct an NFA, non-deterministic finite automata, where it accepts the language in which every string ends with a small a, and let us consider sigma equal to a comma b. So the construction of NFA is very simple compared to construction of DFAs, and when you have to consider a DFA, it is somewhat difficult. But then once you learn about NFA, you will definitely say that NFA is very much easier compared to DFA. So if you have to accept all these strings which are going to end with small a, then you can draw it this way. String can start with anything, but it has to end with a, then only I am going to accept it. So let us name them as A and B. If you observe it, it is definitely not DFA, because on capital B, the state capital B, I didn't decide about the inputs, which means what happens if I get a or B. Moreover, if you look at capital A, I am giving you two ways. One is on seeing small a, you stay in the same state or go to the next state. So I'll show you how the acceptance is being done. Now let us enumerate the language. The language contains set of all strings which are going to end with a. Therefore, language is going to contain a because it is ending with a, or a because it is ending with a, or ba, so on. Right? So let us take a small example. Let us take a. A is in the language. Initially, you will be starting from capital A. This NFA will be starting from capital A, and on seeing small a, it will either go to capital A. On seeing small a, it will either go to capital A, or on seeing small a only, it is even going to capital B. This is called non-determinism. Non-determinism means from one state, on seeing one input, you are not going to exactly one state. You might go to more than one state, or sometimes you might even go to no state also. So if you see this example, now I say that the string A is accepted by NFA if I start from an initial state and if I reach some set of states out of which at least one state is final. If I could reach at least one state starting from initial state, then I say that the string is accepted by NFA. Okay, so let us take some other example which is not in the language. Let us say the example is ending with B. Now let us say AB is the example. AB is the string where it is ending with B. Now I'll start with capital A. On seeing small a, I'll go to capital A as well as I'll go to capital B state. Now on seeing small b, capital A will go to capital A itself, but capital B does not have any move on B. Capital B does not have any move on B. That is also called as dead configuration, which means it will not lead us to any state phi. So finally we ended up only in one state, which is A, and A is a non-accepting state. Therefore AB is rejected because from starting from initial state capital A, I am not able to reach any of the final states. Therefore AB is rejected, right? And you can see the non-determinism here. Right? So how can I write the transition function is, if you look at the state diagram here for this example, delta is a function, transition function, which will take a state capital A, and it will take a input symbol from sigma, and then it can go to either one state or zero state or more than one state, which means it can go to any number. 2 power q is nothing but power set of q, which means it can take a state q and then it can take an input from sigma, and then it can go to any subset of states possible. So for this example, let's see how it is going to work. Now let me explain you how this one exactly works. Let us say q is a comma b in this example, and then sigma is small a comma small b. Now I am going to write q cross sigma. Q cross sigma equal to capital A small a, capital A small b, capital B small a, capital B small b. This is q cross sigma. Now it has to be from q cross sigma to 2 power q. 2 power q is nothing but power set of q. Power set of q is set of all possible subsets. So what are all possible subsets of q? If you take this set capital A, capital B, what are all possible subsets? One is 5, empty set. Other is capital A, capital B, which are singleton sets, and the other is capital A, capital B, containing the entire thing. Right? So if you see this q cross A like this, just look at the diagram. Capital A on small a, where is it going? Capital A on small a is going to either A or B. So what is the state? This one, AB. And capital A on small b is going to only A. And capital capital B on small a is not going anywhere, which means 5. And capital B on small b also goes to 5. Therefore, if you see this diagram, it is actually showing you this relation. This is the main difference. This is the main difference between NFA and DFA. If you look at DFA, delta is from a state on looking at a symbol, I'll go to only one state. From a state on looking at a symbol, I'll go to one state. But if you look at NFA, from a state on looking at a symbol, I'll go to some subset of states which are possible. So 5 can be possible, or singleton sets can be possible, or even the entire thing can be possible, right? So maybe if you look at these two, you may even understand that Q is also a part of 2 power Q. Therefore, you can say that every DFA is NFA. Every DFA is NFA. Now let's take a problem of complementing an NFA. We have already seen the complementation in case of DFA, and in DFA what did we see? If we complement a DFA, the language accepted by the DFA is getting complemented. But in case of NFA, it is not true. So let us take one example and I'll show you how the complementation of NFA is going to affect the language accepted by the NFA. Fine. So let us say I want to construct an NFA which accepts set of all strings over A comma B, where each string starts with A, NA. Fine. So NFA is going to just look like this: A comma B. That's it, right? Let us say we have two states, A, B, and now A is the initial state, B is the final state. If it is going to start with A, I am going to accept. I am not going to talk about what happens to A if it sees a B. That will go to a dead configuration, and I am not going to talk about it. Okay? Why? Because it is NFA. Let us represent this NFA as M. Now if I complement the NFA, see, complementing a language is different and complementing the NFA is different. If I complement the NFA, what is complementing of NFA? Make the non-final states as final states. What are the non-final states here? Only A. Make it final state and make the final states non-final. This is the final state, make it as non-final and leave all the other edges as it is. This is the NFA. Now, what is the language accepted by M, the original NFA? The language accepted by original NFA is set of all strings which are going to start with A, B, so on. And what is the language accepted by M complement? Let us say L1 is the language accepted by the initial NFA M, and L2 is the language accepted by the complemented NFA M complement. Then what is it? It is simply only epsilon. if I see A, it is going to other state and it is not going to accept it, and B, there is no chance that it is going to accept it. So just look at these two. You can find out that L1 is not equal to L1 complement is not equal to L2. What is L1 complement? L1 complement should contain epsilon as well as strings starting with B, but then it is only containing epsilon. Where are the strings starting with B? See, if I take the entire sigma star to be this, one will contain starts with A, so for which there is the machine, whatever it is, the language L1, and the L1 complement it will even contain epsilon as well as starts with B, but then we got only epsilon, which means if I complement a NFA, the language need not get complemented, which means let us assume that I have an NFA M. If I apply the complementation and if I get NFA M complement, if the original language is accepting language L1, then the complemented language, this one, the language accepted by the complemented NFA need not necessarily be the complement of this, and sometimes it may be complement, right? So you have to get one point here. Complementing an NFA is different and complementing the language is different. So I'll try to frame two questions here, try to get the difference. See, first point is, when we complement a DFA, definitely the language accepted by the DFA is going to be complemented, but when I complement a NFA, the language accepted by the NFA need not get complemented. It may or may not get, okay? So I'll try to give you two statements, maybe try to understand them. One is, the question may be, what is the language accepted by complement of NFA, and the other question is, what is the complement of language accepted by NFA? Both are different. See this. First one is, what is the complement of the language accepted? What is the language accepted by complement of NFA? Which means take the NFA and do the complementation of the NFA and then find the answer. And the other one is, what is the complement of the language accepted by the NFA? Which means take the language accepted by the NFA, find out the language and then complement the language. Both are very different. Okay, you have to understand the difference. Why? Since the complementation of NFA need not necessarily complement the language, therefore these two questions are very different. What is the language accepted by complement of NFA and what is the language accepted by, I'll just take an example and explain you. Let us assume that this is the NFA given. This is the NFA given directly, and nothing else is given. They didn't give you anything. Okay. Now if the question in the gate is, what is the complement of language accepted by this NFA? If this is the question, then you have to find the language accepted by this NFA and then complement the language. What is the language accepted by the NFA? Language accepted by the NFA is set of all strings which are going to start with A, which means A, AB, A, so on. Now you have found out the language. After finding the language, find the complement of the language, right? So for this question, answer is, the complement of the language accepted by this finite automata is NFA is epsilon as well as strings starting with B, BB, BA, BBB, so on. Now, if the question is, what is the language accepted by complement of the following NFA. If this is the question, take the NFA and complement it. If I take the NFA and complement it, it is going to look like this. This is the NFA's complement. Now, what is the language accepted by complement of it? It is epsilon. Therefore, answer is this. For the first question, the answer is epsilon as well as all strings starting with B. For the second one, the answer is this one. If they had given you a DFA, the answer for both the questions would be same. So from this question, you should understand that if I complement a NFA, the language need not necessarily get complicated, but then complemented. But then there are cases where if you complement NFA, the language may get complemented. So what is the best example for that? Since every DFA is an NFA, you can take a DFA and say that it is an NFA and then complement the language and you'll get the complement of it, right? So these two questions are important. Till now we have seen DFAs, many questions for which we have constructed DFAs and NFAs, but then I told you that whatever answers I have given you are the minimal DFAs, which means if you construct a DFA on your own, you might not get the same answer which I got, but then I have got all the minimal DFAs because of experience, that's it. Now the question is, can we take any finite automata, any DFA, only DFAs, can we take any DFA and prove that this is the minimal or that such a DFA can even be minimized? So that is called minimization. So if a DFA is given, then we can apply a procedure using which we can decrease the number of states in the DFA. It is also called as minimization of a DFA. So before going for minimization of a DFA, let's talk about how we can minimize it, or what are the properties that we need in the DFA so that it can be minimized. We want to talk about states and equivalence between the states. Let us say there are two states, one is P and another is Q. We say that these two states are equivalent and these two states in a DFA can be replaced by a single state if the condition is, if P on seeing W, which means the state P on seeing any input symbol, on seeing any input string, so W can be any input string, if this one goes to final state, it implies that Q also goes to final state, one of the final states. If in case P does not go to final state, then it implies that Q also does not go to final state. Try to understand this. Now, if I have two states, let us say PQ, when can I combine them into single state is, they both have to be equivalent. I say that P and Q are equivalent when P on seeing any input string, if it is going to one of the final states, implies that Q should also go to one of the final states. Need not go to the same final state, but then they should be either final state or non-final state. If P is going to non-final, then Q should go to non-final. So if any two states follow this property, then we can say that such two states are called equivalent. If length of W is, mod W is 0, then both states P and Q are called 0 equivalent. 0 equivalent. If length of W is 1, which means if I see a single symbol and if they are following this property, then I can say that both states are 1 equivalent. If length of W is 2, then I can say that both are 2 equivalent. In general, if length of W is n, then I can say that both these states are n equivalent. And finally, if for every possible W, if this is the property being followed by P and Q, then I can say that both these states are equivalent, and instead of having two different states, I can merge these two states into one, and I can decrease the number of states in the final answer. So why to use this equivalence property and 0 equivalence, 1 equivalence, 2 equivalence? I'll take an example and I'll explain you with that. So let us say this is the finite automata DFA. So we are going to minimize only DFAs, not NFAs. This is the final automata, which is a DFA, and I want to minimize the number of states in this. First step is identify the start state and identify the final state. Now, in this DFA, if there are any states which are unreachable or unaccessible or inaccessible, which means if there is any state if let us say there is a state like this Q5, and it is simply like this, A and B. If there is any state to which we cannot reach from the initial state, then we have to delete it. Step number 1 is try to delete all the states to which we cannot reach from the initial state. If you look at this diagram, all the states are reachable from initial state. Q0 is obviously initial state, Q1 is reachable, Q2 is reachable, Q3 is reachable, Q4 is reachable. All the states are actually reachable from the initial state. Now, find out or draw the transition table, state transition table. Q0, Q1, Q2, Q3, Q4. A, B. Q0 on A is going to Q1 and Q0 on B is going to Q2. You can let us see the diagram. And Q1 on A is going to Q1 and Q1 on B is going to Q3. And Q2 on A is going to Q1 and Q2 on B is going to Q2. And Q3 on A is going to Q3 on A is going to Q1, Q3 on B is going to Q4, Q4 on A is going to Q1 and Q4 on B is going to Q2. What is initial state? Initial state is Q0. What is the final state? Final state is Q4. Therefore, Q4 I am going to mark it like that, and wherever Q4 is there, I just mark it like that. Okay. Now, first point is try to find out the 0 equivalent states, 0 equivalent sets. Try to find out the 0 equivalent sets. Right here, 0 equivalent sets. So 0 equivalent sets are nothing but try to separate non-final states from final states. What are the non-final states? Q0, Q1, Q2, Q3. What are the final states? Q4. So initially this is the starting point. Start with 0 equivalent. 0 equivalent states are, these are all 0 equivalent and these are all 0 equivalent, which means set of all non-final states and set of all final states. Once it is done, now we have to find out 1 equivalent states. Now take the previous states. For example, you have to see, let us say previous state is in the previous 0 equivalents, take each one of them. See, all these states are 0 equivalent, so we have to see whether they are 1 equivalent or not. Let us take Q0 and Q1. Q0 and Q1, and let us see if they are one equivalent or not. If in order to see that, you have to take both of them and see where they are going on symbol A and symbol B. If you see Q0, it is going to Q1, and if you see Q1, it is going to Q1. Both are going to the same state. And if you see Q0, it is going to Q2, and if you see Q1, it is going to Q3. In the previous state, in the zero equivalent state, Q0 and Q3 are in the same, or I'll just draw a diagram here and I'll show you. See this? Now I'm checking for 1 equivalence of Q0 and Q1. So go to the diagram and you just draw like this: Q0 and Q1, these two, Q0 and Q1, these two. Now these two have to be in the same state in the above state. In the above state, which is 0 equivalent, Q1 and Q2 are in the same group, and Q2 and Q3 are in the same group. Therefore, you can say that Q0 and Q1 are one equivalent. Now, let us say these two are one equivalent. Now we have to see if Q2 is equivalent with any one of them. So, if we have to see if Q2 is equivalent with any one of them, if you have to see if Q2 is equivalent with any one of them, you can take either Q0 or Q1 and check with Q2. See this? I am taking Q0 or Q1. Q0 and Q2. Q0 is here, Q2 is here. Q0 is here, Q2 is here. Just check them. Q0 and Q2 both are going to Q1, which is there in the same state, and both are going to Q2. When they are going to same states, they are obviously equivalent. Therefore, Q2 is equivalent to Q0. Since Q1 is equivalent to Q0 and Q2 is equivalent to Q2, therefore Q1 is equivalent to C. Already we know that these two are equivalent. Now we found out that these two are equivalent. Therefore, Q2 and Q1 are also equivalent. Now we have to check if Q3 is equivalent with any of these three. So you can take only one and you can check it. So you can take any one. Let me take Q2 and Q3 and check for the equivalence. So I'll take Q2 and Q3 and check for the equivalence. Q2 is where? Q2 is here and Q3 is here. Now see them. Q2 on A, they both are going to Q1, so on A it is not a problem. But on B, one is going to Q2, other is going to Q4. One is going to Q2, other is going to Q4. So both are going to different states here, different groups here. Since they are going to different groups, they are not in the same state, or they are not equivalent, one equivalent. Therefore, Q3 only is not one equivalent with the others. See, try to understand it. When I am writing one equivalence, I will be using the information only about zero equivalent. When I am writing two equivalent, I will be using the information about one equivalent. You will understand this with more examples. I will solve more examples, don't worry. See, now I want to find out two equivalent states. In order to find out two equivalent states, again start with the same thing. This is also called as partitioning method. There is one more method called table filling method. I am not going to discuss it and it is very difficult. This one is pretty easy, right? Let us talk about two equivalent. Now, already Q3 and Q4 are the only people in their groups, or are the only states in their groups. So there is nothing to do about them. They are saying that we are not equivalent with any states. So therefore, we cannot combine Q3 and Q4 anymore. Now we have to decide whether we can combine Q2 and these three, Q1, Q2 and Q0. Now let us take Q0 and Q1 and see if they are equivalent or not. Q0 and Q1 and see if they are equivalent or not. Q0 and Q1. So these are the outputs I need to see. Now see this, Q0 and Q1 both are going to Q1 only. That is not a problem. Why? Because they are going to same state. Now on B, one is going to Q2, other is going to Q3. One is going to Q2, other is going to Q3. Both are in different groups. Whenever they are in different groups in the previous equivalence, in this equivalence they are not equivalent. Which means in one equivalent state, if they are going to different groups, then in two equivalent they are not equivalent. Which means Q0 and Q1 are definitely not one equivalent. Now what about Q2? See, Q0 and Q1 both got separated. I don't know whether Q2 is equivalent to Q0 or Q1. Where should I place? Whether here or here. So I'll just check it. Now let me see if Q0 and Q2 are equivalent. Q0 and Q2 are equivalent. In order to check it, if I have to check for two equivalent, go to the one equivalent and use this table. Q0 and Q2. These two. See this? On Q0 and Q2 on A, both are going to Q1, and on B, both are going to Q2. Therefore, definitely they are equivalent. They are going to same states. Definitely they are equivalent. So Q0 and Q2 are definitely equivalent. Now what about Q1? It got separated. What about Q3? It got separated earlier only. What about Q4? Yes, got separated. So now we know these states are saying that we are not equivalent with any other states, therefore we have to have at least these three states, and now I don't know whether these two are going to be in the same group in the 3 equivalent or not. Let us say 3 equivalent. In 3 equivalent, again I have to check Q0 and Q2 only. Now if I check Q0 and Q0 and Q2, again the same result will follow. See this? Both Q0 and Q2 are going to Q1 and Q2 only. Therefore, these two states cannot be separated, or they are just equivalent. Now check this. 0 equivalent, we got 2 groups. 1 equivalent, we got 3 groups. 2 equivalent, we got 4 groups. 3 equivalent, we got 4 groups, and all the groups are same. So continue this method until we get 2 states like this where nothing will change from one another. If you even go for 4 equivalent, you will see the same thing. So on. Go for n equivalent, you will see the same thing, which means this is the final answer. So in the final DFA, we should have only 4 states, and these 4 states are Q0, Q2, Q1, Q3, Q4. Now let us try to draw the diagram and show how does the DFA looks like. Now one state is Q0, Q2. Initially we had 2 states, now I am going to combine them as one state, and the other state is Q1 and the other state is Q3 and the other state is Q4. Okay, now look at this. Q0 on A is going to Q1 and Q0 on B is also going to Q1 only. Q0 on A is going to Q1 as well as Q2 on A is going to Q1. Therefore, Q0 or Q2 on A is going to Q1. Now, Q0 or Q2 on B is going to Q2 only. So, on B, check this. Q0 is going to Q2, therefore Q0 should go to Q2, and Q2 is going to Q2, therefore that is it. Just B. Next one, Q1 is going to Q1 on A, and Q1 is going to Q3 on B. And next thing, Q3 on A is going to Q1 and Q3 on B is going to Q4. Next, Q4 on A is going to Q1 and on B is going to Q2. So the initial diagram, this is the final diagram. So you can understand one thing. Even though there are many states in the initial diagram, they can be states can be decreased if you find out some few states which are equivalent, and then instead of having 2 different states for all the equivalent states, you can have 1 state. Let us say if there are n states which are equivalent, for all those n states we are going to have 1 state in the final diagram. Now, let us consider the finite automata with output. Till now, we have seen finite automatas without output. So, one is DFA and other is NFA. Now, let us even consider the finite automatas where they will take an input as well as they will keep on writing the output. For example, we have 2 kinds of machines. One is Murray machine and other is Mealy machine. So in order to discuss about Murray machine as well as Mealy machine, we are going to see the common part of them. Both of them can be represented by Q, sigma, delta, Q0, capital delta and lambda. Okay. This is lambda and this is capital delta. Now, both of them can be characterized using these values. What does Q mean is, Q is the finite set of states. If you take an example, so both are containing some states, Q0, Q1, so on like that. So Q is finite set of states and sigma is input symbol, input alphabet. So it is simply like, we have seen before what is sigma, same in input alphabet, and delta is transition function. It is worth noting here, transition function is defined as Q cross sigma to Q. So what it means is, a transition function or the transitions in the finite automatas of Murray or Mealy are going to depend on the state, the current state Q and the input. So depending on the current state and the input, they are going to change their state. So it is same as DFA. Therefore, you can even call both of them as DFAs. So both are deterministic. You should not call them as DFA, but then both are deterministic. So both Murray machine, Murray machine and Mealy machine both are deterministic. And Q0 is input alphabet, or sorry, in the initial state, and capital delta is output alphabet. So what is output alphabet? Output alphabet is nothing but the symbols which are supposed to be printed, or the symbols which will be outputted by these automatas is nothing but output alphabet. And capital delta is output function. What is output function is, this function will determine what will be printed as the output. So the only difference between Murray machine and Mealy machine is only the lambda. So if you look at Murray machine, in Murray machine, lambda is a function of, see this, lambda is a function from Q to delta, which means for every state, input is output is associated. For example, for every state, this is the output 0, for this state 1 is the output. So lambda says that for every state, output is associated. So in this case, especially in this diagram, for this Q0, output associated is 1, and for this Q1, output associated is 0. And if you look at Mealy machine, in Mealy machine, output is associated like this. For a state, for a given input, there will be some output. For a state, for a given input, there will be some output, which means, let us say state Q0. For a state Q0, for the given input A, output is 1, which is nothing but, for state Q0, if the input is A, then output will be 1. Similarly, for a state Q0, if input is B, then output will be 0. See, for a state Q0, if input is B, output will be 0. For a state Q1, if input is B, output will be 0. For the state Q1, if input is A, output will be 1. So the only thing you have to remember is, Murray machine is going to associate a symbol or the output with the state itself, and the Mealy machine is going to associate output as a combination of the current state as well as the input. So one thing, how you can remember it is, if you write Murray spelling, M-O-O-R-A, Murray spelling, then you can see these two O's, 1 output. First O is 1, second O is output. That is how I remembered, which means for every state we are going to have one output. I'll take an example and I'll trace out how it really works. Let us say this is the finite automata and I don't know what is it doing exactly, but then this is just an example. So this is the Murray machine. On this Murray machine, what happens if I give an input AB? Initially I'll be in state Q0. Whenever I am in state Q0, output associated is 1. Therefore 1 will get printed. Now, on seeing a small a, I'll again go to state Q0 itself. Therefore, again 1 will be printed, and Q0 on B is going to Q1. Q0 on B is going to Q1. Therefore, in state Q1, output associated is 0. So, on seeing input AB, this particular Murray machine has printed the output 110. On seeing input AB, this particular Murray machine has printed the output 110. So you can think of it this way: if I give a string of length n as input, then the output produced will be a string of length n plus 1. If I give a string of length n as input, then the output produced will be a string of length n plus 1. This is because even without seeing anything, Q0 is going to produce something. That is the reason. Even without seeing anything, Q0 is going to produce some output. That is why after seeing inputs, again we are going to get output, and initially we are going to get one output. Therefore, n plus 1 strings or n plus 1 outputs will be formed over a string of length n. Now let's trace the example of this one, Mealy machine. Let's take the same example in Mealy machine. In Mealy machine, if I have the example of, let us say, AB itself, initially I will be in Q0. Since output is not associated with the state, it will not print anything. Only upon seeing small a, Q0 on small a, Q0 on small a, it is going to print 1. Q0 on small a is going to print 1 and it is going to enter Q0. Now Q0 on small b is going to Q1 and it is going to print 0. Therefore, here output is associated with the inputs. So if I give n bit input, then the output will be n bit. But in case of Mealy machine, if I give n bit input, output will be n plus 1 bit. In this case, if I give n bit input, then the output will be n bit. Now let's try to construct a Mealy machine. So Mealy machine is nothing but a deterministic machine in which output is associated with state, which means for every state we have only one output. Now we have to construct a Mealy machine that takes set of all strings over a comma b, which means it is going to take all the strings which are possible over a comma b as input. So input alphabet is nothing but sigma equal to a comma b. That is what they have given, and prints 1. So output, they have to print 1 as output for every occurrence of AB as substring, which means whenever I see AB, I have to print a 1 as output. Okay, so output, let us say capital delta should contain 0 and 1. So output is 0 and 1, input is a comma b. Now the problem is this: whenever I give any string which is containing AB, it should print 1. If I give AB and AB, it should print 2 ones. If I see AB, BB, AB, it should print 2 ones here, that's it. And I don't care how many zeros it is going to print. For every AB, it is going to print 1. It is nothing but discounting number of ABs. So in order to construct this, we have to decide about 3 things. One is, we can design the deterministic finite machine for set of all strings starting with AB. See, we have to count number of ABs. For that, if I use the problem of starting with AB, the problem here is we are actually seeing only one AB and we are not seeing all the remaining ABs. If I say containing AB, it will be again starting with anything and then containing AB, which means we will be seeing only one AB and after that we are not going to count. But if you take ending with AB, there we are going to actually count. Using that, we can actually count all ABs. Therefore, in order to solve this problem, I am going to construct a finite automata, or let us say a DFA, which accepts set of all strings ending with AB. Okay, so if you remember how to construct set of DFA for set of all strings ending with AB, this is how it looks like. I am not going to talk about the procedure, you already know it. Let us say ending with AB, initially I will be waiting for A and then any number of A's, that is not a problem. And if I see a I'll again wait for a B. If I see a B, I'll again wait for this. So this is actually DFA, which accepts set of all strings ending with AB, right? So if I see any number of B's, I'll be waiting for an A. So even if I get any number of A's here, it is still ending with A. So if I get a at the end, it means that entire sequence, sequence has spoiled. I have seen AB and reached this. Let us say capital A, capital B, capital C are the states. Now I have reached C on seeing a AB. If I see a at C, I have to again wait for a B. Therefore, I'll go here and wait for a B. If I see a B at C, then I have to again see AB to reach it. Therefore, whenever I reach C, I'll reach C on seeing AB. See this? I'll reach C directly on seeing AB, or AB and again when I see one more AB I'll reach it, or AB and again I can go back and again I can come. So whenever I see AB I'm actually reaching the state C. Therefore, according to the problem specification, if C is made to output 1, that can solve our problem, right? So whenever I see AB, I'll be in state C and it is going to output 1. And for the remaining states, you can simply give 0 as the input, right? So let us take an example and see this. Let us say the input is small a, small b. If I am in state capital A, if I see 0, I'll go to state capital B. And sorry, if I see A, I'll go to state capital B. If I'm state capital B, if I see a small b, I'll go to state capital C. Now, capital A is going to print 0, capital B is going to print 0, and capital C is going to print 1. Therefore, on seeing AB, I'm able to print 1. If I see AB, let's see what happens. I'll be in capital A. So capital A on seeing small a is going to capital B, and capital B on seeing small b is going to capital C, and capital C on seeing small a is going to capital B, and capital B on seeing small b is going to capital C. And now the output printed is, for A it is 0, output associated is 0, for B it is 0, for C it is 1, for B it is 0, for C it is 1. So which means for every occurrence of AB, I have printed 1, which is nothing but I have counted the number of occurrences of AB in a particular string. Okay, so this is the final answer. Till now we have seen Murray machines. Now let us see a Mealy machine. Now the question is, construct a Mealy machine. Mealy machine is nothing but for every state, for every input, there will be an output. It is not just, output is not just associated with the state. For every state, for every input, there will be an output. So the question is, construct a Mealy machine that accepts all binary strings, which means sigma input equal to 0, 1. And now we should produce 2's complement of the binary number. So therefore, output is also a binary number which should be 2's complement of the input. If I say input is some number, output has to be 2's complement of that. Assume that the string is read from LSB to MSB and n carry is discarded. Okay, so before actually doing this problem, let us try to do some simple problem where I'll take a binary number as input and I'll produce 1's complement as output. 1's complement as output. So that will be simple. What is 1's complement? Let us say if I have 0, 1, 1. What is 1's complement? 0, 1, 0, 0. Wherever you see 0, wherever you see 1, convert it to 0. Wherever you see 0, you convert it to 1. So that must be very simple. I'll be in initial state. If I see a 0, I'm going to convert it as 1. If I see a 1, I'm going to convert it as 0, and just one state is required, nothing else. So if you have to trace out and see how this one is working, I'm talking about 1's complement, not 2's complement. I didn't reach this problem yet. Okay, so if the input is 0, let us say 1, 0, 1, 1, then I'm going to start in Q0. On 1, I'll be in Q0. Q0 on 1 is going to print 0, and again on 0 I'll be in Q0 only. Q0 on 0 is going to print 1. Again on seeing 1 I'll be in Q0 itself. Q0 on 1 is going to produce 0. Again on 1 I'm going to in Q0 only, and Q0 on 1 is going to produce 0. So that is how we got 1's complement, right? So 1's complement is easy, simple. So whenever you see a 0 you are going to print 1, and whenever you see a 1 you are going to print 0. But 2's complement is not that easy, and moreover 2's complement has to be, let us talk about 2's complement first. Let us say I have a number 1 0 0 1 1 0 0. Okay, I want to find out the 2's complement. How to find the 2's complement of this? First you find 1's complement, which is 0 0 1 1, and then you add a 1. Then what do I get? 0 1 0 0. This is the 2's complement. So let's take one more example. 1 1 1 0 1 1 0 0. So I want to convert this to a 2's complement. First convert it to 1's complement. 1's complement is going to be 0 0 0 1 0 0 1 1. And now in order to convert it to 2's complement, add a 1. So what do I get? 0 0 0 1 0 1 0 0. Simply adding 1, right? 1 plus 1 is 0, and again you get a carry here. 1 plus 1 is 0, so again you get this one and carry here. So that is how you got. Now you just check these two numbers. This is the original binary number and this is the 2's complement of it. If you look at this, if I am reading from LSB to MSB, if I have zeros in the beginning or zeros from the LSB side, LSB is this least significant bit and most significant bit. If I am reading from LSB to MSB, whenever I have zeros, I am leaving them as zeros, and whenever I see first one, I am leaving it as 1, and whatever is there after that first one, it is going to be complemented. Check this. All the zeros are left as zeros, and whenever I see first one, that is left as 1, and after that, whatever I see, I am complementing this. You will understand better in this example. See? Whatever are zeros, that will be left as zeros, initial two zeros are left as zeros, and then once I see first one, that will be left as 1 itself, and after that whatever number is there, that will be once complemented, and after that whatever number is there, that will be once complemented, which means 0 1 1 1 1. You can take one more example. Let us say 1 1 1 0 0. What is the 1's complement of it? 0 0 0 1 1. What is the 2's complement of it? Add a 1 to it. Then it is going to be 1 0 1 0 1 0 0. Whatever is the least significant zeros, you are going to write it as it is, and the first one you are going to write it as it is, and after that whatever is remaining, we are going to take 1's complement of that. So by this you should understand one logic. If I am going to start from LSB, whatever are zeros there, I am going to leave them as zeros, and after seeing the first one from the LSB, I'll leave it as 1, and after that whatever I see, I am going to apply 1's complement. Again see this, whatever are zeros, I am going to leave it as zeros, and whenever I see the first one, that first one will be left as it is, and whatever is the remaining string, that will be like this. What if there are no zeros at all? Then it is going to start with 1 itself, right? What if there are no zeros at all? Let us say, you can even talk about this example, 1 0 1 1. There are no zeros at all. Let's see how it works. So it is going to be 0 1 0 0 is the 1's complement, and 2's complement is 1 0 1 0. So what happened? Whenever I see the first one, that first one is going to remain as it is, and after that everything is going to be complemented, right? So we don't care what happens after the first one. So if there are zeros, they will be left as it is, and the first one will be left as it is, and whatever is remaining on the left of it, that will be once complemented. Okay, so now let's construct the Mealy machine for this. The Mealy machine will actually look like this. I'm assuming that I'm reading from LSB. So initially I'll be in state Q0. In this state, I'll be seeing zeros and I'll be leaving them as zeros. Whenever I see a 1, I'll remember that I have seen a 1, and I'll print 1, and I'll go to next state, and this state will actually complement everything, which means if I get a 0, 0 is printed, 1 is printed, and if I get a 1, 0 is printed, right? So if I have to explain this, I'll take an example. Let us say the example is 1 0 1 1, or maybe I'll take another example, 1 1 0 0. What is 1's complement of it? 1's complement is 0 0 1 1, and what is 2's complement of it? 2's complement is 1 0 1 0 0, right? So I'll take this number 1 1 0 0 and I'll give to this automata Mealy machine, and I'll get this output. See this, 1 1 0 0, Q0 on 1 is going to Q1, and now Q1 Q naught on 1 is going to Q1 and is going to produce 1, right? And we are supposed to read from the ending, right? We are supposed to read from the LSB, which means I should write it as 0 0 1 1. Okay, now Q naught on 0 is going to produce 0 itself and stay in Q naught only. Again, Q naught on 0 is going to stay in Q naught itself and going to output 0 only. And Q naught on 1 is going to produce 1 and is going to go to state Q1. And Q1 on 1 is going to Q1 itself and is going to produce 0. So what is the answer? You have to count it in the reverse order, which means the 2's complement is 0 0 1 0 0 0 1 0. Got it? So this is how this is built. Till now we have seen many problems about Mealy machine and Murray machine. Now the question you should ask me is, which one is more powerful? So if I have to say that one is powerful than the other, one should be able to solve some problems which the other will not be able to solve. Let us say we have seen two kinds of finite automata with inputs. See, finite automata with with outputs, we have seen two types. One is Murray machine and other is Mealy machine, right? And we have constructed for many problems both of them. Now the obvious question is, which one is powerful than the other? If I have to say that Murray is powerful than the Mealy, then Murray should be able to solve some problems which Mealy will not be able to solve. Or if I have to say that Mealy is powerful than Murray, then it should be able to solve some problems which this machine will not be able to solve. But both are actually equivalent in power. If I have to show that both are equivalent on power, then I'll take a Murray machine, if I can convert it to Mealy, and if I can take any Mealy machine and if I can convert it to Murray, then we can say that both are equivalent. So in this question, let's take an example of Murray machine and convert it to Mealy. So let us say I want to count number of A's using a Murray machine. So, or I want to print out number of A's mod 3. Then the Murray machine is going to look like this. We have three states. We'll have three states: Q naught, Q naught, Q1 and Q2. So let us assume that we are counting only A's. So on A's we are counting, and on B's we will not count. So on B's we will not count. Okay. So what is the remainder in Q naught? Remainder in Q naught is 0. See, this is nothing but the some DFA which accepts set of all strings in which number of A's is divisible by 3 or congruent 1 mod 3 or congruent 2 mod 3. So, and this is the Murray machine which will print out the remainder of number of A's when divided by 3. So let us say this is 1 and this 2. Fine. So this is the Murray machine, some Murray machine. Don't worry about what it is doing. This is some Murray machine. Now I want to convert it to Mealy machine. So what is the main difference between Murray and Mealy? In Mealy machine, the output has to be associated with the transitions rather than the states. In Murray machine, output is associated with states. So I have to move the output onto the transitions. So understand this. I'm going to explain this in two ways. One is by transition diagram, other is by transition table. First, let us try to understand it in terms of transition diagram, state transition diagram. It will be very easy. Just see this. Now, see this transition. This transition is going from 0, Q naught, and is going to Q naught. So wherever it is leading to, just go to that state and see the output associated. Since the output associated is 0, I am going to write it on the transition. Since this edge is going to Q naught, and the transition and the output associated with Q0 is 0, therefore I am going to write it as Q0. Now check this edge. This edge is going to Q1 and the output associated with Q1 is 1, therefore I will write 1. Now see this, edge is going to Q1 and the output associated with Q1 is 1, therefore I am going to write Q1. Now see this, this is going to Q2 and the output associated with Q2 is 2, therefore I am going to write it as 2. And this is going to Q2, output associated with 2. And this is coming to Q0 and output associated is 0. So this is the Mealy machine. So you can simply remove this, and this is the Mealy machine. Now the output is associated with transitions rather than states. So how did I convert it? I have first finished the diagram for Murray machine, and then I have taken each transition, and if a transition is going to some state, I'll take the output associated with that state and I'm associating with the transition. Now let us take the state transition table for the same Murray machine. Now Murray machine state transition table is like this. Q0 is the start state, Q1 and Q2, and inputs are A and B. So Q0 on A is going to Q1 and Q0 on B is going to Q0 itself, and Q1 on B A is going to Q2 and B is going to Q1 itself, and it is going to Q0 and it is going to Q2 itself. So this is the state transition diagram for state transition table for Murray machine. Now what is the output? Output associated with Q0 is 0, output associated with Q1 is 1, output associated with Q2 is 2. So in order to convert this table into Mealy table, first construct the table and then see this. What is the state it is going to? It is going to the state Q1. Now go to Q1 and see what is the output associated. Therefore we get 1, which means Q0 on small a will go to Q1 and output as 1. Okay. Now again see this. This is going to Q0. What is the output associated with Q0? It is nothing but 0. Therefore you write 0, which means Q0 on B will go to Q0 and output 0. Q0 on B will go to Q0 and output 0. Now look at this. It is going to Q2. Therefore go to state Q2 and whatever is the output associated with Q2, write it there. Which means Q1 on A is going to Q2 and outputting 2. Q1 on A is going to Q2 and outputting 2. Now check this one. Q1. So go to state Q1 and what is the input? Output associated 1. Therefore write it as 1. Which means Q1 on B is going to Q1 and output 1. Which means Q1 on B is going to Q1 and output is 1. Next one. Check this. What about Q0? Q0 output associated with Q0 is 0. Therefore Q2 on A is going to Q0 and output is 0. Q2 on A is going to Q0 and output is 0. Now see this, Q2. Fine. So Q2, what is the output associated with Q2? It is 2. Therefore I am writing it as 2. Which means Q2 on B is going to Q2 and the output is 0. Output is 2. Q2 on B is going to Q2 and the output is 2. So how did I construct this? Initially I have constructed the state transition table for Murray machine, given Murray machine, and then in the transitions, in the delta function, this is obviously delta function, right? In the delta function, I am associating the output, whatever is associated with this state. If Q1 is associated with Q1, Q1 is associated with 1, therefore I am going to take 1 and I am going to write it here. You can remove this. So this is the final Mealy machine. Mealy machine. So we shall even see more examples. Fine. Now let's consider this problem where this is the Mealy machine given, and now I have to convert it to the Murray machine. So if this is the Mealy machine given, always start with the initial state capital A. And interestingly, in this we have an incoming edge on which we have an output, right? So what does capital A do on 0? Capital A on 0 is going to capital A and it is going to output 0. Therefore, I am going to associate 0 with A and capital A on 0 is going to capital A and is going to output 0. So it is okay. See, you can even write this as capital A comma 1, and you can create one more state as capital A comma 0, and on 0 you can give a transition. That is not a problem at all, right? But then this is simple, we can go with it. Fine. Next thing is capital A on 1 is going to capital B and the output is 1. Therefore, I am moving the output here. So I created a new state capital B comma 1. So capital B is the state and output associated is 1. Fine. So this one is complete. Capital A comma 0 state is complete because I have shown what happens on 0 and 1. Now on capital B, we have to show what happens on 0 and 1. See this, capital B on 0, capital B on 0 is going to capital B itself and the output is 1. Therefore, capital B on 0 is going to capital B itself and the output is 1. Now, capital B on 1, capital B on 1 is going to capital B itself, but the output is 0. Therefore, capital B on 1 is going to capital B itself. Capital B on 1 is going to capital B itself, but the output has to be 0. Therefore, one more new state is formed. This state is complete because we have shown what happens on 0 and what happens on 1. But this state is not complete because we didn't show the transition set. What happens for capital B on 0? Capital B on 0 is going to capital B and the output has to be 1. Which means capital B on 0 is going to capital B and the output is going to be 1. So that is how we got it as 1 here. Okay. And what about 0? What about 1? Capital B on 1 is going to capital B itself and the output has to be 0. Capital B on 1 is going to capital B itself and the output is 0. And this one is also complete. Right. So what is this problem? This problem is nothing but we are going to read a string from the RHS and we are going to print the 2's complement as output. We are going to start from the RHS or least significant bit and we are going to print 2's complement. The main difference between Mealy machine and Muri machine is in Mealy machine, if I have n inputs, which means if I give 0, 0, 1, 1, then I'll get n outputs, each one for each. Let us say, the answer could be 1, 1, 1, 1, 1, 0. Let us say 1. This could be the answer. If there are 4 bits, I get 4 bits as output in case of Mealy machine. But the problem with Muri machine is, if there are 4 bits, if I give 0, 0, 1, 1, I might get 5 outputs. That is the problem. Therefore, we cannot exactly say that this is exactly equivalent, but then it can be mimicked. What my intention is, it can give us some part of answer. Therefore, both are equivalent, but only problem is Muri machine is going to generate one more input compared to the one more output compared to the Mealy machine. One point worth noting is when we are constructing or converting Muri machine to Mealy machine, number of states doesn't change. Number of states didn't change when we are converting Muri machine to Mealy machine. But when I am converting Mealy machine to Muri machine, number of states increased. Number of states increased. Okay, and how much it increased? If initial Mealy machine contains capital N number of states and if the Mealy machine is outputting capital M number of outputs, then the final Muri machine may contain capital N into M number of states. So in the worst case, I might go up to capital N into M. In the worst case, I might go up to 4 states here because 2 states are there. In the Mealy machine, there are 2 states and the outputs are 2. Therefore, I might go up to 4. But in this case, luckily we got only. Till now we have seen DFA, NFA and finite automata with output, which are Muri machine and Mealy machines. And now let us see a special kind of finite automata, in fact is NFA. We are going to see special kind of NFA called Epsilon NFA. Okay, so the word is epsilon. Epsilon means empty string. So epsilon NFA is different from ordinary NFA in the sense that if you look at any transition, that may even contain epsilon. So this is an example of epsilon NFA. So this is actually looking like a DFA or NFA. Our only difference is in DFA or NFA we don't have epsilon moves, right? So in order to define this epsilon NFA, we can directly define it this way. Let us say Q, sigma, delta, Q naught, and capital F. Q is set of states which we already know, and sigma is input which we already know, and delta is bit different here. Q naught is initial state and capital F is set of final states. So delta, if you remember in NFA, delta is nothing but Q cross sigma, which means if I am in some state, if I see some input, then I was going to 2 power Q, power set of Q, which means if I am in some state and if I see some input, I'll go to a power set of, I'll go to a subset of all states. Only difference between epsilon NFA and NFA is here I even have epsilon, which means on a particular state, on seeing some symbol, I can go to some state, or on a particular state, without seeing anything, a transition is possible. See this? On A, without seeing anything, even we are going to transit some state, right? So it is also called as epsilon closure. So I'll talk about a property called epsilon closure. Now let us say epsilon closure of capital A. So epsilon closure of any state is nothing but what are all the states which you can reach only on seeing epsilon from A. Epsilon closure of A is nothing but what are all the states which you can reach from capital A only on seeing epsilon. In order to find it out, see this, always I can reach A on seeing epsilon. A can reach A on seeing epsilon. It is always there. So whatever is there in the epsilon closure, we are going to get that as the output. Therefore, A can be reached, okay, and A can reach B on seeing an epsilon. Therefore, B is reachable only on epsilon from A. Therefore, epsilon closure of A is going to contain B, as well as B can reach D on seeing epsilon. Therefore, epsilon closure of A is even going to contain ABD. This is epsilon closure. Fine. So now the question is, how can I convert epsilon NFA to NFA? Or you can even ask me a more natural question. We have seen one is DFA, other is NFA, and now we are seeing epsilon NFA. Now your question is, which one is powerful? We have already seen that DFA and NFA are equivalent in power. Why? Every DFA is nothing but NFA, therefore I can convert every DFA to NFA, and then I have even shown you a method using which NFA can be converted to DFA, right? Now in order to show that this one NFA and epsilon NFA are equivalent, see, by this definition, if you remove epsilon, it is nothing but NFA, right? Therefore, you can say every epsilon NFA is NFA. So conversion from NFA to epsilon NFA is trivial. Why? Every NFA is epsilon NFA. Now, if you can convert epsilon NFA to NFA, then we can say that these two are equivalent, and by extension, all of them are equivalent. So now I want to take epsilon NFA and convert it to NFA. Let's see the method. Now I want to take epsilon NFA and convert it to NFA. Fine. So I'll go with the state transition table. State transition table is going to start with A. Now I'm not having epsilon moves, so I'll be writing only about 0 and 1. So first of all, in order to fill this particular entry, it is nothing but what does A, capital A on 0, where does it go? So you have to decide about capital A on 0 in the NFA. So in order to convert this DFA to NFA, I'll use this method. See this? Now I'll take state A. From state A, I have to see what happens on 0. So instead of seeing what happens on 0 directly, I'll see what is the epsilon closure of A, which means what are all the states that are reachable from A only on seeing epsilon, and then 0 and then epsilon. I'll write like this. It is nothing but, in order to find out this entry capital A on 0 in NFA, I have to find out capital A on epsilon closure, again apply 0 and again apply epsilon closure. Even you can think of it this way. So what has exactly happened is, I'm going to find out epsilon closure of A, and then whatever I get in epsilon closure of A, I'm going to find out what are their transitions on 0, and whatever is the result, I'm going to again find out epsilon closure. This is the procedure. You have to apply epsilon closure on A, and then you have to apply on 0, and then again you have to apply epsilon closure on the final result. Instead of writing like this and then expanding, I'll just use this shortcut. So what is that I'm going to do is, capital A epsilon closure. What are all the states that are possible for A on epsilon? Only epsilons. One is A, other is B, and other is D. These are all the states where A can reach only seeing epsilons. On seeing one epsilon A, on seeing one epsilon B, on seeing two epsilons D. I should not even count them as 0 epsilons or 1 epsilon or 2 epsilon, because how many ever epsilons are there? 2 or 3, it is simply 1 epsilon, right? Now, capital A on 0, where is it going? Capital A itself. Check this. Capital A on 0 is going to capital A itself, and now capital B on 0 is going to capital C. Check this. Capital B on 0 is going to capital C, and capital D on 0 is going to capital D itself. And again you have to find out epsilon closure. What is epsilon closure of A? Same. It can reach A, it can reach B, as well as it can reach D. What is epsilon closure of C? C will reach only C and not anything else. What is epsilon closure of D? D will reach only D. Therefore, these are the states that should be present in this particular entry in the final NFA, right? What are the states? A, B, C, D. Therefore, I am going to write it as A, B, C, D. Can I write these many states? Yes, obviously I could write, because it is NFA. Therefore, any transition can be, contain any number of states, or it can even contain 5. Okay. Next I want to fill this row. What is this row? Capital A on 1. So again we are going to write the same way. Capital A if I have to find out on 1, I am going to write it as epsilon star 1 epsilon star. What is capital A on epsilon star? Capital A on epsilon star is, I can go to A, B as well as D. Only I am looking at epsilon. A, B and D. What is capital A on 1? Capital A on 1 is, it doesn't have any move, therefore it is 5. What is capital B on 1? Capital B on 1, it doesn't have any move, therefore it is 5. What is capital D on 1? Capital D on 1 is capital D itself. And what is epsilon star of D? D. So D is not going anywhere on epsilon except D. Therefore, here I have to write D. Singleton set. Now, what about B? Instead B, I have to discuss about B on 0. Now I am in capital B and I have to discuss about 0. So I have to write epsilon star 0 epsilon star. Where does B go? Only on epsilons. It will either go to B directly or it will go to D. So it is going to B and D. Fine. And what about on 0? B on 0 is going to C. D on 0 is going to D itself. What is epsilon closure of C? Where is C going on epsilons? Only to C. What is epsilon closure of D? Where is D going on epsilons? Only D. Therefore, I have to write CD here. What about B on 1? B on 1. This part is going to be same. Fine. Now what about capital B on 1? Capital B on 1, it doesn't have any move. What about capital D on 1? Capital D on 1 is going to have one move, which is capital D. What is epsilon closure of D? Simply D. Therefore, write it as D. What happens to 5? phi is nothing but it is not contain anything. So how can you say that it can go somewhere on nothing, from nothing, nowhere? So we are not going to write anything for that. Okay. Next one, C. C on 0. I'll be here, epsilon star 0, epsilon. C on 0 is nothing but, C on epsilon star is nothing but C, and C on 0 is, it doesn't have any move on 0. Check it. C doesn't have any move on 0, therefore it is 5, and therefore the outcome is 5. So what should I write here? C on 0 is 5. What about C on 1? C on 1. Find out C on epsilon star or epsilon closure of C. So C, epsilon closure is C itself. And what about C on 1? C on 1 is going to be, C on 1 is going to be. And what about epsilon closure of B? So it can even go to B as well as D. Therefore, I have to write it as B, D. What about D? Again, here discuss the same things. D, epsilon closure, find the epsilon closure of D and then find out the transition on 0 and again find the epsilon closure on D. Fine. So what is epsilon closure of D? From D I can reach only D on seeing epsilons. I cannot reach anyone of any state other than that. And what about D on D? It is simply D. And what about epsilon closure of D? It is simply D. Therefore, it is going to be D. Fine. And what about D on 1? So again find the epsilon closure of D and then find the transition on 1. So what is epsilon closure of D? Epsilon closure of D is simply D. And what is D on 1? D on 1 is simply D itself. And what about epsilon closure of D? Simply D. Therefore, this is again D. So this is the NFA for the given epsilon NFA. Now let's draw the transition diagram for the same thing. So how many states are there? We have only 4 states. So the main difference between conversion of NFA to DFA is, when I was converting NFA to DFA, the number of states, they have increased, right? And here when converting epsilon NFA to NFA, the number of states are not going to increase, number of states are going to be same. Fine. So let's start with this, capital A, capital B, capital C, capital D. So initial state is definitely A, that you know. Now the question is, what is the final state? So when we are converting epsilon NFA to NFA, the final states are going to increase. So whatever state that can reach the final state only on epsilon is going to be final state. Again, if I can reach the final state from some state by seeing only epsilons, these states are also going to be final states. So in this given example, in this given question, let me draw the NFA same like epsilon NFA. A, let me draw B here, and let me put C here, and let me put D here. Okay. So if some state can reach the final state only on seeing epsilon, then that state is going to be final state. So in this case, B can reach D only on seeing epsilon, therefore B is going to be a final state also. D is already a final state, now B is a final state. Now see this, capital A can reach capital D only on seeing epsilons, therefore capital A is also going to be final state. So remember this, number of states are same, that is the first one, number of states are same, and second point is initial state is same, true, and the third point is the number of final states may increase depending on if a state is going to reach the final state only upon seeing epsilon, then even that state is considered as final state. Since B can reach D only upon seeing epsilon, you can even say B is the final state, and A can reach D only upon seeing epsilon, so you can say that A is also a final state. Therefore A and B are also final states, and all the remaining transitions you can take from this table. So see this, capital A on 0, what is it doing? On 0, it is going to be in capital A, as well as it is going to B, as well as it is going to C, as well as it is going to D. NFA, right? Next, A on 1, where is it going? A on 1 is going to D. Fine. Next, beyond 0, where is it going? Beyond 0 is going to C as well as D. Beyond 1, where is it going? It is going to 1, D. Next, C on 0, it has no move, and then C on 1. C on 1 is going to BD. C on 1 is going to, 1 is B, other is D. D on 0 is going to D, 1 is going to D itself, which means D is going to be 0, 1. So this is the NFA for the given epsilon NFA, right? So we shall revise what we have seen now. First of all, we are given a epsilon NFA. What is the main difference between NFA and epsilon NFA? Only difference is we have epsilon modes. If you look at the transition table, NFA is going to contain a Q cross sigma, which means from a state on seeing an input, I may go to many number of states or no state or one state. That is true. But then if you look at epsilon NFA, I can even be from some state and then looking at nothing, which means epsilon, I can go to any number of states. So only difference is epsilon is added. So once you have found out this, now we have to construct the state transition table. So in order to construct the state transition table, we need a property called epsilon closure. What is epsilon closure? Epsilon closure is nothing but set of all states which can be reached from some state is going to be epsilon closure of that state. If I say epsilon closure of A, it is nothing but set of all states reachable from A. Then if I have to fill some row, fill some entry, then you have to write like this. If I have to fill capital A on 0, I have to write epsilon closure, which is nothing but I have to find epsilon closure of A first, and then whatever I get, I have to find transition on 0, and then whatever I get, I have to find epsilon closure again. So this is the final. So whatever I get here, I am going to write here. Now let's talk about regular languages in depth. We have a class of families which we have seen till now, set of all strings of length 2, set of all strings of length less than or equal to 2, greater than or equal to 2, and then we have seen many other problems starting with A, ending with B, starting with A, B, and then we have seen binary numbers which are divisible by 2, 3 and all. All these are nothing but regular languages. And for a class of language, there will be something called acceptor. Acceptors are nothing but some mathematical representation to which if you give a string, it will say either yes or no. Yes, the string is in the language or the string is not in the language. That is also called as acceptor. So for regular languages, the acceptors are nothing but finite automatas. And we have seen two types of finite automatas, right? So with output and without output. Right, and with output we have seen Mealy machines and Murray machines, and without output we have seen DFA, NFA and Epsilon NFA. That is all done, okay, and all these we have proved that everything is equal and same. Now there is something called generator. So generator means given a language, it will generate all the strings in the language. Acceptor means given a string, it will say yes, the string is there in the language or not. Let us say if the language L1 is set of all strings starting with A, AB, so on, right? Then given a string A, B, if I ask whether this is in this language or not, then I can use acceptors which will say yes or no. But if I want to generate the entire language, which means if I want to enumerate all the strings, I'll just give I'll not ask about one particular string. I want about all the strings present in the language. Then I can use generators. Generators are nothing but grammars. So in case of regular languages, the grammars which accept regular or which generate regular languages are called regular grammars. Regular grammars. And regular grammars are of two types. One is right linear grammar and other is left linear grammar. So remember this, regular grammars generate all the regular languages. One is right linear grammar and left linear grammar. What is a linear grammar and all, we shall see later. And Other class and other thing which can be associated with a regular languages is something called as representator. So regular languages can be mathematically represented by some expressions called regular expressions. These are the mathematical expressions using which we can represent a regular language. So we have already seen what is a acceptor, which means finite automata, and now we'll see what is a representer and how we are going to represent a regular language using these representers. Okay. Let's talk about regular expressions. So, regular expressions are the representations of the languages which are exactly accepted by finite automatas, or if you can take any language which is accepted by a finite automata, we can represent it using a regular expression. So, we shall discuss what is regular expression. Regular expression contains three operators. Okay. So, one is union, which is also called as union operator, and other is concatenation. So it is called concatenation operation, and the third one is star, which is called as clean closure operation. So we have three operations in regular expressions. What is a regular expression is, point number A is, if phi is the empty set, this is a regular expression, phi is the empty set and epsilon is the empty string. These are both regular expressions representing, phi represents empty set like this and epsilon represents the language like this. If this is the language, this is the representation. If this is the language, this is the representation. Phi and epsilon and sigma. Sigma, A belongs to sigma, is also a regular expression. So understand this. One is, I can write phi as the regular expression, it represents the language empty set. I can write epsilon as the regular expression, it represents the language which is containing only epsilon, and any input symbol A which belongs to sigma is also a regular expression. If I write small a, it represents the language like this, A. If I write small b, it means that the language is B. Okay, so these are also called as primitive regular expressions. Fine. And second point is, if I take any primitive regular expression, let us say R1, and if I take any other primitive expression R2, and if I apply any of this or any number of times, R plus R is a regular expression, R1 dot R2 is a regular expression, and R1 star is a regular expression. See this? Primitive regular expressions are phi, empty set, epsilon, which contains only null string, and then any symbol of the input is nothing but primitive regular expressions, and then any regular expression which is union of two regular expressions is a regular expression, concatenation of two regular expressions is again, and this one. And you use these two, A and B, any number of times. You can use both the rules A and B any number of times, and whatever you get is also a regular expression. So understand this: phi, sigma, phi, epsilon, and any symbol which belongs to sigma is primitive regular expression, and then any operator applied to these primitive regular expressions are again regular expressions, and you can take A and B and apply them as many times as possible. Whatever you get is a regular expression. So I'll tell you some basic languages which can be formed using regular expressions. First one is phi. If this is the regular expression, then the language is empty set. If, let me say, epsilon, if this is the regular expression, then the language is containing epsilon. If A is the regular expression, then the language is this. If I write A star as the regular expression, then the language is, see, whenever I write star, it means that in place of star you can put any number including 0. In place of star you can put any number including 0. So if I put 0 here, I get epsilon. A power 0 is, which means no string of length 0, which is epsilon. If I put 1 here, I get A. If I put 2 here, I get AA, so on. And A plus. A plus is a special operator which is nothing but A concatenated with A star or A star concatenated with A. It is nothing but in place of plus you can put any number except 0. So starting number is A, 1. So it is AA. If I put 2, it is AA, so on. That is the main difference between these two. If I write A plus B star, it is nothing but set of all strings possible over A comma B. How I can get it is, you put 0 here in place of star, I get epsilon. If I put 1 here, I get A comma B. If I put 2 here, I get set of all strings of length 2, which is AA, AB, BA, BB. If I put 3 here, I get set of all strings of length 3. If I put 4, set of all strings of length 4. If I put n, set of all strings of length n, so on. Therefore, this represents the set of all strings possible over A comma B. So this is what is the basics of regular expressions. Now we shall solve some problems and then you can understand it better. Let's now convert this regular expression to finite automata. So I want to convert regular expressions to finite automata. So you could follow some few rules and you could do this. I'll just write down the rules like how to construct a basic regular expression to finite automata, and then you could extend this method to any regular expression. Okay, so I'll just tell you some rules here, and then I'll show you even a general method. So if I have 5 means we should not accept anything, right? So simply leave it. Any finite automata which doesn't have any final state doesn't accept anything. So this is a finite automata which doesn't have any final state. Therefore, the language accepted by this is simply 5. So if I have A as a regular expression, then simply the finite automata has to accept only A. Accepted, right? Let us say I have the regular expression R1, or let us say A plus B. Then I have to accept, this is nothing but union of A or B, right? Either A or B, I have to accept it. A regular expression A dot B. Then I have to accept A and then B. Okay. Let us say I have A star, which means I have to have a and it can repeat any number of times. Therefore, after seeing A, I can go back, or if you want to accept it, you can accept it, right? And you can enter here, or you can directly accept only epsilon, right? So only epsilon is accepted and 1A is accepted and 2A's are accepted, 3A's are accepted, everything is accepted, right? So this is one way of doing this, which means epsilon, you directly go here, A, right? So using these building blocks, I have shown you how to accept all the primitive regular expressions. Now only A plus B, A dot B or A star, they're all primitive regular expressions. Now once you understand how to do this with primitive regular expressions, you can extend this method and you can even accept any complex regular expressions. But then strictly speaking, you need not follow these rules always to accept a string. For example, if I have something like this, A B star, just use your intuition and you can do it. So it is A followed by any number of B star, that's it. Let us say I have AB star like this. Then I have to accept AB, isn't it? Any number of ABs. But then this AB is not a input symbol. Always transitions of a finite automata should contain only input symbol. Since this is not an input symbol, so you could even convert it like this. Instead of writing AB directly, A and come back on B. You could write like this, right? Let us say AC star. Okay, that is done, right? Let us say AB plus BA star. How could you do this? So you can directly put, you have to accept AB comma BA, which is nothing but AB and BA. And since this is not a symbol, input symbol, that is a string, you convert it to input symbols by adding one more state. Whatever I am doing is also called as state creation method. A, B. B, A. Okay. So whatever we did now here, it is also called as state creation method. So you can take any regular expression and you can convert it to finite automata, right? So which one is powerful, regular expression or finite automata? Since for every regular expression there is a finite automata, you might feel that finite automata is more powerful. But the next method is, I'll show you how to convert every finite automata to regular expression. After seeing this, you'll understand that both are equivalent in power. Actually, both are equivalent in power. Either it is regular expression or finite automata, both are equivalent in power. I'll show you that. Okay. Let's now see how to convert a finite automata to regular expression. So there are various methods. One popular method is Arden's lemma is there. So Arden's lemma is writing about the equations and then substituting them and then solving it. But that is going to take a lot of time. And if you are interested in writing competitive exams like GATE, and if you want to do it fast, so the other method available is state elimination method. So I'm going to use this method, which is called state elimination method. So state elimination method. So in this method, I could eliminate the states. I'll tell you the algorithm. So first of all, there are three rules. First rule is incoming state should not have the initial state should not have any incoming edge, which means if I have anything like this, this is initial state. Initial state is not supposed to have any incoming edges. If you see any incoming edge to the initial state, then you are supposed to create new initial state. Since there is incoming edge to the initial state, I am going to create new initial state, or I'll do it in the same diagram. So now since there is incoming edge for the initial state, I am going to create new initial state. Okay. So that is what I mean to say. So there should be no incoming edges to the initial state. And second rule is, coming to the final state, there should not be any outgoing edges. So if I have a final state like this, let us say take the same diagram. Let's say there is a final state and then something is like this. Okay. Then the final state should not have any outgoing edges. So initial state should not have any incoming edges and final state should not have any outgoing edges. So whenever you get, before applying this algorithm, whenever you see the final state is having outgoing edge, then you create a new final state with an epsilon move on this, and you make it non-final. That is second rule. So what is it? First rule is initial state should not have any incoming edges and final state should not have any outgoing edges. In case if they have, I'm going to create a new final state. I've created a new initial state with epsilon transition to the initial, with epsilon transition to the final. Okay. And then third rule is, okay, here in the second rule, we have one more rule. There should be only one final state. If you have more than one final state, you might have to consider converting it into one final state, which means if I have, let us say, this is a final state, this is a final state, and this is a final state. If I have more than one final state, you construct a new final state with epsilon moves to that new final state, and you make all the previous final states as non-final. That is what I mean to say. Okay. So remember these rules. First rule is incoming edge, initial state should not have any incoming edge and final state should not have any outgoing edge, or there should be only one final state. If there is more than one final state, we are going to create a new final state. If anything is violating, we are going to construct new final states, right? Then other than the initial state and final state, eliminate the states one by one. Other than the initial state and final state, eliminate the remaining states one by one. If this is the case, eliminate the states one by one. Then you are going to get the answer. That is called state elimination method, right? So what is it? Step 1 is initial state. Step 2 is final state. Step 3 is eliminate all the remaining states other than the initial and final state in any order you would like to do, right? So let me take some examples and I'll explain you how to do this. Okay, let's see them now. So let me take few small examples and I'll explain you the concept. Let us say you have something like this. Okay, now initial state is not having any incoming edges. Let's say this is C. Initial state is not having incoming edge and final state is not having any outgoing edges, right? So the diagram is perfect. So how to transform it is, now from this state to final state, I'm going to have A comma B comma C. A comma B comma C, right? Now what is A comma B comma C? It is nothing but A plus B plus C. Therefore A plus B plus C is the regular expression for this diagram. Okay. Now let's say this is A, B. See the initial state. Initial state is not having any incoming edge and final state is not having any outgoing edge. So leave initial state and final state. Then what is remaining? In the remaining state, you can eliminate all these states in any order. If I eliminate this, then what do I get? A. So whenever you eliminate this state, remember that all the paths which were there previously, they should still be intact, which means if I remove this, there is a chance that I might miss out this path. What is the path? The path will come from this state and go here, isn't it? And on what label will it go? On AB, right? Therefore, after eliminating this state, you should have this path which should give the same effect, isn't it? Therefore, this is the regular expression. AB is the regular expression for the previous diagram. Okay, let me take one more diagram and I'll explain you. So using this method, see, Arden's lemma was having this limitation that it cannot be applied to Epsilon NFA, right? But using this method, it can be applied to anything, any finite automata, Epsilon NFA, DFA, or anything. Okay. Now see this. Say let's say this is state A, state B, state C. Okay. Now, initial state is not having any incoming edges, fine. And final state is not having any outgoing edges, fine. Now, you have to leave the initial state and you have to leave the final state, and in the remaining states, you have to eliminate them in any order. Let us say I want to eliminate B. If I want to eliminate B, how should I do it? So, one thing you should remember is, even after I delete B, okay, then even after doing that, I should have the same effect, which means whatever effect was there before, which means the paths which were there before, those paths should be still there. See this, there is an incoming edge to B, then what is B doing? B could take any number of B's and it is going to C on C, isn't it? Therefore, if I delete that, there should be a path which should take A first, and then any number of B's, B star, and then C. This should be there. So even after you remove it, make sure that A, B star, C is still there with the path. Got it? So this is how we eliminate it. Let me take one more example. Let us say state A on 0, state B, and state B is the final state on 1. Okay. Now observe this. So initial state is having a incoming edge. So what should we do? We should create a new initial state. Let us say I created new initial state QS with epsilon transition to the old initial state. Okay. And final state is having an outgoing edge. Therefore, you should create a new final state with epsilon state to the new one. And you make the final state non-final. Okay. Then you have got a initial state and a final state. Then you can eliminate each state one by one in any order. Let us say I want to eliminate A, and let me see what happens if I eliminate A. If I eliminate A, what will remain? Start state QS will remain, and capital B will remain, and let us say this is QF, final state QF. QF will remain. And let's talk about this. So this one will not change. Now let's see what are the things that we should keep there. See, if A would have been there, then there is a path which starts from QS, comes like this, and it goes like this, isn't it? So for every incoming edge, for every outgoing edge, you should write a path. For every incoming edge, there is this outgoing edge, right? Which means there is a path from QS which starts like this and goes to B. Therefore, there has to be a path from QS to B, and what should be transition? Epsilon followed by 0, which means 0. Okay. And now there is a path starting from B going to A and again coming to B. Therefore, there has to be a path from B to B, starting from B going to A and again coming back to B. What should be label on that? Label on that should be 1 followed by 0. Okay, fine. Now, if I eliminate this, if I eliminate B, then what happens is there is a path which starts from QS and which takes any number of 1 zeros and then which go to QF, which means there has to be a path like this. If I eliminate B, the path should start with 0, okay, and then it should take any number of 1 zeros, which means 1 0 star followed by epsilon, right? Therefore, this is the final regular expression, 0 followed by 1 0 star. Okay, let's see one more example. Let's say initial state small a, these are all final states. So first rule is initial state should not have any incoming edges. Yes, initial state doesn't have any incoming edge. Second state is final state. Second rule is final state should not have any outgoing edges. Yes, final state doesn't have any outgoing edge, but then there should be only one final state. But if you see this diagram, there are 3 final states. Therefore, make one final state and you make all of them non-final and you give the epsilon transition to all of them. Okay. Now, you can eliminate all these states one by one in any order. If I eliminate this state, what do I get? I get a path which contains B from here to here. If I eliminate this state, what do I get? I get a path with C. If I eliminate this state, I get a path with D, right? Which means I get 3 paths starting from this state to this state with B, C, D labeled on them. Therefore, I'll get A and then I'll get 3 paths. Let us say this is 1, this is 2, 3, 4, 5, 6 states. Okay. From state number 2 to state number 6, I have 3 paths, and on 3 paths, one is B, other is C, other is D. Therefore, I can write B comma C comma D. So, how to write this in regular expression? It is also B plus C plus D, which is nothing but comma is nothing but union, right? B plus C plus D. Now, if I eliminate this, what do I get? A followed by B plus C plus D. This is the regular expression for that. So I have always told you this. If there is a language, there will be something called acceptor like finite automata, and there will be something called generator. Generator means grammars. So the grammars will not say whether a particular string is there in the language or not, but the main intention of grammar is to generate the entire language. Okay, so let's talk about grammars. I'll first define grammars and then give you examples, and let's get used to the terminology. After that, we shall solve more questions on grammars. First, let's see the definition of grammar. A grammar is generally represented by V, T, P, S, where V is set of all vertices, T is set of all terminals, P is set of all productions, and S is the start symbol. Okay, V is vertices, T is terminals, P is productions, and S is start symbol. I'll give you an example and we shall see it. Let us say S derives A, S, B, and S derives A, capital B, and capital B derives small b. So this is the grammar. Now, what is V is set of all vertices. Vertices means left hand side. So what are left hand side here? S comma B. And what is T is set of all terminals. So what are all terminals here? Small a comma small b. And P is set of all productions. P is nothing but set of all productions. Therefore, P is going to be this entire thing. And S is start symbol, S itself. So S is the start symbol. Okay. So understand this. V is set of all vertices, T is set of all terminals, and P is productions, and S is the start symbol, which is nothing but S. So why we need all this is, using this we could generate all these strings. So if this is the grammar, let us see what is the language generated by this grammar. So how to find out the language generated by this grammar is, let's try what it is deriving. So getting a string from this grammar is called derivation. So let me show you derivation. Derivation is taking deriving a string from the grammar starting from the start symbol. So let me say I am using the start symbol. So with practice I know that this is the grammar which generates a power n, b power n such that n is greater than or equal to 1. So let me generate AABB. So derivation of the string AABB. I am showing you how to generate AABB. S derives small a, capital S, capital B. Now at every step, every variable, only one variable will be replaced with its right hand side, which means either you could replace S with the right hand side or you could replace B with the right hand side. Right hand side means small b. So if you start replacing the leftmost symbol first, then that is called leftmost derivation. If you start replacing the rightmost symbol first, that is called rightmost derivation. So I'll show you the leftmost derivation first. Leftmost derivation means take the leftmost variable and derive it. So let me substitute this one. A, S, B, B, which means in place of S, I substituted ASB. Okay. In place of S, I will not substitute ASB. I'll substitute A capital B, which means in place of S, I am substituting AB. Therefore, I got this. Then, in place of first B, I am going to substitute the right hand side, which is small b. And in place of the remaining b, I am going to substitute small b. A, B, B. Right? Therefore, from S, I got this string. This entire procedure is called derivation, and whatever intermediate strings I got on the way, these are called sentential forms or sequential forms. Sentential forms or sequential forms. Okay, so these are the sentential forms, and this is the string, and this entire process is called derivation. And at every step of derivation, I am going to replace one variable with a terminal, one variable with the right hand side. At every step, I am going to replace one variable with the right hand side. Okay, this is called derivation. Now let me show you the one other representation of getting the derivation, that is called derivation tree. So if I start with S, then I can go with A, S, B, and S can go with A, B, and this one with small b, and this one with small b. This is called the derivation tree for the same derivation. Okay. Now, if you traverse the parse tree and see what it is, what is the yield of the tree. Yield of the tree is nothing but what is the string that is there, derived from this tree. So if I start the derivation, I got a first, and then a, and then b, and then b, a, b, b. So this is called yield of the parse tree or yield of the derivation tree. Okay, this is called the parse tree, and this is called the derivation. Either you could use the derivation or you could use the parse tree to get a string, and both of them doesn't make a lot of difference. You could use any one of them. So let's see more examples about how to construct the grammars, and let's see given a grammar, how to identify what that grammar is representing. Okay, let us say a language is set of all strings of length 2, which means AA, AB, BA, BB. Now I want to construct a grammar which accepts set of all strings of length 2. So grammar is simple. I'll start, and my start symbol could generate AA or AB or BA or BB. Done, over, right? So if the language is finite, then giving the grammar is very simple. But then instead of writing like this, we could even do somewhat better. So we know that the AA, BB, all of them can be written like this. Now we have seen that the building block for this language is a plus b and a plus b. So let me build a plus b first. What is a plus b? A plus b is nothing but a or b. So let us say capital A derives small a or small b. Okay, and then capital S derives AA. So I'm building this one first, and then I'm building AA. Got it? So this is nothing but set of all strings of length 2. So let us say I want to generate a power n such that n is greater than or equal to 1. Then what are all the strings? A or AA or AAA, AAA, so on, right? Now what is the building block? Building block is nothing but only A. So I could build the block A derives small a, and then I can repeat this any number of times. In order to repeat this any number of times, let us say it is greater than or equal to 0, what I could do is I can write it as, see this, A derives small a, capital A or epsilon. So A, if it wants 0, it can go directly to epsilon, and A, if it wants 1a, it can go and use this, which means AA, and then this one can generate epsilon. If you want 2 A's, it can use AA, and this one can use epsilon. Therefore, writing any production like this is nothing but A star, right? For example, whatever you put in this place, that is nothing but the star of it. For example, if you want to generate any number of some capital S, then what you could do is A derives SA or epsilon, then it is nothing but S star. Whatever you put in this place, it is nothing but simply generating any number of those many, right? So if you want, whenever you want a star, you put it there. It is not just, you could even write it other way. This is one way, and the other way is A derives capital AA or epsilon, or even you could use one more production and you can do it, not an issue. So for a given language, there will be many representations. It is not just, it is not a compulsory thing that you should always use the only one representation. For a given language, there could be many representations, right? And I have shown you some of them. Let us say I want to generate A plus B star, which means set of all strings containing all the strings. Set of all strings over A comma B. Then S derives AS, BS or epsilon, which means if you want A, you can go with this and you can substitute in place of S epsilon. If you want B, you can go with this and you can substitute in place of S epsilon. or if you want only epsilon, you can go with this, right? So using this, you can generate any string. So give me some string, let us say AB, let's see it is generated or not. Sderives, first one is you wanted A, therefore I am going with AS. Okay, second thing is you want B, therefore I am going with BS. Okay, and next thing is you want A, I am going with AS. And next thing is you want B, therefore I am going with BS. And finally S is replaced with epsilon, therefore the yield of the tree is A, B, A, B. That's it. A, B, A, B. So any string can be generated from this. So remember this. This is how I generate star, and this is how I generate A plus B star. Okay. So what we could do is, using these building blocks, we can construct for all the questions we have seen, prior. We could construct grammars for them. Okay. Let us see. Set of all strings of length at least 2. At least 2 means 2, 3, 4, so on. So this is nothing but set of all strings of length 2, and this is 2 or more, right? So how can I construct set of all strings of length at least 2 is, see the building blocks. First one is you need A plus B star, and second thing is you need A plus B. Then you can put all of them together. So what is A plus B? And one more thing, it is not always possible to give a regular expression for every language. Since the language is regular, how do you know? With practice. Since the language is regular, I am writing the regular expression, and then I am seeing the building blocks, and then I am constructing them and putting them together. But it is not possible to give regular expression for every language, because there are some languages like A power n, B power n, right? For which we may not be able to give regular expression, but for this language I will be able to give a context-free grammar. So types of grammars we shall see later. After seeing some examples about grammars, we shall see types of grammars later. Okay. So first of all, what is the building block for A plus B star? The building block for A plus B star is S derives, let me say B. B derives AB, BB, or epsilon. How do I know this? I have already shown you. So in place of, if you want to do A plus B star, it is nothing but S derives AS, BS, or epsilon. I have already shown you. So this is nothing but A plus B star. Then I have to do A plus B, which means A derives A or B, right? And then S derives this one, and this one put together. So what is this A plus B? A plus B is nothing but A, and A plus B is nothing but A, and B is this AAB. So S derives AAB, and A derives this, and B derives this. So this is the language containing at least 2A, at least strings of length 2. What about set of all strings containing strings of length at most 2? At most 2. So for that, since that language is already regular, you know how to use the regular expression. So regular expression can be given as A plus B plus epsilon and A plus B plus epsilon, right? Now these are the building blocks. So first you build this, and then you can put concatenation, right? So A derives A or B or epsilon. This is over. Now S derives A, isn't it? A. This is how you build it. Now you get all the strings of length at most 2. Let us say set of all strings starting with A and ending with B, which means like this. So I want to give the grammar for this. See the building block. So you have to construct A plus B star first, and then you can put A before and B after that. So what is A plus B star? A derives AA or BA or epsilon, right? And then S derives small a, capital A, small b. So this is nothing but generating A plus B star, and if you put a small a and small a before it and small b after it, it is nothing but we'll get whatever it is, the language is, right? And next one is, let us say set of all strings starting and ending with different symbols. So different symbols means if it starts with A, it should end with B. If it ends with B, it should start with A. Which means if it should start with A, if it starts with A plus B star, it should end with B. Or if it starts with B, a plus b star, it should end with a. So this is nothing but starting and ending with different symbols, right? So generate this a plus b star first. So how can I generate it? A derives same thing, a, ba, or epsilon. And now what should s derive? Small a, capital A, small b, or small b, capital A, small a, right? What about starting and ending with same symbol? So starting and ending with same symbol is again same. So s derives, if it either it starts with a, then it should end with a. If it starts with b, then it should end with b, or it can be simply a because a starts and ends with same symbol, or simply b starts and ending with same symbol, or simply epsilon. Then what about a? A can be small a, capital A, or small b, capital A, or epsilon, right? So this is nothing but starting and ending with same symbol. So there are some other examples. So let us say I want to construct the grammar for a power n, b power n such that n is greater than or equal to 1. So this language is not regular, therefore you cannot give a regular expression and then convert it to grammar. So let's see some other approach. S derives a, s, b, which means whenever you generate a in the beginning, you generate corresponding b at the ending. Therefore a's and b's will always be leveled, or ab. So why this ab is just to stop this. So see how it works. S derives, if you want only one a, one b, then it is directly s derives ab. If you want more than one ab, then you can take this production, which means a, s, b, and this s can be a or b, then it is a, b, b, right? If you want a power 3, b power 3, then also you could do the same thing. S derives a, s, b, a, s, b, and then ab. So which means it is 3 a's and again 3 b's, right? So that is how it could be done. Let us say I want to generate set of all palindromes. W power r, it is a palindrome which is even length palindrome, or union W A W R union W B W R, which means where W belongs to A comma B star, which means I want to generate all even length palindromes as well as all odd length palindromes. These two are set of all odd length palindromes, right? So I want to generate even length palindromes as well as all odd length palindromes. How could I generate it? Is whenever you generate a, you generate corresponding a at the end. Why? Because either I read it from this side or from that side, it has to be same. Whenever you generate b, you generate a corresponding b at the end, which means even if I read from this side or that side, it will be same. Or simply small a, or simply small b. These are also palindromes, odd length palindromes, or epsilon. Now check this. So if I generate a, I am going to generate a at the ending. Therefore from both these sides it will be synchronized. If I generate b, b at the ending, both these sides synchronized. It is odd length, and it is zero length, right? So just see, in case if you don't have epsilon in this, then it is set of all odd length palindromes. In case if you don't have this a and b in this, it is set of all even length palindromes. If you have a, b and epsilon, it is nothing but set of all palindromes. See, if you don't have these two, which means it can only end with, s can only end with epsilon, then s is going to generate only even length strings. If I don't have epsilon and if I have a or b, then s is going to end with either a or b. Already there are even length strings to which one symbol is added, therefore that will be odd length, right? So let's see this one example. S derives a, and if it is epsilon, then it is simply a, which is nothing but even length string. S derives b, s, b. If I put small a, then it is nothing but bab, odd length string, odd length palindrome. Even if you could even extend it, s derives a, s, a, which means first symbol is a, then the last symbol is a, right? Then b, SB, which means if the second symbol is B, then the second last symbol is B. Then you can stop it with A. Then if you see this, A, B, A, B, A, A, B, A, B, A, which is a palindrome. Read it from this side or read it from this side. Both are going to be same and it is going to be of odd length, right? So maybe see one more example of that. S derives ASA, which means if first symbol is A, then the last symbol is A. Or BSB, if the second symbol is B, second last symbol is B. ASA, if the third symbol is A, third last symbol is A. You could either stop with A, B or epsilon. If you stop with epsilon, then what happens is A, B, A, followed by epsilon, followed by A, followed by B, followed by A. See, just see how am I tracing it out. I'm just traversing top to down, left to right, and whenever I'm coming across any terminal, I'm just printing it. So that is how you see what a parse tree is going to generate. It is also called as yield of parse tree. Yield of parse tree is nothing but ABA, ABA. In this case, this is also a palindrome. So that is the grammar which will generate set of all palindromes. Let's look at this GNF, Grebac normal form. So there are various ways we represent the context-free grammar. This is one of the way if you represent the context-free grammar. There are some advantages. Like in CNF, the advantage is that the grammar is restricted, which means the size is not going to be too much, and there are various advantages we have seen. Similarly, we have some advantages coming to GNF also. So first of all, what is GNF is? It is named after a scientist, Grebac normal form. If all the productions are of form A derives, capital A derives small a alpha, where alpha belongs to V star, that is important. V star is nothing but set of variables, and it can even be 0. V star means 0 or more, isn't it? So they are saying that if all the productions are of form A derives small a alpha, where alpha belongs to V star, which means alpha can be 0 or more variables, then it is called GNF. Okay. And for example, if you see this, look at this. Now here there are 4 variables. So it can be 4 variables or 1 variable or 2 variable, or it can even be 0, which means like this. In this one it is 0 variables, right? What are the advantages of this? Advantages of this method is the number of steps required to generate a string of length W is only W. The reason is in every step we are going to add one terminal. If we have W terminals in a string, then how many steps does it need is W steps, isn't it? See, if whenever you use a production like this in the process of derivation, in every step the number of terminals are going to be increased by 1, which means either you are going to increase this by this A or this A. So anyway, every step one terminal is going to be added. For example, if you want to see an example like this, A derives AB, B derives B. This is in GNF, isn't it? The reason is it is going to start with terminal followed by any number of variables. If you want to generate AB, then how many steps does it take? Capital A in first step is going to derive AB, which means in one step we are deriving one terminal, and in the next step we are going to derive one more terminal. Therefore, in every step the number of terminals are going to be increased. So we start from 0 and we go till W. So how many steps are required? W. That is the advantage of it. So in every step we are going to derive a terminal. So compared to that CNF, deriving a string using GNF is faster, isn't it? The number of steps taken is less. And then GNF is useful in order to convert a context-free grammar to push-down automata. If you want to take a context-free grammar and directly convert it to push-down automata, GNF is very useful. See this? Conversion of context-free grammar to push-down automata. These are the steps. If you follow these 3 steps, we can convert a context-free grammar to push-down automata. First step is push the start symbol A onto the stack. So we are going to push the start symbol A, assuming that A is the start symbol. If S is the start symbol, we are going to push S. Whatever it is, we are going to push the start symbol onto the stack. So initial state, it does nothing. It will just push the start symbol onto the stack, and then it will go to state Q1. And in Q1, we are going to take every production, each and every production. If push RHS of capital A as follows. Delta of, if you are in Q1, if we have such a production in grammar, and this production is definitely in, first of all, before applying this procedure, we should make sure that the grammar is in GNF. In case if it is in GNF, then this is a terminal and these are all variables, isn't it? If you have such a production, then what is this rule saying is, if you are in state Q1 and if you look at a input terminal small a and capital A is on the stack, then you be in the same state but you replace that small a with this. Okay, instead of I'm trying to explain this in words, don't worry, I don't think that you'll understand it, but I'll take more examples and I'll do it, so don't worry as of now. So what I'm trying to do is, whenever you have such a production, then you are going to add such a rule. What is the rule? If small a is in the input and capital A is on top of the stack, just replace that capital A with right hand side, which is after small a, which means this alpha. And similarly, same thing, if you have such a production, this production, now if small b is in the input and capital A is on top of the stack, then replace capital A with beta. Beta is nothing but the symbols after small b, right? And one more thing is, this alpha and beta can even be epsilon. In place of alpha, you could go for epsilon, or it could be one or more variables also. Finally, add final state. So finally, what we are going to do is, from Q1, we are going to add final. We know whenever the input is over and when we reach the bottom of the stack, epsilon comma z0, we are going to add, we are going to go to the final state. It is nothing but acceptance by empty stack, isn't it? The reason is, once the input is over and once we hit the bottom of the stack, we are simply emptying the state. So we have both the final state as well as empty stack. You need not have the empty stack, since you are already using final state QF. You can just have Z0 there, right? It works. What I'll do is, I'll take some few examples and explain you how this method is working. I don't think that you understood anything by reading out this method, but anyway, write it down. After seeing examples, you'll understand it. That is why I don't actually teach a lot of theory in theory initially in TOC. I'll teach theory later. First, I'll take examples. Okay, that way you'll understand it. Let's see this example of how to convert to PDA, push-down automata, from GNF. So first of all, in order to convert into push-down automata, we need the grammar in the form of GNF. So they're asking, if this is the grammar given, only two productions, they wanted to convert it to PDA. But then if you observe this grammar is clearly not in GNF. The reason is, it is small a followed by, there should be only variables, but there is a combination of variables and terminals, so not possible, right? So convert this to GNF. In order to convert this to GNF, what I am trying to do is, I am introducing one more variable capital B, and that capital B is deriving small b. I introduce one more variable. Okay. Now by using this one more variable capital B, I could write it like this: S derives A as B, A B, and B, by just using one more variable, right? And after using this, after writing like this, now the entire grammar is in form of GNF, right? So now I have to convert this GNF into PDA. So see this, first step is, we have to push the start symbol onto the stack without doing anything. That is why I am introducing this first move in Q0, in the initial state. Epsilon means without using any input symbol. So input symbol might be there, but then without using any input symbol, then just push S onto the top of the stack. If Z0 is on top of the stack, on top of it you push the start symbol S. That is what is done. And next is, when you are in Q1, we are going to take every production in GNF and we are going to convert it. So when I am in Q1, I am going to take every production here and I am going to convert it to some move here. So see this, first this one, this production S small a SB. So how can I convert is, if I am in Q1, if the input symbol is small a, and top of the stack is S, then you push SB, which means in place of capital S, you replace with SB. That is how I converted it. It's simple. See this. Now look at this second one. For this one, if input symbol is small a, and top of this stack is yes, which means left hand side has to be on top of this stack. And now you push push B, right? And look at the next production. If input symbol is small b, and if top of the stack is capital B, then there is nothing here, therefore you push epsilon, which means you don't push anything. Got it? So that is how we converted. And finally the last move is added here. See this? Last move is nothing but adding the final state. So last move is, if input is over, which means epsilon, and z0 is on top of the stack, leave z0 as it is and you can go to QF, or you can even empty the z0 and you can go to QF. Both are right. Either, since there is already final state, you need not empty the stack, or if you wish to empty the stack, you can write epsilon. So finally what it means is, after the entire input is over, it has been passed. If input top of the stack is z0, then leave it as it is and go to F. Let's consider the next language. A power n, B power m, C power n, such that n comma m greater than or equal to 1. So here the logic is, A's have to be matched against C's, and then B's could be left alone. So you need not do anything with B's. Match A's and C's and leave B's like that. So how I could do it is, so in the initial state, initially I put C A and Z0 will be on top of this stack, you push A, and then A and A, you push A. Okay. Then whenever you see a B, so by this time all the A's will be pushed because of these two moves. Next one is, you are going to see a B. So whenever you see a B, if A is on top of this stack, leave it as it is, because we don't want to do anything for B's. We don't want to push or pop B's. We don't want to count B's. Therefore, leave A as it is and go to the next state. And in this state, you remember that I have seen a B and I could see any number of B's. So there will be any number of B's and A will be on top of this stack. Leave the A as it is and go to the next state. In this next state, we are supposed to compare, we are supposed to match C's against A's, which means if I see a C and if top of the stack is A, then I am going to replace it with epsilon, right? So in this state, I have to keep on matching all the C's. If I see a C and if A is on top of this stack, I'll keep on popping it. Finally, if the entire input is over and if the top of the stack is Z0, which means all the C's are over and all the A's are over on the top of the stack, then leave it as Z0 and you accept it. Okay. So this is how you could accept that language. And one thing you should observe is, we need this state and we need this, these three states are compulsory. So why are these three states compulsory and why can't we do it in less number of states here is, after seeing a B, you should go to the next state and remember that I have seen a B and no A's should be allowed after that. And after seeing a C, I should go to the next state and remember that I have seen a C and no B is allowed. That is why I cannot do popping in the same state. If I do popping in the same state, after a C, a B can come and there will be a confusion there. That is why, have these three states. Okay, let's see one more example. Now let's see this. A power m plus n, B power m, C power n, such that m comma n is greater than or equal to 1. So I have to, the basic thing is, you have to save all A's, count all of them and then match them against B's and C's, right? So initial state, I'm going to save all A's. A will be on top of this stack, Z0 will be on top of this stack and initial input will be A, and you are going to push A, right? And you will see A in the input and A will be on top of this stack, you are going to push A, right? And then whenever you see a B and A is on top of this stack, you have to pop off the A, which means you are matching B's against A's, right? So in this state, you will see any number of B's and A's will be on top of this stack and you are going to pop off A for every B. Now, if I get a C here, can I be in the same state and pop off A? The reason is, if you be in the same state and if you pop off A, then after a B, a C will come and after a C again a B will come and you will accept it. So you have to remember that after a C, B's should not be allowed. Therefore, you go to the next state, and in this state, if you see a, you pop it off, right? So in this state, if you see a C and A is on top of the stack, you keep on popping it, matching it, right? So finally, what happens is all the A's, B's, and C's will be over, which means you will get epsilon, and Z0 will be on top of the stack. Leave it as Z0 and you accept it. Okay, so this is very straightforward. So whenever you have A, these three, it is very easy to construct this. So for A's, I am going to push A's, and for B's, I am going to pop A's, and for C's, I am going to pop A's, right? So A's and then B's and then C's, right? We shall see one more example. Let's see this language. A power n, B power m plus n, and then C power m, such that n comma m is greater than or equal to 1, right? Which means A's, you push them, and whenever you see B's, you have to match them against A's, and the remaining B's, you push them onto the stack and then match them against the C's. So if you are not understanding how to do this, I'll just show you how to split the language. It is better you split it like this. A power n, I can write it as B power n, and then B power m, and then C power m, such that n comma m is greater than or equal to 1. So for all A's, you push A's, for all B's, you pop A's, and then remaining B's, you keep on pushing them and then match them against C's, right? So how to do this is, for all A's, A, you push them. You push them, okay? And then for all B's, you are going to match them against A's, right? So whenever you see a B, and if A is on top of the stack, you keep on popping it. As long as you get a B and A is on top of the stack, you keep on popping it. Finally, what happens is, suddenly you'll see that B's or A's are over, and suddenly you'll see Z0, which means in this state, whenever you see a B in the input and Z0 on top of the stack, you can understand that this part is over. Now this part is beginning, which means these two are matched up, and all the A's have been matched up with B's. Now the extra B's, they have to be pushed onto the top of the stack, right? So I'm going to see for every B, and when Z0 is on top of the stack, I'm going to push Z0, and then for every B will be on top of the stack, I'm going to push B, right? So now by doing these two moves in the same state, you need not go to the next state. The reason is, after a B, even if A comes, then I'm not defining any move, right? I'm not defining any transition for A, therefore I can do it in the same state, right? So by this part, all the B's have been matched against A's, and the extra B's have been pushed onto the stack, okay? Then I'm going to get C's. So what should I do with C? For every C, I have to match it against B's. So if I get a C and B is in the input, then I'm going to, B is on top of the stack, then I'm going to match it, okay? So why can't I do this matching in the same state? The reason is, if I do it in the same state, after a C, B will come and that will be pushed. That is why I need to go to the next state, right? In this state, for every C, for the input C, and if B is on top of the stack, I am going to match it. Finally, what happens is, the entire string will be over epsilon, and then you are going to see Z0 on the top of the stack, which means everything is matched up, and leave it as Z0 and you accept it, okay? This is the language. We shall see one more example. Now let's see, A power n, B power m, C power n plus m, such that n comma m are greater than or equal to 1. So in this language, you have to push A's, and then you have to push B's, and then you have to pop C's for every A and B, right? So now let's see this. First, initially A has to come, because there has to be at least one A, which means if the input is A and top of the stack is Z0, I am going to push A onto the top of the stack, right? And then any number of A's can come. So if the input is A and top of the stack is A, I am going to push all those A's. So this part will be over because of these two transitions, right? Then a B will come. So now we have to decide whether to be in the same state and push, or should we go to the next state and push. See, if I be in the same state and push, is there any harm? So if the top of the stack, if the input is B and if the top of the stack is A, then I can push B onto the top of the stack, and then after that there will be only B's following. If B is in the input and B is on top of the stack, I am going to push B, right? So because of this, this entire part will be pushed. So is there any problem if I do this? That is what you should be thinking about. So if I do this one, it is fine. I am going to push A power n, B power m. Is there any problem with this? Okay. So the problem will be, I'm just guessing, you might think that the problem will be after a B, if a comes, what happens? After a B, if a comes, we are not going to accept it, and this state is not having any transition defined for it. After a B, see, now you are thinking that AA is pushed and then BB is pushed. After that, if a comes, what happens is, now these entire things will be on top of this stack, which means you will be in this state and you will see small a and b, which means a and b, the transition is not defined. Since for small a, we are not defining any transition for small b, it means that we are not going to accept it. That is going to be a dead configuration. So no problem, by writing like this, even if there is any, after a b, a comes, that is going to enter the dead configuration. So we could do this in one state confidently. Next one is, so whenever I get a C, I should keep on popping them. So should I be in the same state and do it, or should I go to the next state and do popping? Definitely we should go to the next state and do popping, because after a C, if a B comes, then the configuration is defined, right? That is why you go to the next state and you keep popping it. So if I get a C, then first of all, what will you see? Definitely B, not A. Then you pop it, and in this state, as long as you get C's and if the top of the stack is B, you keep popping all the B's. Then after all the B's are over, still C's will be remaining and A's will come onto the top of the stack. Therefore, you can be in the same state and you pop them off, which means if I see a C and A is on top of the stack, you can pop off A. You need not go to the next state in order to pop A. The reason is already A's have been kept on the stack and then the B's have been kept. Therefore, we have already guaranteed that the order of A's and B's will be A's will be followed by B's. Therefore, while popping off, you need not do anything about this order. You can swap them you can pop them accordingly in the same state. There will be no mistake in that. Then finally what happens is, entire input will be over epsilon and top of the stack will be z0, leave it as z0, and you enter the final state and you accept it, right? So that is how this language could be accepted. Let's see one more example. Let's see some models here. A power n, B power n, C power m, D power m, such that n comma m greater than or equal to 1. How to solve it? You push A's and then match them against B's, and then you push C's and then match them against D's, right? So that is how you could do it. And we have already seen many such models. You can just take it as a homework and you could do it. And let's see the other one. A power n, B power m, C power m, D power n, such that n comma m greater than or equal to 1. And for these languages, we have already given context-free grammars also, right? So whenever you have given context-free grammar, understand that the language is definitely context-free, and so push-down automata is possible. So if you see this language, how to solve it is, first you push A's, okay, and then you push B's, and whenever you see C, you match them against B's, which means for every C, you keep on popping B's, right? And then for every D, you keep on popping A's. So if you can do that, this language could be solved. So other such models are A power n, B power m, C power n, D power m, such that n comma m greater than or equal to 1. So this is interesting. See this. Now we are going to push A's and then push B's. Then we have to compare C's against A's. But the problem is, by the time we see C, top of the stack will be filled with B's, right? Therefore, we may not be able to do this. The reason is, by the time we see C's, top of the stack will be B's, and in order to compare them against A's, we have to go to the bottom of the stack. But then using a stack, we can only see the top. We cannot go below the top. Therefore, this language is not context free, and moreover, push-down automata, we cannot give any push-down automata for that, right? So let's see some other languages. Think about it. A power n, b power 2n, such that n is greater than or equal to 1. So tell me how to solve it. First thing is, if you observe it, a have to be pushed definitely, and then for every a there have to be 2 b's. So one solution for this is, if you think, for every a we could push 2 b's, right? So if you see the strings which are in the language, the strings will be a, b, b, right? Which means a power 1 b square, or a, b, 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 which means a square b power 4, or a, b, 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 which means a cube b power 6, so on, right? So if you are observing this, for every a you might have to push 2 b's, right? That is the way you should be doing it. So but the problem with it is, for every a there have to be 2 b's, right? So how to solve it is, whenever you see a, instead of pushing 1a onto the stack, you could push 2a's. So one solution is like this. Whenever you see a 1a, instead of pushing 1a, you could push 2a's. And whenever you see a b, you could match it off, right? And other solution is, for every 2 b's, you can pop off 1a, right? So let's see these two solutions. First solution is, for every a, I'm going to push 2a's. So initially I'll be in start state. In this state, I'll get any number of a's, a, and z0 is on top of the stack. For every a, I'll push 2a's and z0, okay? And then if I see a and a is on top of the stack, for every a in the input, I'll push 2a's, and for whatever you have removed from the stack, put it back, right? So this is nothing but pushing 2a's for every a, pushing 2a's for every a. By the time this is over, I'm actually pushing a power 2n onto the stack. Then what I could do is, for every b, you could pop off a, which means if b is in the input and a is on top of the stack, pop it off. And if b is in the input and a is on top of the stack, pop it off, and keep on doing it. Finally, the input will be over and top of the stack will be z0, which means a power n, b power 2n has been reached. All the a's and b's have been matched. Then you leave it as z0 and you accept it, right? So this is how you could do it, okay? So just try to see what we did here. For every a, I'm pushing 2 a's, and for every b, I'm popping 1a. This is one method. And other method is, instead of pushing 2 a's, you just push only 1a only. So see this, I will not push 2 a's. Whenever I see a and z0 is on top of the stack, I'll push only 1a. And whenever there is a and z0 is on top of the stack, a is on top of the stack, I'll push only 1a. Let's see some few examples of the languages and tell me whether it is they are regular or not and context free or not. So coming to this language, a power m and this one, we have already seen it. Definitely finite automata is not possible. Therefore, why? The reason is, you might have to save a and you might have to compare against b's and c's. It is nothing but infinite counting and infinite comparison, right? So this language is definitely not regular language. And is this language context free? Yes, the language is context free, and moreover the language is deterministic context free language. So what is deterministic context free language is, if you can give a deterministic pushdown automata, then the language is deterministic context free language, right? So this language is definitely deterministic context free language. The reason is, we don't have any non-determinism here. On seeing a, we are sure to push. On seeing b and c, we are sure to pop, right? Therefore, the language is deterministic context-free language. And so, if a language is deterministic context-free language, it is context-free language as well. Okay, these two. And just to tell you the classification, we have regular languages and we have deterministic context-free languages and we have context-free languages, set of all context-free languages. Okay, if a language has finite automata, then the language is regular. If the language has push-down automata, which is deterministic, then the language is deterministic context-free language. Deterministic push-down automata, then the language is deterministic context-free language. If the language has a push-down automata, either deterministic or non-deterministic, I don't know. If a language has push-down automata, then it is, if a language has push-down automata, then it is context-free language. So this is what you should understand. So if a language is deterministic context-free language, it is definitely context-free language. And the same is true with this. It is not regular. It is deterministic context-free language and not and also context-free. Same with this. And here also see this. This is not regular. The reason is A's have to be stored and compared against B's, therefore not regular. But then it is deterministic context-free grammar because context-free language because we know what to do with A's, which means we know that A's have to be pushed and B's have to be popped, C's have to be pushed and D's have to be popped. Therefore, this is deterministic context-free language as well as context-free language. And see this is not regular because we have to save infinite string and then count it. Definitely not regular. And if you see this, A's have to be matched against C's and B's have to be matched against D's. And this is infinite language also. Therefore, this is not context-free also. By the time you reach C's, B's will be on top of the stack and you cannot match A's. So this is not context-free language. Okay. Therefore, if a language is not context-free, it is not even deterministic context-free or regular. What about this one? This is not regular because you have to save A's and compare against D's, save B's and compare against C's. But then this is deterministic context-free language. Definitely deterministic context-free language. The reason is on seeing A's you can push A's, on seeing B's you can push B's, and on seeing C's you can pop B's, which means we know whether to push or pop, and exactly we are not having any non-determinism here. Therefore, this language is definitely deterministic context-free language and hence context-free language also. Right? And see this one, A power m, B, C power m, and then B power I, D power k. And the language is infinite. A's have to be compared against C's, therefore not regular, but then it is context-free and moreover deterministic context-free. Why? A's push, B's don't do anything, C's pop, D's don't do anything. We know exactly whether to push or pop. We don't need any non-determinism. Therefore, this one is deterministic context-free language and by extension context-free language. A power m, B power n such that m is greater than n, which means I have more number of A's compared to B's. If I have any such language, definitely it is not regular because comparison is required and that is unbounded comparison, which means I have to save all this and then compare against this, not regular. And it is deterministic. How? You are going to push all A's and then you are going to pop A's for every B. So you can do that. And finally, at the end, how are you going to accept this one is, at the end, if you see epsilon, which means if the entire string is over, and if top of the stack is containing A, which means at least one A is extra. Epsilon means all the B's are over. Small a means top of the stack contains one A, which means at least one A is extra. Then you can go to the final state. Therefore, there is deterministic context-free. It is a deterministic context-free language. The reason is we could construct a deterministic PDA, and so the language is context-free also. And A power n, B power 2n, we have already seen it, right? So we have already constructed a deterministic context-free push-down automata. How? Push for every A you push 2 B's and for every B you pop a, right? Therefore, the language is deterministic context-free language and by extension context-free language. Okay, so we shall see more examples. a power n, b power n square. This is definitely not regular because if you observe this, a power n has to be stored and then it has to be, this saving has to be unbounded, right? And then we might have to compare against base. So there is a comparison involved which is unbounded. Therefore, the language is not regular. Okay. And let's see whether we could do it with push-down automata. So a power n we can push onto the stack, but then there is no way for every n square I have to pop off 1a. So if b would have been in a AP, if length of b would have been in AP, then I could put a loop in the finite automata, and for this one loop I could pop off 1a. That is how we did a power n, b power 2n, isn't it? See, if you remember this language a power n, b power 2n, how we did it is, we are putting these b's in a loop, and in this loop for one time we take the loop, we are popping off 1a, isn't it? For one time we are popping off 1a. That is what we are doing using a power n, b power 2n. But I cannot put b power n square in a loop and I cannot compare or pop off for one loop 1a. Therefore, it is not possible to give any push-down automata, either deterministic or non-deterministic. Therefore, the language is not context-free language. Then a power n, b power 2n, the same thing, right? So it is definitely not regular because unbounded comparison is required, and then we cannot put b power 2 power n in the loop. The reason is, inside a loop we cannot put 2 power n, right? So if you have a loop, I cannot put any loop with 2 power n as the count of it, right? So since 2 power n is not in AP, this one is not possible with context-free languages, and definitely it is not regular language also, right? And then w power r, such that w belongs to a comma b star. It is nothing but set of all even length palindromes. So we have to save w and then compare it against w power r. This example we have seen it. This is an example of non-deterministic context-free language, which means the language is not regular because I cannot save infinite w and compare it against infinite w power r. And this language is not deterministic context-free language because I don't know where this center is. Therefore, I cannot know till what part to push and from what part to pop. But then this grammar is context-free language, which is non-deterministic context-free language, and so context-free, right? Next one is WW, right? If you see this language WW, definitely we have to save unbounded W onto the stack. So finite automata, it is not possible, so it is not regular. And then if you are looking at this language WW, we have to save W first of all and then compare it with W. For example, if I have string AB, this has to be accepted. I have to save W, which means I have to save W, AB. Now how do you identify that this is W and this is W? You can use non-determinism to guess that one thing is, at every point you could guess whether the center has come or center has not come. That is fine. But then even if you have guessed out the center, how can you compare the first symbol, which means the input symbol, with the bottom of the stack? You can only compare the input with the top of the stack, right? But the problem requires that you have to compare the input symbol with bottom of the stack. But then we cannot see the bottom of the stack, we can only see the top of the stack. Therefore, this language is not context-free language because push-down automata or stack cannot examine the bottom of the stack. Next one is a power n, b power n, c power m, but then there is a comparison between n and m. It is not that a power n, b power n you compare and for c you don't do anything. It is not that language. So first of all, a power n, b power n is there, therefore it is not regular. That is fine. And now let's see whether it is context-free or not. So for every a you push a and for every b you pop a, therefore you can accept a power n, b power n. By the time you reach here, there will be nothing remaining in this stack. All the a's will be emptied and all the b's have already been seen. Now you cannot compare the remaining c's whether they are greater than b's and a's or not. By the time you finish comparing a's and b's, you will not have anything on the stack, or you cannot go back to read the input. So there will be nothing to compare against c's. So for such a language, push-down automata is not possible. Maybe you might argue that for every A's, I'll push 2 A's, and then for every B, I'll pop one A. But using that, you cannot, compare how many A's are remaining, isn't it? Then you might compare A's and B's, but then you cannot compare how many B's are remaining, right? So nothing works for this. See, your logic is for every A, if you push 2 A's, and for every B, if you pop it, there can be only one B, and there can be 4 A's, isn't it? And then this one will be accepted, right? So definitely that logic does not apply here. So remember that this language is not context free language. It is very simple. If you want an example, I'll show you. See this, if I have A, B, C, this has to be accepted, right? So if your logic is for every A you push 2 A's, and for every B you pop 1 A, and then you compare if C's are greater than A's or not. How does that logic work is, for every A you are pushing 2 A's, which means I'll get 4 A's, and for every B you are popping A's, and then you can compare this one. Fine, this one is accepted, but again a string like this, A, B, C will also be accepted. The reason is, for every A you are going to push 2 A's, which means 4 A's will be pushed on the stack, and for every B you are going to push 1, and for C you are going to compare A's. This one will be accepted. Therefore, that logic doesn't work. So, this language is not context free language. See this, A power n, B power n, C power n, D power n. N is less than 10 power 10. So, obviously the language is finite, and every finite is regular, and every regular is deterministic context free language, and every deterministic context free language is context free language, right? And now A power n, B power 2n, you can compare this. By the time you are done, there will be nothing to compare against C's. See this, A power n, B power 2n, and then C power 3n. So your logic is, you can compare A's against B's by pushing 2 A's for every B, fine. And and then by the time this comparison is over, nothing will remain on the top of the stack. Therefore, you cannot compare C with A's. So this is not context free. You might try to argue that for every A, instead of pushing 2 B's, I would like to push 5 A's. Sorry, for every A, instead of pushing 2 A's, not to match this, I can match these two by pushing 5 A's. How does that logic work is, if I push 5 A's, which means this string has to be accepted, B, C. So your logic is, for every A, I'll push 5 A's, and for B and C, I'll keep on popping 1 A. If that is your logic, then the flaw in that logic is this. Understand this? For every A, you will push 5 A's. Fine. Then that is going to accept A, B, 1, 2, 3, 4. This will also be accepted, isn't it? If you do that, this will also be accepted, right? So it is nothing but, if you push 5 A's, it is as good as A power I, B power j, C power k, in such a way that 5i equal to j plus k. That will become the language. So we cannot apply the logic that for every A I'll push 5 A's, and for every B and C I'll keep on popping A's. That doesn't work here. So definitely it is not possible, and it is not context free language. So this language is not context free. If it is not context free, it is not regular, or it is not deterministic. Now this one is, x can be anything, y can be anything, x, c, y, such that x comma y belongs to 0 comma 1 star. X can be any regular, any regular expression, y can be any regular expression, and only thing is c should be there. It is nothing but set of all strings containing c as a substring. Okay, this is nothing but set of all strings containing c as a substring, which is definitely regular. Since it is regular, it is deterministic context free language, and since it is deterministic, it is context free language as well. Okay, we shall see more examples. See this, x power r, such that x belongs to a comma b star, which means x can be anything, but there is a restriction that length of x is exactly L. So how many strings will be possible? If you count the number of strings, there will be 2 power L strings. So this language is clearly finite, and therefore it is regular, and therefore it is context free language, both deterministic and non-deterministic, right? And what about W, W and W power R such that W belongs to A comma B star is, we have seen that this only this part W, W is not context free. Therefore, adding one more part is not going to make it context free. So definitely, since W, W cannot be recognized by push down automata, W, W, W R will never be recognized by push down automata. So this one is not context free language, and so not deterministic context free as well as not regular. Now A power n, B power 3 power n. Okay, so for A's you can push all A's, but for B's you have to put them in a loop, and that loop should contain 3 power n B's, right? And if you see 3 power n is not in AP, right? So since this is not in AP, for the same reason why 2 power n and n square are not context free, this is also not context free. If it is not context free, then definitely it is not regular, and as well as it is not deterministic context free. Now A power n and B power n such that m is not equal to n. So number of A's and number of B's should not be equal. So what you could do is construct the ordinary push down automata where A power m and B power n both are equal, and then what you do is either A's have to be greater or B's have to be greater, which means at the end, if you have reached epsilon, then if A is there in this stack, then you accept it. That is one way. Or if B's are remaining and if you reach Z0, which means B's are more. This indicates that B's are more, and this indicates that A's are more. You can think of it, okay? You could easily do that. So definitely this is context free language, and moreover it is deterministic context free language. Why? Because we know that A's have to be pushed, and for B's, A's have to be popped. We know when to push and when to pop. And this one we have already seen it. A power n, m and B power n such that m equal to 2n plus 1. I mean, what you could do is, so for every 2 A's, you can push 1 A and then leave 1 A, and then for every B you can pop 1 A. I mean, in the reverse order, what you could do is you can put a loop for A's, and for every 2 A's you can push 1 A, and then for B, simply for every B you can pop 1 A. This is same, but then for first A you need not push anything, leave it, and for second A you can push, right? And for second A you can push. Now let's look at Turing machines. So before talking about the theory about Turing machines, my concept is always straightforward. I'll take examples, lot of them, and I'll explain all the examples first, and then let's get into the theory. So even if I talk about Turing machines in theory, you will not be able to understand anything. So I'll just take an example and I'll explain you few examples, then we shall move on to the theory. So Turing machine. So what is the main difference between Turing machine and other machines like push-down automata and finite automata is, till now we have seen that either push-down automata or finite automata, it moves in only one direction, from left to right. But then Turing machine can move in both the directions. That is one difference. And second thing is, Turing machine can even read a symbol from the tape as well as write on it. So a Turing machine will have something called as a tape, and on the tape input will be present and there will be a read-write head. So Turing machine will have finite control, and using this read-write head it will read the symbol on this and it can even write on it. For example, I'll just design a small Turing machine which will be able to accept A power n, B power n such that n is greater than or equal to 1. And remember that Turing machine is not capable of accepting epsilon. The reason is Turing machine, okay, I'll tell you that later, but for now understand that Turing machine cannot accept epsilon. Therefore, I'm taking A power n, B power n is greater than or equal to 1. It rarely, it doesn't make any difference whether you include epsilon or not. It doesn't really make any difference. So let's keep it simple. A power n, B power n is greater than 1. This is the language given. Now we have to design a Turing machine which is going to accept this language, A power n, B power n. First of all, is this language regular? It is not regular. Is it context free? It is context free. We have even seen a grammar which context free grammar which is used for this, and we have even seen push down automata how to design it. Now let's see how the this Turing machine work on it. So I'll take an example. Let us say a power n, b power n is greater than or equal to n. One of this string is a, b, b. If this is present in the tape, what happens is on the tape you will be given the input, and to the left of it there will be blanks, all blanks, and to the right of it there will be all blanks, and your Turing machine will be pointing to a symbol in the input like a, right? So how Turing machine works is, just to take an analogy and explain you could think of Turing machine as a man who doesn't know how to count. So let us assume that a man doesn't know how to count and he is supposed to count now. So just assume like this: there are two rooms. Okay, there are two rooms. And in one room there are bags of cement, and in other room there are bags of sand. And now you are given, there is a man here and he doesn't know how to count, and he is given the responsibility to cross check whether the number of bags of cement are equal to the number of bags of sand, and he doesn't know how to count. Then how is he going to do that? One possible answer you might come up with is, pull out one bag of sand outside and one bag of cement, and one bag of sand, one bag of cement, one bag of sand, one bag of cement. Pull them out and pair them up, it is done, isn't it? Yes, we can do that. If he doesn't know counting, obviously he has to do all that labor, right? He has to pull out every bag and then match them. But then can he do something better? Which means without pulling or moving these bags, can he do something better? Yes, one thing is simple. He can take a stone, a brick, a small, or a chalk, and he can go to one room and mark on this, and then he can go to other room and mark on this. Again he can come back, mark on this, come back, mark on this. So he can keep on marking one here, one here, one here, one here. If we do that, then it is nothing but comparing, isn't it? So the same way our Turing machine will also act the same way. So it has the capability to read a symbol and then change that symbol, move left as well as move right. These are all the functions which a Turing machine can do. So Turing machine is capable of reading and then changing. Changing means writing on it, and then moving left and moving right. Okay. So what it will do is, it will see A and mark it as seen, which means it will make it X, and then it will keep on moving right, and whenever it sees a B, it will make it Y, and then keep on moving left, and again the next A it will make it X, and again keep on moving right, and next B it will make it Y and keep on moving left, like this. So every A will be marked as X and every B will be marked as Y. So if you didn't understand it, I'll take one more example. See this. Let us say A, B, B, B is given to the Turing machine, and on either side there are simply blanks. There is nothing but blank. Okay. Now how our Turing machine works is, if you look at first A, make it X, and then go right. Look at first B, make it Y, and then go left. Go left until it reaches the first X. It ensures that we are standing just behind the unmarked A, first unmarked A. So you go left until you reach X. After you reach X, you turn right and make it X, and again go right and cross all the A's, cross all the Y's, and then reach B and make it Y, and again go left, crossing all the Y's and crossing all the A's until you hit the first X. After you hit the first X, move right and make it X, and again you keep moving right until you hit the first Y. On the way you might get any number of A's and any number of Y's. Leave them and then make it Y, and again keep moving left until you reach the first X. And after first X, if there is no A, if there is simply Y, what does that mean? It means that all A's are over. Now make sure that all B's are over or not, which means go to the right and see if all B's are over. If all B's are over, you can say that yes, it is accepted. All A's are followed by all B's, right? Now let's write the Turing machine. I'll just write the transition diagram for Turing machine and explain you this in a easy way. So in order to construct this, Taking an example and doing it will be very easy. I found out that it is very easy to explain you by taking an example. So let me say I have A, 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 B, 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 and to the left there are blanks, and to the right there are blanks, and there are lots of blanks. Okay, and now I'll start in, assume that in state Q0. In state Q0, what happens is I'll see a. If I see a, I'll replace it with x, which means I'll replace it with x and I'll move right. Right means I'll go to the next symbol like this. Okay. And after moving right, what my purpose is, I have to search for 1b and make it as y. So in Q1, the purpose of this state Q1 is to find the next b or the first b. So it will keep on moving. While moving, what it could see is any number of a's, leave them all as a's, and you keep moving right. So it helps if I extend this, if I trace this example 2 more steps and then show you, because it will help you. Let us say the b is found and it is made y, and again we are here and now it is made x. Okay, now we are here, so again we'll be in state Q1. Now it will help you see this. Now after making a as x, and when you are searching for y, on the way what you could get, when you are searching for b, on the way what you could get is any number of a's. Therefore any number of a's you can get, leave them as a and keep moving right, and then you can get any number of y's. So before you get a y, second b, you might get any number of y's. Therefore as long as you see y's, leave them as y's and you keep moving right. Understand this? Whenever you have made a as x, and when you are searching for a b, on the way you might get any number of a's or any number of y's. So you leave all the a's as it is and you leave all the y's as it is, and you keep moving right until you hit the first b. So whenever you hit the first b, that is where you make that b as y and you start moving left, which means you make this b as y and again you start moving left in search of first a. So in order to search the first a, you should search the first x. Therefore when you are moving left, you are actually searching for x. So once you search x, when you are here and when you are moving left like this, once you hit x, then the symbol next to it is a. That is what you wanted. Okay, so now you will be in Q2, state Q2. When you are moving left from here, you may get any number of y's and any number of a's. So you might get any number of y's, leave them as y and keep moving left, and you might get any number of a's, leave them as a's and you keep moving left, and finally you might hit the first x. So whenever you hit the first x, the history repeats, which means whenever you hit the first x, if it is x, leave it as x and you move right, which means you will be standing at this point. And again entire thing will repeat. What is it? Make a as x, and you move right, and as long as you see y's, leave them as y and keep moving right. And whenever you see a b, you make it as y, and you keep moving left, and when you're moving left, you may get any number of y's, and finally you will see a x. Therefore whenever you see a x, you are here. Now after x, you are supposed to see a if there is a present, but then if all a's are already marked as x, all a's will be over. If all a's are over, how do you know that all a's are over? After ax, you will immediately see a y. Therefore there should be one more path. So what does it indicate? After ax, you are seeing y. So what does this mean? All a's are over. So should I stop here and accept it? No. I should even check whether all b's are over or not. The reason is 3 a's will be there, but 4 b's might be there. So you should even check whether all b's are over or not. If all b's are over and all a's are over, then only you can accept it. Therefore I just want to make sure that all b's have been marked. So if there is a y, I'll leave it as y and I keep on moving right. So when I'm moving right, what am I supposed to see is only y's. So as long as I see y's, I keep on moving right. Any y I see, I leave it as y and I keep on moving right. And finally, all the y's will be over. In case if all the y's will be over, and if I see a blank, then you can leave it as blank. You can move left or right, no problem. And finally, you can accept. it. What does this mean? It means that Q0, okay, let's number them, Q3, Q4. Just see what has happened. Initially, you started with A and you marked it as X and you kept on moving right. When you are moving right, on the way there can be any number of A's or any number of B's, and finally you might see a B. And when you see a B, mark it as Y and you keep on moving left. When you are moving left, there can be any number of Y's or any number of A's, but keep on moving left. And then what happens is, finally, when after seeing this first X, if you see a, it means that there is one extra A, then you go in the search of one extra B. Or in case after seeing the X, if there is no A, if there is directly a Y, what does this mean? That all the A's are over. If all the A's are over, then what should you do? You should even check whether all B's are over or not. So I'm going like this and I'm checking all the Y's. If all the Y's are, if there are only Y's, then I'll keep on moving right. And finally, if I see a B, blank. So when I see a blank, it means that there are no B's. Therefore, I'm going to accept it. So this is how the Turing machine works. So again, I'll take an example and explain you how this one is working. See, A, B, 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 and then there are blanks, blanks, blanks. So just see if you understood this or not. I made this one as X and then I kept on moving right. When I'm moving right, I can get any number of A's, and finally I see a B. Then I made it Y and I kept on moving left. When I'm moving left, I can get any number of A's, and finally I hit a first X. And then after that, immediately I turn right. See this. After seeing a first X, I immediately turn right. And if I find a, the entire procedure repeats. What is the procedure? Make it X, make it Y. Make it X, make it Y. That is how this one is working. Now, there is something called as dead configuration. Dead configuration means I am expecting that, okay, if everything goes on well, which means if the string is in the format of A power n, B power n, then everything will follow exactly, or everything will fall in place. But if the string is not in the language, then something unexpected might happen. One of the things which is unexpected is A, B, B, B. This string is not in the language, which means we are not expecting one extra B here. We are expecting only 2 A's followed by 2 B's, isn't it? There is one extra B, that is unexpected, right? Then how is our Turing machine going to answer this one is, it will take make it X, keep on moving right, make it Y, keep on moving left, make it X, keep on moving right, make it Y, and when it comes here, X, immediately X will be followed by Y, which means after seeing a X, immediately it will be followed by Y. Therefore, this path will be taken, right? And now in this path, in this one, so when it is taking this particular path, the problem is, check this, we are going to check whether every symbol is Y or not. So here the transition defined in Q3 is, as long as you see Y, you are making it as Y and you are keeping right. And if you see a blank, these two are defined, which means once you reach here, you are going to see only Y's or only blanks, and suddenly you will see a small b. So you will be in state Q3 and you will be seeing a symbol small b, but nothing is defined there. That is called dead configuration. If the string is not in the language, then you are going to hit dead configuration. Therefore, the Turing machine will halt in Q3, which is not a final state. Therefore, you can say that string is not accepted. So, if a string is present inside the language, our Turing machine is going to hit the final state and halt there. Generally, final state will halt. If the Turing machine has seen a string which is not in the language, it is going to halt in a different state because of dead configuration, right? So, because of dead configuration, we are going to stop here. So, we need not define every configuration like in DFA. In DFA, we are going to say for every state what happens on every symbol. But then here we are actually using it as a kind of not non-determinism. Non-determinism means from one state, if you go to two symbols, two states on the same symbol, it is non-determinism. It is incomplete determinism, or it is deterministic only, but then we are not defining every possible configuration. Therefore, if there is any configuration for which we are not defining the transition, it is called dead configuration. And whenever our Turing machine hits such a dead configuration, we are going to halt in that state. So when our Turing machine halts here, we can say that the string is not accepted. And one more input which you could guess, which is not in our this symbol is language is A B B blank 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 blank. So what is the specialty of this input? Number of A's are greater than number of B's. Then what happens is, initially this will be made X, and again you'll keep on moving right. Initially this will be made X and we'll keep on moving right, and then this will be made Y and we'll keep on moving left. This will be made X, this will be made Y, and then this will be made X, and now we'll be in search of B, which means after making A as X, we'll be in this state and we are in search of small b. So we'll be looking at all the A's and we'll be looking at all the Y's. We'll be looking at all the Y's, and now we want to see a small b. Suddenly, instead of seeing small b, we'll hit a capital B, which means in Q1 for capital B it is not defined. Then what can you understand? So since capital B is not defined for Q1, it is a dead configuration. Therefore, if for such an input, the Turing machine is going to halt in Q1. So either if A's are greater or B's are greater, Turing machine is going to halt in a non-final state by hitting something called as dead configuration. Then you can understand that, oh, it is dead configuration and you are not supposed to accept it. In case if the string is in the language, Turing machine is definitely going to go to the final state and halt there, right? So anyway, whenever you give any input which is not in the language, this is an example of a Turing machine which will definitely halt, but some Turing machines may not halt. Okay, but anyway, here in this example, what I mean to say is, if the input is given and if the input is in the language, the Turing machine halts in final state. Otherwise, it halts in some other state. It need not be in Q1 and Q3 only. It can be anywhere. It can be Q2 or anywhere. So if the input is starting with, let us say, small b, let us say input is BA, then what happens? Q0, it is expecting to see small a or capital Y, which means it is expecting to see small a only, but suddenly small b has come, therefore it halts here, right? And let us say here, when you are moving left, something unexpected might happen, and then you might halt there. So there are various conditions in which we are going to halt in a non-final state. So whenever the language string is not in the language, we will halt in a non-final state. Now you might have got one doubt. The Turing thesis says that every Turing machine is as powerful as a computer, isn't it? That is what Turing thesis said. So every Turing machine is actually as powerful as a computer. But then, what is a computer? It has a power to run any program. But then when I was designing these Turing machines, I was designing the Turing machines for a specific problem, which means a Turing machine which is designed to accept a power n, b power n, cannot add two numbers a plus b. But our computer, our digital computer, it will be able to add two numbers, as well as it will be able to do this, isn't it? So there is a basic difference. Our computer acts in a different way and our Turing machine is acting in a different way. You might have got that doubt. When I am saying that Turing machine is as powerful as a digital computer, our digital computer can do many things. So depending on the input program, the program which you give, depending on that, our computer will change its behavior. But then a Turing machine, once it is programmed, which means once I design the Turing machine, it is able to solve only one particular problem and it is not able to solve other problems. A Turing machine which is designed to solve a power n, b power n will not be able to solve a plus b, but our real computer does. Then how can I say that a Turing machine is as powerful as a computer, right? So in order to answer your doubt, in order to clarify why Turing thesis is right, we could do some other thing. So we are going to design a new Turing machine which will act as a computer. In the sense, I am going to design a new Turing machine which will take as input one Turing machine and then run that Turing machine inside this big Turing machine. Okay, it is going to be somewhat confusing. You have to really pay attention here. So what I mean to say is, I'm going to design a new Turing machine which will act as a computer and which will answer your doubt and which will prove that Turing thesis is right. What is Turing thesis? Every Turing machine is as powerful as a computer. Therefore, I am going to really design a Turing machine which is as powerful as a computer. So that Turing machine is called universal Turing machine. Universal Turing machine means it is the biggest Turing machine. Okay. Now let's see how does this universal Turing machine works. A universal Turing machine is going to have a finite control, but then it is a multi-tape Turing machine. It is going to have three tapes. It is going to have three tapes. Let me call one tape as tape 1, tape 1, and other tape as tape 2, and the other tape as tape 3. Tape 3. So it is a multi tape Turing machine, and you already know that multi-tape Turing machine is as good as a standard Turing machine. Then why am I taking multi-tape Turing machine? Is it is, you know, it actually simplifies many things. That is the reason. So in order to implement a multi-tape Turing machine using a single tape Turing machine, it is going to be difficult or complex to explain you how it works. But if I take a multi-tape Turing machine, the explanation will be very straightforward. Now this is entirely a one Turing machine. I want to use this as a computer. Then if it has to be a computer, then it should be able to do any generic work. So what I do is, for example, if I want to add two numbers a plus b, then what I do is I design a Turing machine separately. I'll have a Turing machine separately, and which is written actually to add two numbers. So what will that Turing machine will have? That Turing machine will have a finite control, and along with that it will have a input tape, and on this input tape you are going to put what are the two numbers you are going to add, right? So the two numbers are, let us say, 2 plus 3. Then I am going to represent 2 and I am going to represent 3, and now I want to add it. And now this this Turing machine is going to be designed the way we have already seen it. So this is some other Turing machine, the normal Turing machine, and that is universal Turing machine. Now what will this universal Turing machine do is, it will take this Turing machine and it will store the Turing machine in its one tape. Therefore this tape T1 contains representation of some other Turing machine. Okay. And now what about the input? The numbers, whatever is the input given to the original Turing machine, that input can be saved in the second tape of the universal Turing machine, which means here I am going to put the input, actual input, right? And this tape 3 is used for the rough work. Rough work means, now what we do is, this universal Turing machine will trace out this small Turing machine on this input. While tracing out the Turing machine on some input, what is that we are supposed to remember is, what is the present state we are in. So here it is going to save the internal state, which means initially internal state will be Q0. You know, if you assume that let us say initially the internal state is Q1, if you assume that this Turing machine is going to start with internal, initial state as Q1, then Q1 will be in this tape, then input will be here. Now you will see Q1 and you will see the first symbol of the input. Then you will go to the representation of this Turing machine and you will see for this configuration, which means what is the configuration? Q1, and for the input let us say 1. Then delta of Q1 comma 1. Then it will go and consult this Turing machine representation to see what should be really done here. Now let us say this Turing machine representation is saying that if this is the configuration, then you have to go to the state Q2 and write it as some other symbol, let us say 1 or 0, and then let us say X. something, if you remember that transition, okay, let us say x, and you might have to move right or left. Then what will this one do is, our universal Turing machine will see this configuration from this representation of the Turing machine, and it will change the internal state from Q1 to Q2. It will just write Q2, so that it will remember that now we have entered the new state Q2, and along with that it will do whatever modifications are specified on the input in this input, which means it will make that one as x, and it is asking you to move right. Therefore, you will move right and you will see the next symbol. Then again, what will you do? Again, you will see that the configuration is you are in state Q2, and now you are looking at the symbol 1. Then what should be done? Then again, our universal Turing machine will visit the representation of our Turing machine and see for this configuration what has to be done. Then appropriately it is going to apply the changes. Got it? Therefore, in order to represent in which state we are in at present, we are going to use step 3. And in order to represent what is the input we are looking at and what has been done to the input, we are going to use step 2. And in step 1, the entire mystery lies. The entire Turing machine, some other Turing machine, has to be saved in one tape. How are we going to do that? That is the mystery, isn't it? So to solve that mystery, what we are going to do is, how can we represent this entire some other Turing machine in one tape, right? So what we assume is, without loss of generality, what we assume is that the original Turing machine has set of states Q as Q1, Q2, Q3, Q4, so on. And the tau means the input alphabet as A1, A2, A3, A4, so on. And A1 could be blank, or we could assume any other symbol. So every symbol is represented like this, and every state is represented like this. I'm not talking about a specific Turing machine which is going to add. In general, it can be applied to any Turing machine. So if you have any general Turing machine, you can represent it in number of states and number of this input symbols. I mean the symbols which are allowed on the tape. Then what we do is we encode every symbol. So for Q1, the encoding I use 1, and for Q2, the encoding I use is 1 1. For Q3, the encoding I use is 1 1 1. For Q4, the encoding I use is 1 1 1 1. Similarly, for A1, the encoding I use is 1. For A2, the encoding I use is 1 1. And for A3, the encoding I use is 1 1 1. A4, the encoding is like this. So on, I can continue encoding them, right? Now we know that every symbol which is required in these states to represent a state, or every symbol which is required to represent a input, is going to be encoded. There is no problem in using the same encoding for state and then the input, because in transition function we are going to use it. I'll show you how it is going to be easy. Now all the ones are used for encoding, and now I'm going to use the symbol 0, this particular symbol, as a separator. So whenever I put a 0, it means that to the left of it there is something else, and to the right of it there is something else. Now how to represent a Turing machine is, we have to represent its transition function. Now assume that in the transition function I have something like this: delta of, if you are in state Q1, let me write it here. In this transition function, let us say I have something like this: delta of, if you are in state Q1, and if you are looking at symbol A1, let us say you want to go to, the transition is defined as you have to go to state Q2 and make it to A2 and move right if this is the symbol there. Then how can you represent this in terms of zeros and ones is simple. See this, Q1 already we represented as 1 1, and then followed by 0, so that we can differentiate it, and then A1 we already represented as 1 and then followed by 0, differentiate it, and then Q2 is represented as 1 1 and then write as 0, so that you can differentiate it, and then A2 is 1 1, we already seen it. And now for right and left also we could use some encoding. Let us say for left it is 1 and for right it is 2 1s. then I'm going to write it as 1 1, then again the next symbol is going to follow, right? So using a string of 1 1, I can represent every transition. So the entire transition function for a Turing machine can be represented as a string of zeros and ones. It has a very important implication which we are going to see later, but for now understand that every Turing machine can be encoded as a string of zeros and ones. Now these strings of zeros and ones will be kept in this T1. Okay. Then how does this universal Turing machine work? If you want to use a Turing machine as an adder, you design the entire Turing machine, and now we have seen that every Turing machine can be represented as a string of zeros and ones, and now that representation is going to be stored in the tape T1. Therefore, universal Turing machine is going to see the actual Turing machine, which means the program which you have given to it, and it is going to see the input, and then it is going to use this tape T3 in order to simulate what happens if this Turing machine actually runs on this input. So that is how this can be used as a computer. Okay. Therefore, Turing is right. A Turing machine can be used as a computer, and Turing machine is as powerful as a today's digital computer, right? And one important point here you should remember is, from all this discussion, you had to remember one important point. Every Turing machine can be represented as a string of zeros and ones, which means you can take any Turing machine and encode all its states and the input symbol into ones and use 0 as a delimiter, and then you could encode the delta. See that transition function is nothing but a Turing machine, isn't it? So if you could represent that transition function in terms of zeros and ones, it is nothing but we are representing any Turing machine in terms of zeros and ones. Therefore, one important point you should remember here, and again we are going to revisit this point, every Turing machine can be represented as a sequence of zeros or ones. Therefore, a Turing machine is nothing but a string of zeros or ones. So how can you represent a Turing machine is, if I have sigma equal to 0 comma 1, and if I construct the language sigma star, then Turing machine is nothing but one of the string of this language. But then just be careful that every string of zeros and ones may not be a Turing machine. Okay, I'll just tell you two statements. Just write it down. One statement is, every Turing machine can be represented as a string of zeros and ones. That is one statement. And the second statement is, not every string of zeros and ones might be a Turing machine. The reason is, if you take a random string, it may not get converted to a Turing machine. But then if you take a Turing machine, we can convert it. Keep that in mind. Okay. Therefore, the Turing machine is nothing but a string of zeros and ones, right? So that is how we have proven that Turing is actually right, that a Turing machine can be used as a computer. So finally, to wrap it out, I have three tapes T1, T2, T3. At any point, I am going to use T2 and T3 to find out the configuration of the tracing, and then I'll use that configuration and I'll go into T1 to see how the Turing machine behaves in that configuration. And once I get the transition, I'll apply the changes on these two. Got it? That is how our universal Turing machine can simulate any Turing machine on the given input. Therefore, Turing is right. Turing is right, right? We have seen various types of grammars, various types of machines, and various types of languages. Now, collectively on these languages, there are some few questions we could ask, like how these. I'm saying that there is a let me draw the diagram, then you'll understand it better. I've told you that there is one language which is enclosing everything, that is recursively enumerable language, which is nothing but set of all languages. This is nothing but set of all languages which are acceptable by or accepted by Turing machines. And now inside this, the set of all languages which are accepted by halting Turing machines is there, which is recursive language. And inside that, set of all languages which are accepted by linear bounded automata, which are called context sensitive languages. And inside that, set of all languages accepted by push down automata, which are called as context free languages. And inside that, set of all languages accepted by finite automata, which are called as regular languages. So we have all these classes of languages. Now the one interesting question which you could ask is, is this regular languages really a subset of context-free languages? Which means, is there at least one language which is not regular, which is context-free? If there is at least one language which is not regular, which is context-free, then you can say that the regular language is a proper subset of context-free language. And for that, yes, we can say answer is yes. The language is a power n, b power n. A power n, b power n, n is greater than or equal to 1 or 0 is a language which is not regular but which is context-free. Similarly, you could ask one more question saying that is context-free languages, set of all context-free languages, a proper subset of context-sensitive languages, which means all the strings accepted, all the languages, is there any, at least one language which is accepted by context-sensitive or which is accepted by linear bounded automata, which is not accepted by a full John automata. And you can find out that yes, there is one language which is a power n, b power n, c power n. And now naturally, to extend this question, you might ask, is there any language which is recursive and which is not context sensitive language? That is a difficult question to answer. In this sense, now I have given you some examples like this just to prove that yes, it is a proper subset. But then if you have to prove that there is a language which is recursive but not context sensitive, I cannot give you any such language like this, which means I cannot say a power n, b power n, c power n or a power p such that p is a prime. Such kind of proof or language is not available for us. So in order to prove that, there are mathematical theorems which are used in order to say that, in order to prove that there is at least one language which is recursive but which is not context sensitive. So we don't have any language, or if you ask me to give us an example, I don't have any example, not anyone has. So proving it is a other case, which means they have used mathematical theorems to prove that there will be one language, at least one language, which is not context sensitive and which is recursive. That is what we could say. But then precisely writing that formal language is difficult. We can say that there exists at least one language and we can prove that, but then we cannot say what that language is because we don't have that. Okay, so and again the same question is true here also. So if you ask me, is there at least one language which is recursively enumerable, which is not recursive? Answer is yes, there is at least one language, but then I cannot give you in this form a power n, b power n, c power n. So using the mathematical theorems, we can prove that these are all proper subsets of each other, which means this one is proper subset of this, this one is proper subset of this. But then we cannot say exactly what what that language is. And now next extension is, you might ask next question you might be asked, you might have doubt is, yes, Turing machine is the most powerful machine in all the machines like finite automata, full John automata, linear bounded automata. If you take all the machines, we know that Turing machine is the most powerful machine. Now the natural question is, how powerful is this Turing machine? So you might ask whether Turing machine is capable of accepting every possible language, which means if there are some languages, let us say set of all languages, I'll take all the languages which are possible. Now the interesting question to ask is Turing machine capable of accepting all these languages? Which means for every language, will there be a Turing machine? That is the interesting question. So in order to answer it, we are going to use the set theory. Okay. So the question is, I want to answer this question. For every language, is there a Turing machine accepting it? It is a difficult question to answer. So for every language, do we have a Turing machine to accept it? Is a difficult question to answer it directly, but then we are going to use indirect proof to prove it. So I'll just give you a overview about what I'm trying to do, and then I'll tell you in detail how to do it. Okay, giving you an overview will help you in understanding the concept better before getting into the actual concept. In order to answer it, what I'll try to do is, I'll show that the set of all Turing machines are infinite. the set of all Turing machines are infinite, and I'll show that the set of all languages are also infinite. This is set of all Turing machines and this is set of all languages. And then I'll show that, I'll try to prove that the number of Turing machines available, even though infinite, are lesser compared to the number of languages available. Both are infinite only, but then I'll prove that this is a bigger infinity and this is a smaller infinity. By showing that, we can understand that for every language, if you give one Turing machine, then we'll quickly run out of the Turing machines, and then there will be some languages remaining for which there will be no possible Turing machine. Remember, every machine can accept only one language. Therefore, if I have, let us say, 10 machines, I can accept only 10 languages. Similarly, if I have these many machines, I can accept only these many languages. Now, it just indicates that there are some languages remaining for which we'll never be able to give a Turing machine. Therefore, using this, we can prove that Turing machine is not so powerful that it can accept everything. Therefore, there are some languages which are not even recursively enumerable. Recursively enumerable means they are not accepted by Turing machine. So, even the most powerful machine, Turing machine, is not capable of accepting every language. So, using this proof, using this argument, we can prove that. But then I cannot find out a language which is not accepted by Turing machine. That is not what I mean to say. What I mean to say is I'll use some methods or theorems using which I'll prove this. Now, in order to prove this, I'll talk about countable sets, uncountable sets, finite sets, infinite sets. Then I'll just build some mathematical theory gradually, one by one, step by step, and you please keep noting them down, and later slowly I'll prove this. I'll prove this method. Okay. Now look at this. Sets are of two types. Sets means you know that already. Set is nothing but a collection of objects. I'm not going to define it. And sets is of two types. Again, we have something called as set theory, group theory. There I'm going to discuss about sets in mathematics. But now I'll just discuss the part which I need in order to explain about the Turing machines. I'm not going to discuss everything. Okay. Later we shall see it again. Now, sets are of two types. One is finite and other is infinite. Finite sets means if all, you know that, okay, I'm not going to define. Finite means if there are countable number of elements like 10 elements, 20 elements or whatever. For example, if I have a power n such that n is less than or equal to 10 power 10 power 10, even though there are many elements, it is still finite, okay? So you know what a finite is, I'm not going to define it. And now infinite means there is no upper bound. For example, a power n is greater than or equal to 1. If I have anything like this, a power n such that n is greater than or equal to 1, there is no upper limit. That is called infinite. Now coming to infinite, there are two types of infinite sets. One is countable infinite and other is uncountable infinite. So countable infinite is actually smaller infinite compared to infinite means there are lots of strings or lots of elements, and again in this lot of elements we can say that it is not too many and it is too many, which means if I say that a set is countable infinite, it means it is infinite but it is not too much. And if I say it is uncountable infinite, it is infinite and it is too much. If you try to compare a countable infinite set and uncountable infinite set, we'll see that we'll take it that countable infinite set is lesser compared to uncountable. So it is not right in writing like this, but then still this is the actual meaning. So you should not write it directly, but I'm going to write it. It is the actual meaning, but don't write it anywhere. What I mean to say is finite set is less than, countable set is less than uncountable set. It is not given anywhere, but actually that is the meaning that I want you to understand. So finite set is less than, countable sets is less than uncountable sets. And now my main intention in talking about this entire theory is simple. I want to prove that set of all Turing machines are countable and set of all languages are uncountable. Therefore, number of Turing machines are less than number of languages. Therefore, there are some languages which are not accepted by any Turing machine. So, there are some languages which are not recursively enumerable. That is what I want to prove by the end. Okay. Now, before going ahead, given any set, how will you distinguish whether it is finite or infinite? That is very easy, straightforward. Now, once you found out that talking about finite sets is not very interesting because no one is interested in talking about it, but then talking about infinite sets is actually the most interesting thing. Now when we talk about infinite sets, we have to make distinction between two types. One is countable and uncountable. Given any set which is infinite, how can you say that it is countable, or how can you say that it is uncountable? That is the most important question. Now watch this. Countable set means a set capital S, any given set, is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of natural numbers. What do I mean by saying this is, if a set is given and if you take every element of the set and if you can give one element from the natural numbers to this one, and if you can arrange them all like that, then it is called as a countable set. And what is uncountable set is a set, obviously if a set is infinite and if it is not countable, definitely it is uncountable, isn't it? So instead of saying it entirely, which means if we cannot put in one-to-one correspondence with the set of natural numbers, what you could directly say is a set is said to be uncountable if it is infinite and if it is not countable. You can directly say that even. Okay. So I'll just take an example and I'll show you what I mean by giving one-to-one correspondence from the set, from all the elements of a set to all the elements of a natural numbers. See this, the definition says that a set is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of all natural numbers. It is, you might think that it is very simple definition, but then in order to actually apply this, it takes a lot of experience and practice. So I'll discuss about some of the examples using which you can answer any question in GATE coming to this topic, countability. Okay, so watch it once. Let us say, let us start with a small example, set of all even numbers. Let us assume that set of all even numbers is written like this: 0, 2, 4, 6, 8, 10, 12, so on. They are all set of all even numbers. Okay, and now I'll take set of all natural numbers. Set of all natural numbers are 1, 2, 3, 4, 5, 6, 7, so on. Fine. Now there should be one-to-one correspondence between every number here to every number here. If I can give that one-to-one correspondence, which means for every element in the set E, if you can give an element in the set N natural numbers, then I can say that set of all even numbers is countable. Okay, so how can I do that? We already did it, isn't it? So now for 0, the element given in natural numbers is 1. For 2, the element given is 2. For 4, the element given is 3. For 6, element given is 4. Right? Now, how did we do that? So, what is the procedure? So, given any element, will there be a natural number? That is the question. So, let us say the element given is 2i. So, what is the natural number corresponding to this? I think for 2i, natural number corresponding to this is I plus 1. Isn't it? Check that. For example, 2i, 2 into 1, 1 plus 1. 2 into 2, 2 plus 1. 2 into 3, 3 plus 1. Therefore, for any element of form 2i, we can give an element of form I plus 1. Right? So, what can you understand from this? We can understand that for every element in the natural even numbers, we can give an element from the natural numbers as a correspondence. Therefore, we can say that this even numbers is countable since we are able to give it. So it is very straightforward for this example, but then it is not so easy to prove that some other languages or some other sets are actually countable. So let's just extend some of the I'll just explain you some of the terminologies used here. One is called index. Now element 0 is given element 1. Therefore, I call this number as the index given to this. This number as the index given to this. Therefore, every element is going to get an index, and that index is nothing but a number from the natural number set. So, one other way of saying it is, if every element in the given set is going to have an index, then that index is nothing but the number to which it can be mapped to in the natural numbers. Therefore, you can say that such a set is countable, right? And this is how you can say that the set is countable, and every element is also going to have an index. So the element 2i has an index of I plus 1, isn't it? So if we can get the indices, then we can say that if every element is having an index, then we can say that the set is countable. One definition is, if you can put them in one-to-one correspondence with natural numbers, it is countable. Or for every element, if there is an index, which means the position at which it can be placed in the set, if you can say that, then also it is countable. Now let's see one more example. Let us say set of all odd numbers, 1, 3, 5, 7, 9, 11, so on. Now, can these elements be put in one-to-one correspondence with natural numbers? Check this. We can put them like this, isn't it? Therefore, for every element in this odd number set, there should be an element in the even number, in the natural number set. For the element 2i plus 1, what do you think is the corresponding index? So for the element 2i plus 1, for example, for the element 5, the corresponding element is 3. So how can you get this one? It is nothing but same as I plus 1. So for every element of the set of odd numbers of type 2i plus 1, the corresponding index we have is I plus 1, isn't it? Therefore, what can we say? Since we are having for every element one element in the natural number, there is a one-to-one correspondence between the elements. Therefore, the set of all even numbers is countable and the set of all odd numbers is countable. Okay. And now let's see one more example. The set of all real numbers. Real numbers means we can take any number, 0.1, 0.2, 0.3, anything, isn't it? Now, if you take set of all real numbers, the problem is just between 0 and 1, there can be so many numbers that they can all eat up the natural numbers available. Whatever natural numbers are there, I can generate so many numbers between these two that they can eat up all of them. Or you can come up with any method in which you will try to assign a number to that, but then it will all fail. Therefore, the set of all real numbers, the proving that set of all real numbers is this way. Between 0 and 1, we have so many numbers that they are capable of eating up all the numbers. Okay. So later I'll prove it in a concrete manner using some method called as diagonalization. But for now, understand that just is an informal proof, just to understand for your understanding sake. It is informal proof. Later I am going to give you a formal proof. What I mean to say is, only between 0 and 1, we have lots of numbers that all these numbers have the capacity to eat up all the numbers of natural numbers. So, only between these two, if we eat up all the natural numbers, what about the remaining numbers on the number line scale? Real numbers means everything, isn't it? Therefore, we cannot actually give one-to-one correspondence between real numbers and natural numbers. Therefore, set of all real numbers is uncountable. Remember this, I'll give you the proof later. So the proof for even numbers is countable and odd numbers is countable is, for every element I have given you an index. For every element 2i, the index is I plus 1. For every element 2i plus 1, the index is I plus 1. Therefore, if you are able to give an index, that is nothing but a correspondence in the natural number. That is how I am able to prove that they are countable. But then for these real numbers, I will not be able to come up with any index. Now, I'll just use some other proof. This one-to-one correspondence is okay. You can prove it this way, but then it is difficult to prove it for all the sets that they are countable. We shall use some other better methods to prove that a set is countable. Okay, I'll tell you what they are now. Using the previous definition for countable sets, like putting one-to-one correspondence from all the elements of a set to natural numbers, it is very confusing, which means for some sets, it might look as if we can easily put them in one-to-one correspondence, and for some sets, it might look as if we cannot put them in one-to-one correspondence, and in both the cases, you might go wrong. So, by using the definition which is given in textbooks, some of the textbooks, that previous definition, it is very difficult to say whether a language is countable or not, whether a set is countable or not. Therefore, I have framed this new definition And using this, you'll be able to understand this concept very easily, and you'll be able to answer any gate question, and you'll be able to prove the rest of the things very easily. So I framed this definition. You please read it and make a note of it, and it is right. And anything that you want to prove as countable can be kept in this form. Okay, I'll read it out and I'll explain you this, and then I'll take examples. The previous examples which we have seen, the set of all even numbers, odd numbers, we shall again examine them in the light of this definition, and then we shall see how we could use this one in order to prove that set of all Turing machines are countable, which means set of all Turing machines are infinite but less, and then we shall prove set of all languages are uncountable later. Okay, so just watch it once. A set is said to be countable. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated for any particular element. Okay, let's go step by step. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated. This means that if you are given a set, then you should be able to write a kind of algorithm or program, but then I am not saying that it is an algorithm because it need not stop. So you just give a method using which we should be able to generate all the elements of the set one by one. You give me a method, okay, using which all of them are going to be generated, and then for any particular element, which means given any element, if you follow your method, it takes only finite number of steps to generate it. If that is the case, which means, try to understand it, I'll give you an infinite set. What you should do is, you should come up with a method or a procedure, or we should not call it an algorithm. Calling it as a method or procedure is right, but then don't call it as an algorithm because it need not stop. It could go on infinity, but then what is required is you should be able to write it down as a method. Now that method should be able to generate all the elements of the set one by one. And now, given any particular element, I should be able to reach that element using your method in a finite number of steps. Now, if you can give me such a method, then the language is said to be countable. Then the set is said to be countable. Okay, so come up with a method, given a set, generate it, which means generate all the elements, enumerate. Enumerate means write it down. Every element, writing every element one after one is enumeration. And now enumeration method means we are writing a method which will write down all the elements one after the other. Now your method should write down all the elements one after the other. Then what I need is, I want this method so that all the elements have to be generated, so that all the elements can be generated in any particular way. And if any particular element is given, I should be able to reach it in finite number of steps. If such a method is given, then I can call that the set is countable. And the finite number of steps that are required, that are taken to generate an element, which means given an element, you are able to generate it in finite number of steps, right? That finite number of steps which are actually taken in order to generate that element can be used as its index, which means you can call that number as the index. Now once you get the index, that is nothing but a mapping into the natural numbers, isn't it? Once we get an index, that is nothing but the mapping into the natural numbers, isn't it? So it is simple, very simple. So definition is very simple, and I'll just take the example, and then I'll show you how to use this definition to prove that a set is countable. Now, as an example, let's say set of all even numbers. Set of all even numbers. Now, you come up with a procedure using which you will be able to generate all the even numbers, and then using your procedure, if I give you any element, you should be able to reach that element in a finite number of steps. If we can do these two things, then I can say that it is a countable, right? So how can I generate set of all even numbers? You can just write a for loop, isn't it? Maybe I can write like this: for I equal to 0 to infinity. It is not an algorithm because we are going to infinity. What is an algorithm? You should always stop in finite number of steps. But since I is going from 0 to infinity, we are never going to stop in finite number of steps, isn't it? for I equal to 0 to infinity, if I write like generate means just print 2i. So this is the enumeration method, right? So now if I write like this, what will this enumeration procedure do? It will try to generate all the numbers one after the other. Like first it will generate 0, then it will generate 2, then it will generate 4, then it will generate 6, then it will generate everything. Therefore we found out an enumeration method using which we will be able to generate all the elements. But then it is not just enough. Just finding out the enumeration method is not enough. What you should do next is you should be able to generate a given number in a finite number of steps. For example, how many steps does it take to generate 0? 1 step. How many steps does it take to generate 2? 2 steps. How many steps does it take to generate 4? 3 steps. 6, 4, 8, 5 steps, so on. Therefore, every element can be generated after fixed number of steps. What is the implication of that? Now, these number of steps can be used as the index for this particular element. Therefore, for every element, I found a natural number, isn't it? That natural number is the index itself. Therefore, I can say that the set of all even numbers are countable because there is a one-to-one mapping to the natural numbers. We found the one-to-one mapping without actually doing that original definition. See, you might feel that this method is long and it is difficult, but then later you'll understand that with other examples, this is the easiest method rather than putting one-to-one correspondence to natural numbers. Okay. Now let's see how to do this with the set of all odd numbers. Now we found out that set of all even numbers are countable. Now let's see what to do with the set of all odd numbers. Set of all odd numbers. It is simple. For I equal to 0 to infinity, you generate I plus 1, then 2i plus 1. Then what will be generated? Initially 1 will be generated, and then 3 will be generated, 5, 7, 9, 11, so on, right? And what about the index? This will be generated in 1 step, this will be generated in 2 steps, 3 steps, 4 steps, 5 steps, so on, isn't it? So every element can be generated in these many steps. Therefore, these are nothing but the indices for these elements. And since every element has got an index, and one more thing, for a particular index, there will be two elements will not be there, which means 2 elements are not going to be mapped to one index. In 1 step, we are generating only 1 element. Therefore, every element will get a different index because at every step only 1 element is going to be generated. So this particular element can be used as the mapping into the natural numbers. So for every element of the set, we got a mapping into the natural numbers. So we can say that set of all odd numbers is also countable. What about set of all real numbers then? Set of all real numbers, it is very difficult to come up with an enumeration method first. So you cannot generate all the real numbers using an enumeration method. Maybe you might try to generate it, but then later you will not be able to reach a particular element. Let us say you are trying to generate all the real numbers, but then if you start with 0.0, then 0.01, then 0.001, then 0.0001, this procedure itself will never stop, because if I start with 0.01 and then 0.1, 0.01, 0.001, this procedure itself will never stop and it will go on, keep on going for infinity, and you will never reach an element starting with 1.0. Therefore, even though it is not an actual proof, we shall prove this later. I'll prove that the set of all real numbers are not countable later using some other method. But for now, just understand that giving a enumeration method and then generating an element in fixed number of steps for real numbers is impossible. Therefore, it is uncountable. Let's examine some other examples. Now, knowing that set of all Turing machines are countable is going to lead us to many implications. Now, what are the results we get out of it is, since we already know that, watch it. Now, Turing machines are countable. Let me say C is the shortcut to represent that Turing machines are countable. Then what does this imply? Then how many our Turing machines are there? There will be those many recursive enumerable languages. Therefore, since the number of Turing machines are countable, the number of recursive languages are countable, isn't it? Therefore, recursively enumerable languages, not recursively enumerable languages are countable, isn't it? Now, what does this mean? If recursively enumerable languages themselves are countable, so we can say that a recursive language is a subset of recursively enumerable language. Therefore, the number of recursive languages are countable. RL means not regular, it is recursive languages. Recursive languages are countable. Now, context-free language is a subset of recursive language, isn't it? Sorry, context-sensitive language. Therefore, context-sensitive languages are countable. And push down onto that, context-free languages are again subset. Therefore, context-free languages are countable because every subset of a countable set is countable, and we know that all these languages are, like Russian dolls. If you open Russian dolls, you know that if you open a doll, inside that there will be one more doll. If you open that doll, inside that there will be one more doll, isn't it? Like that, inside that language everything is contained. So therefore, if the main language is countable, then already the languages which are present inside it as a subset, proper subset, are already countable, isn't it? So context-free languages are countable, therefore regular languages are countable. Everything is countable. All the languages, either you say the number of recursively enumerable languages available, they are countable. Everything is countable. And next implication is, if you look at the hierarchy of these Turing machines, these machines, Turing machine is the biggest machine, and all the machines are present inside it. And what we could say about all this is, now see, the better solution will be, instead of talking about the languages directly, the better idea would be the other one. So for every language there is a Turing machine, isn't it? So every recursive language if number of Turing machines are countable, every recursively enumerable language is countable. Okay, the set of all recursively enumerable languages, and direct implications will be like this. So we can say that every Turing machine is a push-down automata is, you can modify a Turing machine in such a way that it can act as a push-down automata. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, we can modify a Turing machine in such a way that even though it is having the input tape, instead of using it as a tape, if it could use it as a stack. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, push-down automata are a slight modification to Turing machine, isn't it? And now, if we know that even LBA is also a slight modification of Turing machine. If already Turing machines are countable, then a subset of the machines which are supposed to use only that restricted stack, they are also countable. Therefore, push-down automata are countable, and finite automata is nothing but a Turing machine which is restricted in such a way that it has to use only finite amount of memory on the tape. Then finite automata are also countable. So everything we know of as of now are all countable because of this rule. Okay, but then even though the number of languages are countable, see this, one important thing is, even though all these languages are countable and the machines are countable, we didn't prove that the set of all languages are countable. Okay, so I'm not trying to confuse you, it is a bit confusing, so you please rewind the video over and again and listen it. So what I didn't prove at is, I didn't prove that the set of all languages possible are countable. I didn't prove that. Actually, the set of all languages possible are uncountable. Now, the set of all Turing machines or any number of machines possible is countable, and the set of all languages possible is uncountable. Therefore, there are some languages for which there are no machines at all, which means there are some languages which are not even recursively enumerable. Okay, we shall prove it later, but for now these are all the implications which we got from this. Okay, let's talk about computability and decidability. Actually, both computability and decidability are same. In the sense, both of them talk about whether there exists an algorithm or not. Okay, before going ahead, let me explain you what an algorithm is, and let me show you what the difference between Turing machine and algorithm. Okay, So algorithm it is nothing but a Turing machine, but this Turing machine is supposed to halt. So if for a problem there is an algorithm, it is as good as saying that for that problem there is a Turing machine which is always going to halt. But then if you have a Turing machine, it is not actually an algorithm. The reason is algorithm is supposed to halt after finite number of steps or after some number of steps. But then Turing machine is never going to halt. Therefore, only halting Turing machines are considered as algorithms. Okay. And now you already know that Turing machines are countable. So I'll just extending this concept. You already know that Turing machines are countable, isn't it? And therefore, halting Turing machines are a subset of Turing machines, and I already told you that every subset of a countable set is already countable. Therefore, halting Turing machines should also be countable. So, halting Turing machine is nothing but an algorithm. So, what did we find out now? Even the algorithms are also countable. But then we found out that the number of languages are uncountable. Every problem can be compared to a language. Okay, so now the number of problems are uncountable and number of algorithms are countable. Therefore, what could we derive? That there are some problems for which an algorithm might not exist. Okay, so let's talk about what is the exact meaning of computability and what is the exact meaning of decidability. I hope that you understood what an algorithm and Turing machine is. From now on, I am going to use wherever in order to say that there is an algorithm, I can even say that there is a Turing machine which halts, or in place of Turing machine which halts, you can put an algorithm. Okay. Now let's see what is the difference between countability and decidability. Actually, both the concepts are very identical, or sometimes both of them are used in place of each other with a minor difference. Okay. Whenever we talk about a function, so whenever we talk about a function, like let us say f of n equal to n square plus 1. So what is the meaning of it is, if you give it some n, it is going to compute this value. So given an input, if it is going to compute some output, then that is called a function. Now if there is a algorithm to compute a function, then such a function is called computable. Okay. So if there exists an algorithm, or what is an algorithm? Turing machine which halts, isn't it? If there exists an algorithm or a Turing machine which halts, which takes this input and then produces this output. In terms of Turing machine, how can I write it is, if there exists a Turing machine to which if the input is given on its tape, then again it is going to produce the output on the same tape, and then it is going to halt for every input given is called a then that function is called computable. Okay, so what is the definition of computability is, if there is a function which is defined on a domain. So what is the domain for this? F of n, let us say the domain is set of all numbers, set of all integers. Then what about the range? Range is nothing but set of all a subset of positive integers. Okay, so given a function and a domain, domain means from which set are you going to pick up the input. Given a function and the domain, if there is a Turing machine which will produce the output on the tape, given that input on the tape, it should produce the output on the tape, and it should definitely halt for every input chosen from the domain. Okay, domain is very important. So once you fix up a domain, and if for all the inputs from the domain, if your Turing machine is definitely going to halt with the output on the tape, then we can say that such a function is computable. It is very simple. See, in simple words, what it is let us say you have a function. Okay, let us say the function could even be not just this one. The function could even be a problem. I don't want to use the word problem, but then just think of it like this. We want to sort all the numbers. Now all the numbers are given to the Turing machine. They are all on the tape. And now the Turing machine should try to sort it out and then keep them in ascending order. Then that is also a function. A function is going to take a set of natural numbers and then it is going to produce a set of natural numbers. Therefore, domain and range both are natural numbers. So if your Turing machine is able to solve that function for all the inputs coming from your domain, and it is definitely going to halt, then such a function is called computable. Okay. And coming to decidability, we just want to simplify the things. So very often talking about functions and then giving some proofs is somewhat difficult. It is not impossible, but then it is somewhat difficult. Just to simplify the things, we are more interested in rather than functions, we are more interested in problems. So what is a problem is a statement whose output will be either true or false. And now our whenever we, for example, a problem can be like this. Classic problem is n, a number n, a prime? You just have to find out is m a prime, which means here you are not actually taking the input and then producing some output. Here you take an input and you just say one thing, either yes or no. If 3 is given, if n is given as 3, you say yes. If n is given as let us say 10, you say no. Alright. So if you have such a problem whose answer is either yes or no, and if there is an algorithm or a Turing machine which should definitely halt for all the inputs from the domain. So here domain is, let us say, domain is set of all natural numbers. Set of all natural numbers. Okay. Now, when do I say that a problem is decidable is if for a problem there exists an algorithm or a halting Turing machine, both are same, which will take anything from the domain, which means it will take any input from the domain and which will say either yes or no correctly, and it should halt. If you have such a machine or such an algorithm, then we can say that that problem is decidable. So decidability is very easy to apply compared to computability. It can be shown that we can convert a problem from computability to decidability and then think about this, or give some proof whether a problem is decidable or not. Okay. So what we are interested in is either in TOC or in algorithms. Rather than talking about computability, we'll talk about decidability. We'll take a function and we somehow convert it into a yes or no problem, and then we try to find out if there is a Turing machine which can answer that problem. In case if there is a Turing machine which can answer that problem, we can say that there will be a Turing machine which can compute it. It is straightforward. Therefore, we are not interested actually in the functions, we are interested in the problems. Okay. So what I mean to say is, whenever we have a domain, okay, and now given any input from the domain to a Turing machine, that Turing machine should definitely halt and say yes or no for such a problem if you can find such a Turing machine, or if there exists such a Turing machine. If we can prove that there could be such a Turing machine existing, then we can say that the problem is decidable. Okay, simple. So function means, computability means we talk about function and there should exist algorithm or halting Turing machine. And decidability means we are talking about a problem which is nothing but yes or no answer, and if there exists algorithm or Turing machine which halts, then we say that it is decidable. So computability and decidability both are actually same, but only difference is when we talk about the function and when we talk about the problem. I hope that you understood it. And one more thing you should be very, very careful is, every time a problem, whether it is decidable or not, that should depend on the domain, because given a single instance, it is always decidable, isn't it? So for example, given a single instance, it is always decidable. Simple. So how can I prove that a single instance is decidable is, let us say you have given me some problem. Okay, I'll just talk about a problem which is undecidable, which means we cannot give a generic algorithm for that, and then I'll tell you that for a given instance we can find a problem. See, it is somewhat difficult to understand, so you please pay more attention here. Now there is one example, classic example. Example is, a given grammar capital G is ambiguous, which means given a grammar you should find out whether it is ambiguous or not. Okay, And now let me say the domain is set of all context-free grammars. So actually this problem is undecidable. Okay, I know I'll just talk about this problem shortly after some time, but then this problem is undecidable, which means there is no algorithm or there is no halting Turing machine which can say that a given grammar capital G is ambiguous. This problem is ambiguous. So how is it a problem is, now you give a specific instance or specific grammar and you put in place of G, the answer should be either true or false, isn't it? So the statement will be either true or false depending on what the input is. But the domain is set of all context-free grammars and this problem is undecidable. Later I'll show you how to prove that it is undecidable. But for now assume that it is undecidable. Now if the domain is not set of all problems, if I give you only single instance, which means I'm just giving you domain is not this, I'm just giving you this particular grammar G1, is it decidable or not? This is definitely, this particular grammar G1, is it ambiguous or not? So answer is definitely it is decidable. The reason is you could find a Turing machine which will always say yes or which will always say no. Now if this grammar is actually ambiguous, now you can give this Turing, now there exists a Turing machine which will say yes, isn't it? So it is very difficult to understand this, but just pay attention here. See, I'm saying that if the domain is very large, sometimes some problems might go undecidable. But then if the domain is a single instance, which means given a grammar, if you are asking whether it is ambiguous or not, I'm saying that it is decidable. Why? There has to be a Turing machine which should say yes or no, and then it should definitely halt. Now what I take is, I'll just produce a small Turing machine which will always say yes. And then I'll say that there exists a Turing machine which will say this, or I'll produce a Turing machine which will always say no, and in case if the answer for this one G1 is not an ambiguous grammar, then I'll say that for this problem there is a Turing machine, therefore it is decidable. So just keep this point in mind, that a particular instance of any problem is always decidable, but then when it is applied to a common domain, it might be decidable or undecidable. For that we need to prove. So it is very important, just write it somewhere. Any particular instance of a problem is always decidable. Any particular instance means given a particular grammar G1, whether it is ambiguous or not, it is decidable, because you can give a Turing machine which always says yes or which always says no. At least one of it is going to be the answer, isn't it? So very important point. Given an instance of a problem, it is always decidable. Why? Because there always exists a Turing machine. What is a Turing machine? Take a Turing machine which always says yes, or take a Turing machine which always says no, whatever the input is. Now at least one of that Turing machine is going to be the Turing machine for this instance, isn't it? That is how we can prove it. But then given over a range, then that depends, right? So now in TOC, our main concern is will be given many problems, and now we should be able to say whether that problem is decidable or not. So in order to do this, we use a trick, we use an indirect method. So finding out whether every problem is decidable or not, it's somewhat difficult. So what we do is, we find out one problem which is undecidable. Okay, let me just show you this in terms of writing. Hope that you have taken everything, and whatever I speak, you please note them down also. You keep pausing the video and writing it. Okay, these are all very important. And what happened is, in GATE, for the past 2-3 years, before 2-3 years, they didn't focus much on the Turing machines, decidability, countability. But then I think they have used the regular expressions, regular languages, context-free grammar questions so much that I think they are out of the questions. Therefore, they are now focusing on a new topic. See, and one more thing is, previously, before 5-6 years, this particular GATE question paper, the number of aspirants used to be less and the coaching used to be not so good. Therefore, even for a moderate kind of question, it was very difficult for many people to answer them. But now with these many coaching centers and with this lot of effort going on, people are able to answer many questions very easily. Therefore, the standard of the GATE examination is going to be increased. So if they have to ask a difficult question in TOC, the only topics which will be suitable will be Turing machines or decidability, undecidability, countability. So these are very, very important. Even in algorithms also we have the same concepts. So I feel that in GATE 2015 they are going to definitely touch more questions from PNP, decidability, undecidability, and then Turing machines. So I'll be discussing about Turing machines in depth, so that even if they ask you a very difficult question, you will be able to answer it. Okay. So what I would like to tell you is, whatever I speak, even every single word, you please pause the video and keep noting them down. It is very difficult for me to write everything on the board. It is not that if there is something on board, you should write it. Write everything that I am speaking, so that you will be able to, easily understand it later or easily refer to it later. Now let me tell you one important, very, very important point here. This is going to be very important even when you discuss algorithms. Now, how can we prove that a problem is undecidable? I'll talk about something called as convertible. So if there is a problem P1 and if there is an algorithm or a halting Turing machine which can convert it to a problem P2, which means there is algorithm, okay, and now if there is an algorithm to solve problem P2, which means there is an algorithm, this P2 is decidable. See, now there is a problem P1, I am able to convert it to problem P2, and now problem P2 there is algorithm. Then I can say that for problem P1 there is an algorithm. Therefore, if P2 is decidable, then P1 is decidable. How? First you convert the problem P1 to P2 and then you solve P2. Therefore, since we are able to solve P2, it is nothing but the answer for P2. Now the conversion should work in such a way that the answer to P2 should also be an answer to P1. Okay, I'll just repeat it again. See this, if there is a problem P1 and there is an algorithm to convert it to a problem P2 in such a way that if the answer to P1 is true, the answer to P1 should be true, which means whatever answer I get here, that should even be the answer to P1. If there is a conversion algorithm like that, and now there is an algorithm to solve P2, it is as good as saying that we got an algorithm to solve P1. Then what is the algorithm? Conversion algorithm plus solving algorithm. Now this procedure is called reducibility. Reducibility means converting one problem to other problem in using an algorithm or a halting Turing machine. Now, if you find out that this problem is decidable, then definitely this problem is decidable. Okay, so I'm just writing it. See this: if P2 is decidable, then P1 is decidable. Under the conditions, what are the conditions? There has to be algorithm to reduce every instance of problem P1 to an instance of problem P2, and there has to be algorithm to solve problem P2. Therefore, if there is a reduction algorithm and then there is a solving algorithm for P2, then we can say that if P2 is decidable, which means if there is a solving algorithm for P2, then P1 is decidable. If we can solve P2, it is as good as solving P1. Okay. And it is very straightforward. I think you will understand it, but the next point is somewhat difficult to understand, so just try to understand this. Now, if it is already known that, if it has been already proven that, or it has been already proved that problem P2 is undecidable, problem P1 is undecidable, and now there is a polynomial time conversion to problem P2, definitely problem P2 cannot be decidable. Okay, so try to understand this. If P2 is decidable, P1 is decidable. But before this, if it has been already proven that the problem P1 is undecidable, which means there is no algorithm or Turing machine. It has been already proven. Then definitely P2 should be undecidable. The reason is, in case if P2 is decidable, then it actually conflicts with our proof that P1 is undecidable. Okay, these 2 points are very, very important. Okay, so if there is a polynomial time conversion from, or not polynomial time conversion, we shall talk about the time later. If there is an algorithm or a halting Turing machine which can convert every instance of problem P1 to some instance of problem P2 in such a way that answer to problem P2 is also an answer to problem P1, and if there is an algorithm or halting Turing machine which can solve P2, then we can say that P1 is decidable, which means if there is a reduction algorithm from P1 to P2 and if P2 is decidable, then P1 is decidable. This is straightforward, isn't it? Now, the second point is very important. If P1 is already proven to be undecidable, it is already proven to be undecidable, then definitely P2 must be undecidable. Why? The reason is, if P2 is decidable, then it turns out that P1 is decidable, which actually conflicts with our already existing proof that P1 is undecidable. Therefore, P2 should definitely be undecidable. So, how do we now from now on, how can we prove that a problem is undecidable is, see, this particular point is given wrong in every possible book. In every possible local addition book you take it, in every possible gate question they solved it, this point is completely given wrong. Okay, if you want to learn about it, please read this standard books like Ullman. There they have given it right, but then don't read them, you will not be able to understand this. Just follow my lectures, I am going to cover everything possible. Okay, now what I am trying to say is, in order to prove that a given problem is undecidable, so what you should do is, try to find out first a Turing machine. If it is not possible, you cannot say that if you fail to find a Turing machine which halts, or if you fail to find an algorithm, you cannot directly say that it is undecidable. There should be a rigid proof. Now, for that reason, already there is one small problem or one basic problem which has already been proved to be undecidable. That problem is halting Turing machine. That is also called as halting problem. I'll discuss about it shortly. Now there is already a basic point or basic problem which everyone knows that it is undecidable. Okay, that is nothing but halting problem. Now you take this halting problem and then you give it to you convert it to any problem, any given problem at hand, then we can say that it is undecidable. And now you take this problem and you convert it to any other problem, then you can say that it is undecidable. So that is how undecidability is decided. Okay, undecidability is found out. So given any problem, first you start with the halting problem, convert it to some other problem, convert it to some other problem. Whatever you get on the way, all these problems are undecidable. Complexity classes means there are some set of problems which are called P class and some set of problems which are called NP class. Anyway, I am going to discuss about this topic in depth when we discuss about algorithms. In algorithms, I am going to take about this topic in depth, in detail. There we are going to take an algorithm and then see how to classify P and NP. But here we are interested in taking a Turing machine, and in terms of Turing machine, I am going to define what is P and NP. But then people, generally people are not interested in talking about these complexity classes coming to Turing machines. So I am just going to give you definitions and leave it here. But then the detailed explanation I'll give you at the algorithms course. Anyway, before going ahead, I'll just tell you what P and NP is. I told you that a problem is decidable if there exists a polynomial time, not a polynomial time, if there exists a Turing machine or an algorithm, that's it. So, but then when I say that there is an algorithm, we are not actually interested in all the algorithms. Even though there are some algorithms, we will not be able to implement some algorithms as a program at practice. Theoretically, if there is an algorithm, it does not mean that we could apply that algorithm at practice. The reason is, That algorithm, if I implement as a program, that might take lots of resources like CPU time or memory, so or number of copies of computers. So some problems, even though they have algorithms, I am not going to implement them as a program, because not even today's computer, even in future, if there is a supercomputer, even that supercomputer will not be able to compute those algorithms efficiently in the sense in less time or less energy or less space. Okay, now we are interested in finding out the algorithms which can be easily implementable as a practical program. That is what the entire purpose is. Okay, so now we know that there are various types of Turing machines, and I told you that all the Turing machines are equivalent in power, either deterministic or non-deterministic or single tape or multi-tape. All the Turing machines are equivalent in power, which means the number of languages accepted by every Turing machine is same. If some Turing machine is accepting some language, we would accept the same language using some other Turing machine, unless you restrict the way tape is used. That is a completely different topic. If you do modifications enhancing the power of a Turing machine, still all the Turing machines are equal. But then some Turing machines are better compared to other Turing machines for some problems. For example, if I take a language, I already gave this example. If I take this language a power n, b power n, if I use a single tape deterministic Turing machine, the time taken to accept a string of length n is order of n square, isn't it? If I have a single tape deterministic Turing machine, a time taken to accept a power n, b power n is order of n square. The reason is, if you have a so on n times and b so on n times, in order to match one a with one b, the number of cells I might have to cross is order of n, isn't it? I have to go there and again come back, isn't it? Which means 2n, which is nothing but order of n. Then how many such a's and b's have to be compared? N. Therefore, it is going to be order of n square. But for the same problem, if I apply a multi-tape Turing machine, then what I could do is, I'll have a so on n, and then b so on n in one tape initially. Then I'll copy the entire input onto the second tape. Therefore, since I have multi-tapes, okay, I'm talking about a Turing machine with multi-tapes, then I can directly in one scan, I can match AB like that. Therefore, here the time taken is order of n. So what I mean to say is, the time taken to solve or the time taken to accept a string of length n, it may vary significantly based on the type of Turing machine. But then every Turing machine can accept the language. Therefore, all the Turing machines are equivalent in power. No problem. There is no argument about that. But only I am trying to say is, depending on the type of Turing machine, some Turing machines can do some work faster and some Turing machines can do some work slower. And it is very, very easy to see that non-deterministic Turing machines will do any work very fast compared to deterministic Turing machines, isn't it? But then we cannot implement a non-deterministic Turing machine at practice. The reason is, non-determinism means what? At any point, it is making two copies of itself. At any point, it is making two copies of itself, which means if I have to implement such a program practically, your computer has to make two copies of itself, which is nothing but we need more and more resources. If the size of n increases and at every phase, if you are simply replicating the copies, then what happens is, see this, a non-deterministic Turing machine at every point is going to, at some point is going to replicate like this, right? If at every point it is going to replicate like this, if I have to implement it as a practical algorithm, then what happens is, our computer should be able to split itself into these many, or you should have overall these many machines in order to implement this program, that particular Turing machine. Which means the requirement for the number of resources is going to be increased exponentially in case your algorithm is in case if your Turing machine is non-deterministic. But what is the effect we get? Our work will get done very fast. But then still, even though our work will get very fast, easily done, we are not really going to use such algorithms. Got it? Therefore, even though there are algorithms, we are not going to use the algorithms which are actually equivalent to non-deterministic Turing machine. We are going to do the algorithms which are equivalent to deterministic Turing machines. Okay. Now, depending on that, what are easy to do and what are not easy to do, or I mean, what are easy to do by deterministic and not by non-deterministic, we have divided the class of problems into two types. One thing is for sure, there are some problems for which there is no halting Turing machine. We have taken it out. And in the remaining problems, again we are dividing it like this. The problems which can be solved by a deterministic Turing machine using multi-tape, and the problems which can be solved by a non-deterministic Turing machine using multi-tape. Got it? So all the problems cannot be solved. For every problem there is no Turing machine, but then among the problems for which there is Turing machine, again there are two types: deterministic Turing machine and non-deterministic Turing machine. Got it? So deterministic Turing machine problems are called P class and non-deterministic Turing machine problems are called NP class. Therefore, we are interested mainly in P class. All the practical algorithms are generally P class. If we have any NP class problem, we don't use that algorithm at practice. Instead of that, we use something called as heuristics. I'm going to talk about in algorithms course. Now just see the definition here. The set of all languages that are accepted by some deterministic Turing machine in polynomial time. What is polynomial time? Order of n power k. This k can be any number, that we don't worry about it. So the set of all languages that are accepted by some deterministic Turing machine in polynomial time is called P class. So you take all the problems which can be accepted by a deterministic Turing machine, and remember that this deterministic Turing machine can have any number of tapes. There is no restriction on that. Our practical computer can use any number of tapes, okay, which means any number of data structures, right? Therefore, such problems are called order of n power k. So we generally take such an algorithm and we generally implement it as a program in the computer. NP class is the set of all languages accepted by non-deterministic Turing machine polynomial time is NP. So if you take all the Turing machines, which are the languages which are accepted by non-deterministic Turing machine. Non-determinism means they can multiply themselves, right? They can make copies of themselves. Non-deterministic Turing machine, and here also remember that either this or this, there can be multiple tapes. In polynomial time is order of n power k is NP. It is very clear to see that if a problem is solved by a deterministic Turing machine in polynomial time, definitely it could be solved by a non-deterministic Turing machine in polynomial time. Therefore, it is very easy to see that P is here and NP is here, which means for every problem where there is a deterministic Turing machine, for every language where there is a deterministic Turing machine, for that there will be a non-deterministic Turing machine as well, isn't it? Therefore, it is very easy to see, but then we don't know whether P equal to NP or not. Till now, one question is still open, which means is P equal to NP? No one is able to prove it, but then we are just started believing that P might not be able, P is not equal to NP, but then we are not sure it. In future, if someone says that, or if in future if someone has proven that, okay, that one we shall discuss in algorithms. Just now, leave it, okay? Just understand these two definitions, okay? Now, the main question is P equal to NP? So no one has ever given that solution. So when will P be equal to NP? P will be equal to NP if whatever problems were solved by non-deterministic Turing machines in polynomial time, if they could be solved by a deterministic Turing machine in polynomial time, then we can say that P equal to NP. But now, till now, no one has ever given an algorithm which will take a non-deterministic Turing machine and convert it into a deterministic Turing machine in such a way that the language accepted will be order of n. See, for every it is all okay. One more thing, I have been using problem and language interchangeably, so don't worry about it. Both are same. Either I say a problem or a language, both are same. So if I say language, it is nothing but set of strings. When I say problem, it is nothing but set of instances. Every instance of the problem can be compared to a string in the language. That is first thing. And next thing is, now whenever I say that for every deterministic non-deterministic Turing machine, definitely there will be a deterministic Turing machine. But the problem is, once we convert that non-deterministic Turing machine to a deterministic Turing machine, the time taken by the deterministic Turing machine to solve the same problem will be exponential, not polynomial. Which means, see this, I told you that all the Turing machines are equivalent. If a problem or a language is accepted by a non-deterministic Turing machine, there will definitely be a deterministic Turing machine which will accept the same language. Okay, but then the problem is when you convert a non-deterministic Turing machine which is solving a problem in order of n power k, a polynomial time, into a deterministic Turing machine. We can solve it, we can convert it. There will definitely be a deterministic Turing machine which solves the same problem. But the problem is the time complexity required is becoming exponential, which means by taking the same time, both the machines are not able to solve the given problem in polynomial time. When I convert the non-deterministic machine to deterministic machine, it is actually taking order of 2 power n time. I'll just give you a small example of this thing. I'll just give you a small example explaining you this concept of converting a non-deterministic Turing machine to Turing machine and then telling you what is happening here. But then this should not be taken as any valid proof for the for saying P is equal to NP or P not equal to NP. The small problem is this. See this? If I have a Boolean expression A or B or C. Okay. Now, what are the values? The A and B and C, A, B, C are Boolean variables. Boolean variables means they can take a value of 0 or 1. Okay. Now, what are the assignments of, or tell me at least one assignment of 0 and 1 to A, B, C in such a way that this expression becomes true. True means 1. If that is the question, then the problem is our deterministic Turing machine will have to go through all possible values. So how many possible values will be there? If you write, if I have n variables like this, and if every variable is having 2 chances, true or false, then how many possibilities will be there? 2 power n. Then our deterministic Turing machine is going to take 2 power order of 2 power n time. The reason is it has to take every possibility and check it. But then on the other hand, what our non-deterministic Turing machine will do is, it will simply make a copy of itself. How many copies? 0 to 2 power n copies. And then like this. For A, our non-deterministic Turing machine will be starting at here. And then for A, it will one copy will assume A equal to 0 and other copy will assume A equal to 1. Depending on that, we got 2 Turing machines. And again at B, one copy will assume B equal to 0, B equal to 1, B equal to 0, B equal to 1. And again here, C equal to 0, C equal to 1. Therefore, we are going to get nearly all 8 Turing machines for every combination, and at least one Turing machine is going to say yes. Got it? Therefore, in just order of n time, we are able to solve the problem using the non-deterministic Turing machine. But then using a deterministic Turing machine is going to take order of 2 power n. The reason is we have 2 power n rows or 8 rows, and every row has to be examined by only a single instance of machine. But here the work is being done parallelly, therefore we are able to do this in polynomial time, here exponential time. So for every problem which can be solved by non-deterministic Turing machine, there will be a deterministic Turing machine. But the time taken by the non-deterministic Turing machine, if it is linear or polynomial, the time taken by the deterministic Turing machine for the same problem might sometimes go to order of 2 power n. Got it? But then there is no valid proof, which means no one has ever proven that, there is no way we could find out a deterministic Turing machine which can solve a problem in polynomial time like non-deterministic Turing machine, nor no one has ever given a proof saying that there is at least one problem for which there is non-deterministic Turing machine, but for which there is no deterministic Turing machine. As of now, P equal to NP or not, it is unknown. Got it? Got it? So we are going to look at this P and NP class in detail again at later in algorithms. There I am going to talk about some other things like what is NP hard, what is NP complete, and then I am going to compare everything. Okay, so this is all about Turing machines, and coming to Turing machine terminology, what is the complexity classes? Fine. See this? The problems I'll just read out for you. Just zoom in this area. Okay. Now see this. The problem is, does W belong to L? Which is nothing but, given a language, some representation of the language like finite automata or Turing machine, some representation, and then given a language, given a string W, does it belong to the language or does it not belong to the language? It is nothing but membership problem. And next one is L equal to 5, which means is the language empty? It is called emptiness problem. And next one is L equal to sigma star? Sigma star means does L contain everything in the universe? Sigma star is the universal language, isn't it? So if L equal to sigma star means does L contain all possible strings? That is called completeness problem. Other name of it is completeness problem. And now L equal to L2, L1 equal to L2, which means given two languages of same type, either regular or context-free, are they both equal or not? Equality in the sense, are they both containing same strings or are they going to contain different strings? Is L1 subset of L2? So L1 subset of L2 means, given a language L1 is the other and language L2, both are of same type, is one language a subset of other language? Subset, you know that, right? It is also called as subset problem. So remember one thing, whenever I say L1, L2 here, L1, L2 here, L1, L2 here, I am assuming that both L1, L2, this problem is discussed given when both L1 and L2 are of same type. Either they could be regular or context-free or CSL, whatever it is, both are of same type. Okay. And next one is L finite or not? It is also called as finiteness problem. Finiteness. Next one is complement of L a language of same type or not? Which means if I take a language L and if I complement it, is its complement the same type or not? Is intersection of two languages same type? If I take L1 and L2 and if I apply intersection, is the resulting language same type? For example, if I take regular and intersect it, then is the resulting language also regular or is it not regular? Okay. Next one is L regular language? Which means given some representation like a Turing machine, is that language regular or really recursively enumerable? Or given a context-free grammar, is that language regular or context-free, like that? So even though a language is regular, you know that still we can give a Turing machine for that. Therefore, given a Turing machine, you should be able to say whether it is regular or not. So all these are the problems. Now, when we ask such a problem for one particular type of language, whether there exists an algorithm to answer it or not, that is what I want to do. Okay, so what the question is, these are all problems. Now, when this problem is applied to some particular type of languages, now the question is, for that kind of languages, is that problem decidable or not? Which means for that problem, will there be a algorithm or not? Okay, so just you can just copy it all. I'll just tell you how to remember it. You can just take this, pause it, show this all in one frame. Is it possible? So you can pause it and just copy down the, okay. So you can just copy it down, and now I'll tell you how to memorize it. See, whenever you find out that something is undecidable for a smaller type of language, if for a smaller type of language it is undecidable, obviously for the other languages, bigger languages, it is undecidable. Therefore, remember it, whenever you start undecidable somewhere, the entire row should contain undecidable from that point on. So that is a hint. Okay. And what are the main important languages that you should remember is, one thing is for sure, for regular languages everything is decidable, that is for sure. And for recursively enumerable languages, nothing is decidable. All these problems are undecidable. These two things you need not remember at all. So what is it? For regular languages, everything is decidable. For recursively enumerable languages, nothing is decidable. And for recursive languages, only membership is decidable and nothing else is decidable, which means only this is decidable and nothing else is decidable. Oh, there is one more, is complement. Yes, complement is it is also decidable. Okay, so apart from complement and the membership, nothing is decidable for recursive languages. For recursive enumerable, nothing is decidable, and for this only two exceptions. And now it is very simple. See, I am saying that for regular, everything is decidable. For recursive enumerable, everything is decidable. And for recursive language, only two things are decidable, and apart from that, everything is undecidable. And you need not worry about deterministic context-free languages and CSL. Generally, they will not be asked. And the one important one is CFL. So you have to by heart only CFL. So CFL is important. Maybe it, 3 times there it is decidable and all the others are undecidable. You just remember what are the problems that are decidable. Then obviously the remaining are undecidable, right? So questions will be 1 regular, 2 recursively enumerable, 3rd recursive, and 4th one is CFL. So CFL only 3 are decidable. Okay, remember what are decidable and the remaining are undecidable. So these 4 classes are important: regular, CFL, recursively enumerable, and recursive. Now let's see the properties of context-free languages. In context-free language, see, if a language is context-free, definitely there will be a context-free grammar. Let us say 2 context-free languages are given, L1 and L2. Then definitely there will be context-free grammars, right? Context-free grammar, let me say CFG1 and context-free grammar 2. And each context-free grammar is going to start with a start symbol, isn't it? So let us say the start symbol for context-free grammar G1 is S1. S1 derives, it is going to start like this. And the context-free grammar this one is going to start with S2. S2 derives, it is going to start like that. Now, if I want to combine these 2 languages, which means if I want to apply the union, what does that mean? The resulting language should have all the strings or should have all the strings of L1 as well as L2. Therefore, what I do is, I'll write a new grammar S derives S1 or S2. So, if you want to derive any string which is present in the language L1, you start with S1, which means from S you start with S1, and S1 is going to generate the string which is present in the language L1, right? Or if you want a string which is present in language L2, then from S you start with S2, right? Then you are going to generate a string which is going to be present in the language L2. Got it? So if whatever you want to generate, you could choose appropriate start symbol, and since this is the resulting grammar is also a context-free grammar, the resulting language L1 union L2 is context-free. How did we do this? Find out the context-free grammars and you just apply the slash and you put a new symbol, isn't it? It is straightforward. And next one is, if L1 is a context-free grammar and L2 is a context-free grammar, L1 concatenated with L2 is again a context-free grammar, context-free language. So if 2 context-free languages are given, the concatenation is also a context-free, which means context-free languages are closed under concatenation. How can we prove it? You start a new start symbol with S1.S2. If this one is having a context-free grammar which is starting with the start symbol S1, and if L2 is having a context-free grammar which is starting with the starting symbol S2, then you write a new grammar which is going to start with a start symbol S and which is having S1 followed by S2, and all the remaining productions are same. For all the S1 and S2, you add all the productions of language L1 and L2. Here also you add all the productions of language L1 and L2, right? It is fine. And now, after concatenation, let us say closure. Closure means if you have L1 as a context-free grammar, then L1 star should, what can you say about the L1 star? It turns out that even L1 star is context-free, which means context-free languages are closed under closure operation. So how can we prove it? If L1 is a context-free language, then there will be a context-free grammar which is starting with some symbol S1, right? Now what we want to do is, we want to repeat the number of strings in L1 as many times as possible. Then I am going to introduce a new grammar which is having S1s or epsilon. So what is the meaning of it? If you want to generate epsilon, it will generate it. If you want to generate one string from S1, you can take this one and then S will go to epsilon. If you want to generate 2 strings from S1 concatenate with S1, then what you do is, S will generate S1 concatenated with S, and again S will generate S1 concatenated with S, and wherever you wanted to stop, you can stop it. Now if you want 2 strings, yes, you got 2 strings. If you want 3 strings, you extend it. Therefore, by using this rule, you can generate closure of the language. Therefore, context-free languages are even closed under closure. They are closed under union, concatenation, as well as they are closed under clean closure. Got it? Context-free languages are not closed under intersection and complementation. We shall prove it with a counterexample. See, now I'm saying that context-free languages are not closed. Till now we have seen the closure properties. Now I'm saying that they are not closed under intersection. Intersection is if I take two context-free languages, L1 and L2, and if I do the intersection, then the resulting language might not be context-free, which means the resulting language need not be context-free all the time. It might be some other language also. So how can we prove this? If you have to prove it, find at least take two context-free languages in such a way that at least one example should give us a language which is not context-free. So let's see which examples will be better. See, this is called proof by counterexample, which means I'm assuming that context-free languages are closed under intersection. Then I'll find out an example which will show that actually intersection of two context-free languages, we are not getting the context-free. But then there will be other examples where when you apply the intersection of context-free languages, then the resulting might be context-free language, but it doesn't prove that they are closed, isn't it? In order to prove that they are not closed, you find out one example which says that they are not closed. But then if you find an example which says that they are closed, it doesn't mean that they are closed. Okay, it is like this. See, if you want to prove that some person is bad, you can find out one bad thing which is done by that person and you can say that he is bad. But then if you want to prove that a person is good, one good thing is not going to be enough. It has to be his entire lifetime in which there is no bad thing, isn't it? Similarly here, if you have to say that the context-free languages are closed, you have to take every possible languages, all possible languages, and apply the intersection and find that all the languages or the resulting languages when you apply the intersection are actually context-free. Got it? But then if you can find out at least one example in which the resulting intersection is not context-free, that is enough to say that the languages are not closed under intersection. Now just see this. Let us say you already have seen this example. L1 equal to a power n, b power n, c power m such that n comma m greater than or equal to 0. Do you remember this? We have already seen this example, isn't it? So this is definitely context free. How? You generate a and b together using a variable, and then you generate c separately using a variable, and then you concatenate them. This is context free. We did both the context free languages, the context free grammar as well as PDA for this example. And let us say L2 equal to a power m, b power n, c power n such that n comma m greater than or equal to 0. So what does language L1 say? That the number of a's and b's are equal. And what does language L2 say? That the number of b's and c's are equal. And when I apply L1 intersection L2, see, it is most confusing. Many people get confused here. Okay, so think about it. So what are the strings that we get in L1 intersection L2? I am saying that the strings which will be present in the intersection will be a power n, b power n, c power n. It is very easy to see it, but then I don't know why people get confused in this. See, if a's and b's are equal in L1 and b's and c's are equal in L2, if the string has to be present in both L1 and L2, obviously all of them have to be equal. You please work it out on math. Okay, what you could do is take some examples and work it out. See, if L1 is containing all these strings in which a's and b's are equal, and L2 is containing all these strings in which b's and c's are equal, then definitely L1 intersection L2 will contain the strings in which a, b and c are equal. Otherwise, they will not be present. See, a string is present in here, which means a's and b's are equal, and a string is present here, which means cc. A string which is present here is also present in L1, which means a's and b's are equal. A string which is present here is also present in L2, which means b's and c's are equal. Therefore, applying these two rules, a, b and c's are equal, isn't it? Therefore, I got this one. I don't know where people get confused. Whenever I teach this in the classroom, they'll generally have this doubt. How did you write this? Maybe for me it is just easy. You just think about it. You please work on it. And A and B, see, this language is definitely not context free. We have seen it. There is no context free grammar for this one. or there is no PDF for this one. We have already seen it, right? And it is actually context sensitive language. We have seen the context sensitive grammar also. You please refer to the context sensitive grammar's concept. Okay, so anyway, this is not context free. Therefore, what can we say? The languages, context free languages are not closed under intersection. And we can even extend it and say that context free languages are not closed under complementation also. So how can we prove it is? Using this proof, now we have already shown a proof that context free languages are not closed under intersection, isn't it? Now L1 intersection L2 can be written as L1 complement union L2 complement whole complement, right? Now let's say, just for the sake of assumption, so it is called proof by contradiction, which means I'm going to assume something and again I'm going to prove that my assumption is wrong. I'm assuming that context free languages are closed under complementation. Then what happens? If they are closed under complementation, if L1 is a context free grammar, context free language, L1 complement should be context free. If L2 is a context free language, then L2 complement should be context free, right? And we already know that union of two context free languages is context free. Therefore, this entire thing must be context free. And I'm assuming that the complement of a context free is context free. Therefore, this entire thing should be context free, which means this one is now turning out to be context free. So if I assume that L1 complement is context free, then what is that we are getting? We are getting that L1 intersection L2 is also context free. But then it is already shown that L1 intersection L2 is not context free. Therefore, our assumption must be wrong. What is our assumption? That the complementation of a context free language is context free. So it is not true. Therefore, what can we say? Context free languages are not closed under complementation. So it is very important to remember, context free languages are not closed under intersection, as well as they are not closed under complementation. Look at these properties of regular languages. So there is something called as closureness or closure, or let us say there is a term called as closed under some operation. What I mean by closed under operation is, if I take set of all natural numbers, let us say this is set of all natural numbers, then set of all natural numbers is closed under addition. So what I mean by this is, if I take any two natural numbers from the set of all natural numbers, and if I apply the addition on those two natural numbers, then the resulting is also a natural number. That is called closed under addition. So this set natural numbers, the set of all natural numbers is closed under addition is, if I take any two natural numbers or any two elements from this set, and if I apply this operation, if the resulting whatever I get as the result also belongs to the same set, which means if I add two natural numbers, if the result is also going to be a natural number, then I can say that set of all natural numbers are closed under addition. Similarly, whenever I take regular languages, set of all regular languages, if this is the set of all regular languages, and if I apply some property on the set of all regular languages, if I take two regular languages and if I apply some property on that, some operation, and if the resulting language whatever I get, it also belongs to the set of regular languages, which means after taking two regular languages and applying a operation, if the resulting language is also regular, then that operation is said to be closed under regular sets, or regular languages are said to be closed under that operation. Terminology is regular languages will be closed under some operation, not operation will be closed under regular languages. Okay, so when can we say that regular languages are closed under some operation? You take two regular languages and you apply a property on that. If the resulting is also resulting also belongs to the same set, then we can say that set of all regular languages are closed under that particular operation. And now let's see how to prove it, which means let's see some of the properties and I'll show you how to prove them. See, for regular languages I'm going to prove all the properties, but for the other languages, context free, contextually I'll prove some of them, and for the other languages like recursively enumerable and recursive context sensitive, I'll just give you a table. You refer to the table. That table is good enough. Okay. Now just watch it. If L1 union L2, see, what can you say about the regular languages under union L1 union L2? So if L1 is a regular language and L2 is a regular language, then definitely L1 union L2 will also be regular language, which means set of all regular languages are closed under union. How can I prove it? If it is a regular language, there will be a regular expression, let us say R1, and if this is a regular language, there will be a regular expression R2. Then union of these two languages is nothing but putting a plus in the middle, isn't it? And then intersection, okay, intersection we shall prove it later. And let's talk about concatenation. If L1 is a regular language and L2 is a regular language, then L1 concatenated with L2 is also regular. How can I prove it? Same way, if you take the regular expression R1 for L1 and you take the regular expression R2 for L2 and you just apply the concatenation, then whatever language we get or whatever expression we get is again a regular expression. So since it is a regular expression, the language which resulted must be regular, isn't it? Then what about closure, clean closure? Same thing you can do. If L1 is a regular language, then you can find out a R1 which is a regular expression for this language. Then L star, clean closure of the language, is nothing but the clean closure of the regular expression, and the resulting regular expression is also a regular expression. The resulting expression is also a regular expression. Therefore, you can say that the resulting language is regular. And now let's prove that L1 complement is a regular expression. L1 complement is regular. So if L1 is regular, then L1 complement is nothing but sigma star minus L1, isn't it? Which means if this is the set of all strings and if this is L1, then whatever is outside L1 is L1 complement, isn't it? Now what I want to prove is, if I take the complement of a language which is regular, then the resulting language is also regular. In order to prove this, it is already given that L1 is regular. Therefore, there will be a DFA for that, right? And now we complement the DFA. Then what we get? Again, we get one more DFA, which will be accepting the complement of the language, given language, which is L1 complement. Since we got a DFA for the language, therefore L1 complement is also regular. How to complement a DFA? I have already given you examples. You please check on that. So complementing a DFA is nothing but construct the DFA and then make the final states non-final and non-final states final, which means only thing that changes here is in the final states. Look at this. So if you have Q, sigma, delta, Q naught and capital F representing a DFA, then complement of the DFA will be Q, sigma, delta, Q naught, and the final states will be just the states which were non-final before. What are the states which were non-final before? Q minus F. This is complementation. If this is the DFA for the given language, we got one more DFA which accepts the complement of the language. Therefore, we can say that complement is again closed, which means complement is also a regular language. Almost every property about regular languages is closed. So one good thing about regular languages, everything is closed, everything is decidable, everything is simple. Okay. And now let's prove that intersection is closed. So intersection proof is actually beautiful because it is an example of a constructive proof. Constructive proof means we'll prove something else before and then based on that we derive this. That is called constructive proof. So there are various types of proofs. You can prove by contradiction, you can prove by induction, you can prove by construction. Construction means we build some other proofs and then we show that this is true. So in order to prove that L1 intersection L2 is regular, I would rewrite this L1 intersection L2 like this: L1 complement union L2 complement whole complement. If I write this, both are same, isn't it? So we have already shown that L1 complement is regular, L2 complement is regular, and union of two regular languages is again regular. Therefore, this entire thing is regular, and again a complementation of the regular language is regular. Therefore, this is regular. Okay, understand this. L1 is already given as regular, L2 is already given as regular. So complementation of two regular languages are already regular. Therefore, this one is regular and this one is regular. And then we are applying union to two regular languages. Therefore, the resulting is regular. And then we are simply complementing it. And so, the complementation is also closed. Therefore, the resulting is regular. So, finally, the intersection of two regular languages is always regular. So, what can we say? Regular languages are closed under intersection. Okay. Look at these two properties. Regular languages are closed under difference, which means if I have one language L1 which is regular, and if I write L1 minus L2, I'm saying that the resulting language is also regular. How can we prove this is? It directly comes from the proof of intersection. Already we know that intersection is regular, right? So we can write it like this. Difference is nothing but L1. See, I'm talking about the first property, not the second one. I'm talking about the first one, then I'll talk about the second one. Second one is regular languages are closed under reversal. First one is regular languages are closed under difference. So L1 minus L2, I can write it as L1 intersection L2 complement. These two are same. Therefore, already we know that this complementation is closed, which means this is regular. Why? Because L2 is regular. Therefore, L2 complement is regular, and two regular languages are now applied intersection. Therefore, the resulting is regular. So, difference is always closed under, regular languages are always closed under difference. This is the proof. And what about this reversal? I told you how to reverse a language of a DFA, or I told you how to reverse a finite automata. That method was applied both for DFA as well as NFA. Do you remember that reversal? How to do the reversal is, you please refer to that examples, and I'll just tell you how. Make the final state as initial state and initial state as final state, and you just reverse all the transitions. That is nothing but reversing a finite automata. Now I'm saying that regular languages are closed under reversal. So what does it mean? You take the DFA first, or NFA, anything. DFA or NFA, both will do. Even Epsilon NFA will also do. And now you apply the reversal of the DFA. Then again we get a finite automata which will be either DFA or NFA. Okay. And now you can find out that the resulting finite automata, if this one is accepting L, the resulting finite automata will accept L power R reversal. I hope that you remember what reversal of a language is. String reversal is if you take a string and if you reverse it, that is string reversal. Language reversal is if you take every string in the language and if you reverse it, that is language reversal. Now let's look at this. The function h from sigma to tau star is called homomorphism. So what it means is, if you have an alphabet, which means input symbols, and in every symbol, for every symbol in the input, if you substitute a string from some other alphabet, then it is called homomorphism. And it is known that it can be proven that regular languages are closed under homomorphism. So before going ahead and seeing the proof, I'll just give you an example and explain you what homomorphism is. Let us say we have a input alphabet A comma B. Then if it is defined, a H is defined, that a homomorphism is defined in such a way that for every small a in your input, if you substitute a string from some other input, let us say some other input is 0, 1, 2, some other alphabet is 0, 1, 2, and now for every symbol here, if you substitute a string from that particular some other alphabet, then it is called homomorphism. So once you define this homomorphism, then we call it as homomorphic image of a language or a string. So what we do is generally so initially sigma is defined, which is your alphabet, and then tau is defined, which is some other alphabet, and now this mapping is defined for every symbol. For every symbol in your alphabet, there has to be some string. Once this mapping is defined, then for a given string from this alphabet or for some language we are going to find out the homomorphic image. So what is homomorphic image of a string? Let us say a string is ABA. What is homomorphic image of the string ABA? According to this homomorphism is, in place of A you have to substitute 0 1, and in place of B you have to substitute 1 1 2, and in place of A again you have to substitute 0 1, isn't it? So it is nothing but homomorphic image of a string, right? And then what is the homomorphic image of a language is, you take the language and in every string you find out the homomorphic image, then it is nothing but the homomorphic image of a language. So what is the homomorphic image of a language is, I'll just take an example of a language. Let us say language A is, some language L1 is A star B. It is a regular language, isn't it? And now the homomorphic image of this language is, in this language take every string and in place of every string you put the homomorphic substitution, which means whatever is the homomorphism is substituted there. But then taking every string and doing it is as good as taking the regular expression, and in the regular expression you do it. So in the regular expression we have A star B, isn't it? So take this regular expression and do it. In place of A, what should you substitute? 0 1, 0 1 star, and in place of B, what should you substitute? 1 1 2, right? Therefore the homomorphic image of this language is this one. So now I'm saying that regular languages are closed under homomorphic image. It is a proof also. The reason is, we have taken if the language is regular, there will be a regular expression. Now take the regular expression, and in the regular expression for every input symbol you substitute the homomorphic image, then you are going to get one more regular expression, isn't it? It is a regular expression. Therefore the resulting language is again regular. Therefore regular languages are closed under homomorphism. Okay. If you apply the reverse of the homomorphism, then it is called inverse homomorphism. The same way where we are taking one alphabet and taking it to some other strings of other alphabet, we could take the strings of other alphabet and bring them back to the original alphabet by using inverse homomorphism. Okay. So inverse homomorphism is simply, not to understand it, you can understand it as reverse of the homomorphism, which means if homomorphism is from here to here, inverse will be from here to here. So don't worry about the definition, you might not understand it. Let's take an example, then you'll understand it better. So anyway, definition goes like this. Inverse of a homomorphic image of a language L is, H inverse of L is X in case H of X is in L, which means if the homomorphic image of a string is in language L, then that string will be in H of L. And homomorphic image of a language can be found out, and homomorphic image of a string can be found out, isn't it? Similarly, inverse homomorphic image of a string can be found out, as well as inverse homomorphic image of a language can be found out. Let's take an example. Let sigma equal to 0 1 2. So one alphabet is defined as 0 1 2, and delta equal to a comma b. Other alphabet is defined as a comma b, and we are given a homomorphic image from sigma to delta, from sigma to this delta star, which means in place of 0 a is substituted, in place of 1 ab is substituted, in place of 2 ba is substituted. Let L1 equal to ab aba, which means we are given only one string, L1 equal to ab aba, one string, and now they are asking us to find out the inverse homomorphic image of L1. So how to find out is, whenever they ask you about the inverse homomorphism, take that string and see using what combinations of the original alphabet we could form the resulting string, which means if this is the string required, what are the combinations of the original alphabet in order to form this string. So you can see that I could have substituted, if you have AB, ABA like this, AB, ABA, I could have substituted in place of AB 1, which means 1, and in place of AB 1, and in place of A 0. Therefore, what did I get? 1 1 0, isn't it? And other inverse homomorphic image is AB, ABA means in place of A, I could have substituted 0, and in case of BA 2, BA 2, which means 0 2 2. The same string can be generated with different strings. That is why I am getting more than one answer here. it is completely valid, perfectly valid. So, and one more possibility is, if I have AB, ABA, I could have substituted in place of this 1 and in place of this 0 and in place of this 2. Therefore, other homomorphic image is 1, 0, 2. Therefore, for a given string, I have got 3 inverse homomorphic images. Now, if we again try to convert this to the actual one by applying the homomorphism, but you will get only one string. Okay, so just remember that if I apply the reverse again, I get only one string. Okay, now watch the other one. Let us say we have x equal to L2 equal to A, BA star B. This is the language given, and now I want to find out the inverse homomorphism of that language. It is always better to convert the language into strings or enumerate the language, and then you go on back substituting it. That is the best way possible. So if this is the string given, now I am just writing that string in terms of, if this is the regular expression, I am just writing it in terms of all the strings. Then these are all the strings I got. Then inverse homomorphic image of the language is, see this, for A I get only one combination, which is 0. For ABA I get two combinations. AB can be 1 and A can be 0, or A can be 0 and BA can be 2. Therefore, for the second one I got two combinations, 1, 0 and 0, 2. For the third one, ABA, BA, it is same as that string. We have already seen it, ABA, BA, for which I got all this, isn't it? Maybe you could extend it further and you could even get more. What will be next string? A, BA, 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 isn't it? That is the next string. For that, what do I get? One possibility is 1, 1 in place of AB, AB, and then 1 and then 0, which means 1, 1, 1, 0. And other possibility is AB, AB, ABA. Other possibility is, in place of this I could go for 0, and in place of this 2, 2, 2. And other possibility is, if I have this AB, 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 A, other possibility is, in place of this I could go with 1, AB means, in place of 0, small a I could go with 0, and in case of BA I could go with 2, and BA I could go with 2. Other possibility is, in place of AB I could go with 1, in place of AB I could go with 1, and in case of small a I could go with 0, and in case of BA I could go with 2. Therefore, these two are possible. Anyway, what are all the possibilities is, for this language, one is 1 star followed by 0, it is an answer, or you could have represented as 0 followed by 2 star. See, 1 star followed by 0, it will generate everything, or 0 followed by 2 star, it will generate everything, or you could have even represented as 1 star, 0, 2 star. In fact, you could write all these three as an answer, or if you could observe this, the third language itself, this will properly contain these two. Therefore, you could even write this only this one as the answer. It is also valid. So, if you want to simplify the answer, this one is the final answer. Or even if you write entire three things as the answer, no problem. The reason is, finally everything means the same. But then if you look at this, in place of this star, if you put a 0, it will boil down to 0, 2 star. In place of this star, if you put a 0, it will boil down to 1 star 0. Therefore, you could go with anything, not an issue. Okay, fine. So that is how you can find out the inverse homomorphic image. Okay. Now I want to illustrate one important property of inverse homomorphism using an example. Okay, take this example. See this one. Let sigma equal to 0, 1 and delta equal to a, b. So one alphabet is 0, 1 and other alphabet is a, b, and they're defining a homomorphic function like this. So h of 0 equal to a, and h of 1 equal to aba. So which means, in place of 0 they are substituting aa, and in place of 1 they are substituting aba. So then they are asking, if this is the language given, so this is the homomorphism defined, which is in place of 0 they are putting aa, and in place of this they are putting this. And for some language is already formed over delta. Now we want to find out the inverse homomorphic image of that language. Now that language is L equal to AB plus BA star followed by A. So I want to enumerate the language first. So I have written all the strings. If this is the language given, these are all the strings. Now I want to find out the inverse homomorphic image of L. Then I'll take every string and I'll examine if I could write it in terms of 0 and 1 so that I could put it in the inverse homomorphism of the language. Now I'll take the string A. Now if I take the string A, there is no way I could either write it in terms of 0 or 1 because the string lengths are at least 2 and 3. So A is not possible in inverse homomorphic image. And what about this ABA? Yes, it is possible and it is 1. What about BAA? You cannot write either, one thing, it is not just enough that you encode a part of it in terms of zeros and ones. You should do it completely, okay? So BAA cannot be completely written in terms of ones and zeros. So there is no inverse homomorphic image of this string. And what about this one? ABA. So maybe you could write ABA here, but then the remaining string BA cannot be derived by anything, and AA is completely useless in this case. The reason is no two A's are actually together. Therefore, it is not possible to write it in the inverse. Then what about this one? AA could be written as this 0, but then ABB cannot be written as 1. Therefore, inverse homomorphic image of this string is also not possible. So, if you look at this entire language, only one string inverse homomorphic image is possible. Therefore, inverse homomorphism of this language is only 1. So, see this? Inverse homomorphic image of this language is only 1. Now, if we apply the homomorphism for this one, which means H of H inverse of L, then we get ABA. So, if I apply the homomorphism for the inverse homomorphism applied, contrary to the belief that we should get L, we got only ABA, which is not equal to L. Therefore, even though a language is given, and if you first apply inverse homomorphism, we are going to lose some of these strings. And again, if you apply the homomorphism back, we might not get the entire language. Sometimes we might get, sometimes we might not get. But actually, this subset is the true relation. It is not equal to, it is subset, and it is not proper subset. It might, which means it might not always be the case that we lose some of these strings. In this example, we lost some of these strings, but then in some other example, we might get all these strings. Okay. So anyway, what I mean to say is, in case if you try to apply the homomorphism to a language and again homomorphism, we might not get the entire language. Some of these strings might be lost in the process. Emptiness problem of finite automata is decidable. So decidable means there has to be algorithm. What is emptiness problem? Given a finite automata, we should know whether the finite automata accepts at least one string or it is not accepting anything at all, right? And it is decidable. Decidable means there has to be an algorithm. So algorithm looks like this. Select the states which are not, okay, so first of all, let's discuss about this problem for some time before going to the algorithm. See, given a finite automata, when can you say that it will accept at least one string? If there has to be a final state, at least one final state, isn't it? So, but then having a final state is necessary to accept some string, but then it is not always sufficient in the sense, even if you have a final state, one final state, it doesn't mean that we'll be able to reach that final state ever. Therefore, having a final state is not just enough. That final state should be reachable from the initial state. Then only we can say that some string is accepted by the finite automata. So, how does this algorithm look like is, first select all the states which are not reachable from initial state and delete those states and corresponding states. Which means if you are not able to reach some state from initial state, obviously they are useless. Even though you have them, we are never going to use them, useless. Therefore, you delete them. That is the first step. Now, in this step, if the final state is not reachable from initial state, that will get deleted. Therefore, if we don't accept anything, that will get deleted there itself, right? And second step is, in the remaining finite automata, whatever is remaining, if we find at least one final state. So, in the remaining finite automata, if you get at least one final state, it means that there is a final state which is reachable from initial state. Therefore, there are chances that it will accept at least one string. That is the meaning of it. Okay, so since we have an algorithm and this algorithm is going to stop in exactly certain number of steps, therefore it is decidable. I told you what is decidability is. You please refer to the concept of decidability, which is discussed at the Turing Machines concept. Decidability means we are able to give an algorithm. Since we are able to give an algorithm, the problem of emptiness is decidable. I'll just take an example and explain you what is the meaning of it. Let us say there is a finite automata like this. This is the final state. Okay. Now, even though there is a final state here, it doesn't mean that it will accept anything, because if you see it, this from initial state I'll never be able to reach the final state. That is the meaning of it. So first step says that if they find out all these states which are not reachable from initial state and you delete them completely. So in first step, this state is reachable, this state is reachable from initial state, but then this state is not reachable from initial state. Therefore, it has to be deleted. And after I delete it, I get only 3 states and none of these states are final. Therefore, you can say that this finite automata doesn't accept any string. So the language accepted by this is empty. So emptiness problem has been solved using an algorithm. Therefore, it is decidable. Okay. What's this problem? Infiniteness problem of regular language is decidable. So it means that decidable means there is an algorithm to say whether a regular language is infinite or not. So for every regular language, the basics is like this. For every regular language, there will be a finite automata, isn't it? Now let's draw the finite automata for the regular language. That is the algorithm. Okay. And now in the finite automata, I apply the algorithm like this. When do you think that a finite automata will accept an infinite language? Only when there is a loop in that, isn't it? Loop is able to generate infinite number of strings. Now, having a loop is that necessary condition or sufficient condition? Which means if I have a loop, does it definitely mean that we'll be able to accept infinite language? It is not true. Having a loop doesn't mean that we could accept infinite language. I'll give you an example of that. See this? Now, this is initial state, this is the final state, and then there is a state, but then here there is a loop. But having a loop in the finite automata doesn't mean that this finite automata is able to accept infinite language, right? So what should happen? In order to, if a finite automata has to accept infinite language, there should be 2 conditions. One thing is there should be loop, and that loop should be reachable from initial state, as well as from that loop we should be able to reach the final state. Got it? So either if these 2 conditions doesn't hold, which means if the loop is unreachable from the initial state, which means even if you have a loop here, it might sometimes be unreachable from the initial state, or from the loop you will not be able to reach the final state. Even if anything like that happens, we cannot accept infinite language. Therefore, in order to accept infinite language, the main conditions are: first thing is there should be a loop. Second thing is from initial state I should be able to reach that loop, and from that loop I should be able to reach the final state. In order to put all these points in terms of an algorithm, and in order to check whether all these points are happening or not, we have written the algorithm. See this? Step 1 is remove the states which are not reachable from initial state and the corresponding transitions. That means you should delete all the states which we never reach. Therefore, if there is any loop inside these states which is not reachable at all, that will get deleted. That is what we wanted. Therefore, in the resulting finite automata, we'll have the loops only when they are reachable from the initial state. If they are not reachable from the initial state, they'll all obviously get deleted. So see this? Now from the initial state, this state is not reachable. Even though there is a loop, this state is not reachable. Therefore, we are going to delete it. So what are remaining? Only the states to which we can reach from the initial state. Now what is the second step is, from a state, if we are not able to reach the final state, we should remove it. Therefore, the loops which are not reaching the final state will get deleted. See this? Delete the state and the corresponding transitions from which we cannot reach the final state. The reason is, if a loop cannot reach the final state, there is no way we can say that it is going to accept a infinite language. Got it? So now you delete this one, because from this we are not able to reach the final state. In the remaining finite automata, if you find at least one loop and a final state, which means in the remaining finite automata, in case if you find any one loop and final state, then we can say that it is infinite. Otherwise, it is not infinite, it is finite. In this case, it is finite. The reason is, in the remaining one, there is no loop. In case if on the path there is a loop, then we can say that it is infinite, isn't it? So by making these 2 points, we made sure that if there is any loop in the finite automata, which is reachable from initial state and from which we can reach the final state, that loop will remain in the finite automata, and we can say that it is accepted by, we can say that the language generated by that finite automata is infinite. Got it? So that is what we derived from this algorithm. Okay. So see, one more thing, when we are doing any when I'm showing this algorithm and doing some modifications on the finite automata, you should not take it that the finite automata which we get finally is equivalent to the initial final automata. I don't want to compare the languages. I just want to answer whether they are infinite or not, empty or not, like that, those questions. So the resulting finite automata is way different from the initial finite automata. This method is not actually minimizing or simplifying a finite automata. The language which is accepted by the final, whatever you get, that might not be the original language. But then what we want to derive is the answer to this question, this particular question only. We are not trying to minimize the finite automata here. Okay, fine.